In this lesson, we want to review translating phrases into algebraic expressions and equations. So for the majority of you, you've already taken an elementary algebra course, and so you have at least some experience with solving a word problem where you need to set up and solve a linear equation in one variable. So these problems are usually referred to as applications of linear equations, and this is going to be the topic of our current section of the course. So for most students, word problems are extremely challenging, and the reason for this is, in addition to solving an equation, they now have to read through a problem, interpret the problem correctly, and create an equation based on the situation given. Now, one of the roadblocks to success with word problems is being able to understand the phrases that you come across in your word problem. You have to be able to correctly translate those phrases into the required algebraic expressions and equations that are needed to get the correct solution. All right, so we're going to look at some of these phrases and just go into how we can translate them into, again, expressions and equations. We're going to start out today by looking at some common addition phrases. And so first we have for a phrase, more than. So more than is telling us we need to add. So as an example, we have 11 more than a number. Now, anytime I see a number or the number, I can replace it with a variable like x or y or z, whatever you want to use. I'm just going to use x. One strategy is just to kind of line out where you see a number and just put a variable. I'm just going to put x there. And if I read it now, it says 11 more than x. Well, that just means if I had x, I want 11 more than that. So that can be represented with x plus 11, right? This is 11 more than x. Then you have sum of. So the sum of a number and 5. So again, when I see a number, it's going to line that out and put x. Let me kind of change my ink here. So the sum of x and 5, that's just x plus 5. Then next we have total of. So the total of 9 and a number. So let me line this out and let me put x here. So now we have the total of 9 and x. So that just tells me I have x plus 9 or 9 plus x. So next we have increased by. And then we have, for our example, a number increased by 17. So where I see a number, I'm going to cross that out. Just put x. So if x is increased by 17, it's just x plus 17. Then we have plus. A number plus 2. So again, let's line this out, a number. Let's put x here. And it says x plus 2. That's just x plus 2. Very straightforward. Then lastly, we have added to. And then we see 15 is added to a number. Let me line this out where it says a number. Let me put x here. So 15 is added to x. So we have x plus 15. Okay, so it's very easy when you're working with addition because addition is commutative. The order that you add in does not affect the result. So in this case where we have x plus 11, I could reorder that and say 11 plus x. It doesn't change anything. Same thing here. X plus 5 could be 5 plus x. X plus 9 could be 9 plus x. So on and so forth. So with addition and also multiplication, they're commutative. The order does not matter. With subtraction and division, the order does matter. So we've got to pay closer attention to the way things are worded when we work with subtraction and division. So let's look at an example of some addition phrases. And we have this sample problem here. So if a number is increased by 7, the result is 19. Find the number. So again, if I see something like a number, or if I see the number, I'm just going to replace it with a variable. So I'm going to use x, but again, you can use whatever you want. So I'm just going to put that in each place. And down here, I can even specify that I'm going to let my variable x be equal to the unknown number. Let me make that e a little bit better. Okay, so what am I saying here? If x, let me write that down, is increased by, we know this is a key phrase that means plus. So x plus, we have our number 7. It says the result here is 19. So when you see is in this context here, it means equals, okay? So we're going to put equals here, and then we have 19. So once again, if x is increased by, we have our x here. Increased by, again, means plus. Then we have 7. 7's here. The result is, that means equals. And then we have our 19, so our 19 is here. So we want to find x, and all we need to do is just solve this guy. So I'm going to subtract 7 away from each side of the equation, and that's going to give me that x is equal to 12. And you can read back through the problem and determine if you got the right answer, right? If 12 is increased by 7, the result is 19. Well, yeah, that's true. 12 plus 7, or 12 increased by 7, is 19. So if we want to find the number is just 12. Okay, let's take a look at another one. So if a number is added to 12, the result is negative 11. We want to find the number. So again, if I see a number, or I see the number, I'm just going to replace that with a variable, and I'm going to use x. And again, I can label this down here and just say that we're going to let x be equal to the unknown number, okay, just for clarity. And again, if x, so I'm going to read it like that. So if x is added to 12, so is added to just means plus, so x plus and then 12. The result is, okay, in this context, this means equals. Then we have negative 11, okay? So if x is added to 12, so x plus 12, the result is, or the result equals, negative 11. So that's how we got our equation. Then we want to find x, or find the number. So again, I just want to solve this guy. Let me subtract 12 away from each side of the equation. I would have that x is equal to negative 23, right? And again, reading back through the problem, if negative 23 is added to 12, the result is negative 11. That is true, right? So our number here is negative 23. Okay, this is what we're looking for. All right, let's look at some subtraction phrases. Again, you've got to pay close attention with subtraction because it's not commutative, right? If I have something like 10 minus 5, this is not equal to 5 minus 10. I can't switch the order there like I can with addition. Right? If I had 10 plus 5, that is equal to 5 plus 10. With addition, I can change the order. With subtraction, I cannot. Okay? So one of the phrases is minus. Okay, we all know minus means subtraction. Something like 12 minus a number. So I'm starting with 12, and I'm subtracting away a number. So again, every time I see a number, I can line that out and just put x. So 12 minus x is 12 minus x. Again, if you put x minus 12 there, it's not correct, right? This would be wrong. This would be wrong, okay? So you've got to make sure you go in the correct order. 12 is what I'm starting with, and then minus my variable x, or my unknown number. Then we have less than. So 14 less than a number. Okay, let me line this out and put x here. So again, very important to interpret this correctly. We want 14 less than x. So that means I'm starting with x, and I want 14 less than that, so I'm going to subtract away 14. So this translates into x minus 14, not 14 minus x. Okay. Next, we have less. So a number less 8. Okay. Again, a number, I'm going to cross that out and put x. So x less 8. That means I'm starting with x, and I'm taking away 8 from that. Okay, another one is subtracted from. So again, a number subtracted from 19. So let me line this out and put x. So we have x subtracted from 19. So pay attention there. It's subtracted from 19. So I'm starting with 19, and I'm subtracting away x. Okay, so this is 19 minus x. Then we have decreased by. So a number decreased by 4. So let's line out a number and put x. So if x is decreased by 4, it's just x minus 4. Then we have difference of. So the difference of 5 and a number. So you've got to go in order here. Remember, when we talk about the difference, that's a result of subtraction. So the difference of 5 is going to go first, and a number, let me line this out and put x. The difference of 5 and x would be 5 minus x. If it said the difference of x and 5, that would be x minus 5. So you've got to go in order. Then we have take away. So a number is taken away from 15. So again, for a number, I'm just going to put x. So x is taken away from. Okay, it's taken away from 15. So 15 starts out, and then we take away our x. Okay? So again, with subtraction, the order matters. So you've got to correctly interpret these, otherwise you will not get the right answer. So let's look at some examples. All right, so we have that 4 less than a number is 29. Find the number. So again, wherever I see a number or the number, I'm just going to replace that with a variable. Again, I'm going to use x. And again, for the sake of completeness, I'm just going to say we're going to let x be equal to our unknown number. Okay. So 4 less than x, right? Think about that. That means I have x and I want 4 less than that. So x minus 4. Then we have is. In this context, that means equals, and then 29. So to find the number, I would just add 4 to both sides of the equation, and we get that x is equal to 33. Right? So if I had 4 less than 33, that would be 29. So the number is 33. All right, next we have the difference of a number and 7 is 13. Find the number. So again, where I see a number and the number, I'm just going to replace that with a variable. So we'll use x again. And again, for completeness, I'm just going to say that we're going to let x be equal to our unknown number. Okay, so what can we say here? The difference of, we have x and 7. So the difference of x and 7, x comes first, so we'd have x, and then we have minus, we've got our 7, and then we've got our is, okay, this means equals, and then we have 13. So essentially we have x minus 7 equals 13. To solve this for x, we add 7 to both sides of the equation. We get x is equal to 20. So the difference of 20 and 7 is going to be 13. That's correct, right? 20 minus 7 is 13. So we can say our unknown number here is 20. All right, let's take a look at some multiplication phrases. So we have times. We all know that times means multiplication. So 19 times a number. Again, I can mark out a number and put x. 19 times x is just 19x. Or you can put 19 times x like this, whatever you want to do. Then the product of, we know the product is a result of multiplying 2 or more numbers together. So the product of 11 and a number. So again, we can mark out a number and put x. So the product of 11 and x is, again, just 11 times x. Then multiplied by 4 multiplied by a number. Mark out a number and put x. 4 multiplied by x is 4 times x. And then twice. We know that's like doubling something or multiplying by 2. So twice a number. So if we put twice x, that's just 2 times x. Tripled. A number is tripled. We know if we multiply by 3, we're tripling something. So we can mark out a number and put x. X is tripled. That's 3 times x. And then of, here we have 1/2 of a number. So again, mark out a number and put x. Generally, you're going to use of when you're working with fractions. You want a fractional amount of something. So I want 3/4 of something, 5/6 of something, or in this case, 1/2 of something. So 1/2 of x is 1/2 times x. Now again, with multiplication, it's commutative, right? The order that I multiply in does not affect my result. So let's look at some examples. So when a number is multiplied by 19, the result is negative 266. Find the number. So again, when a number, and here we have the number, I'm going to replace that with x. So let's put an x here, and let's put an x here. And again, for completeness, I'm just going to say let x be equal to my unknown, again, my unknown number. Okay, so when x is multiplied by 19, so that's just 19x, the result is, again, this guy right here is just going to be equals negative 266. So this tells me I have 19x that's equal to negative 266. I can solve this very easily. I can divide both sides by 19. And I'm going to get that x is equal to negative 14. So again, find the number. It's going to be negative 14 because when negative 14 is multiplied by 19, the result is negative 266. That's true. So negative 14 is my unknown number here. All right, now we're saying that 1/2 of a number is 28. Find the number. So again, a number and the number. I'm just going to replace that with a variable like x. So 1/2 of x would just be 1/2 x. And then we're saying is, okay, this is going to be equals. And then we have 28. So find the number. All I've got to do is solve this equation. But let me write this right here and say that we're going to, again, let x be equal to our unknown number. Again, this is just for the sake of completeness. And to multiply both sides by 2 here would give me a solution for my equation. Right? I can multiply this side by 2 and this side by 2. This guy here would cancel. I'd have x is equal to 28 times 2 is going to be 56. So that's my unknown number, right? 1/2 of 56 is 28. That's correct. All right, so we also have some division phrases. We want to remember that division is not commutative. So the order that we divide in is going to change the result, right? So something like divided by, and then we have a number divided by 3. So again, I'm just going to line out a number and put x. If that's divided by 3, we would have x over 3, right? X divided by 3. So essentially, x goes in the numerator, it's your dividend, and 3 goes in the denominator, it's your divisor, right? So x divided by 3 would be x over 3. It would be wrong if you put 3 over x, right? If I put 3 over x, that would be incorrect. So again, the order matters here. Then we have quotient of. So the quotient of a number and 7. I'm just going to line out this part that says a number and put x. So the quotient of x and 7 would be x over 7, okay? Then we have ratio of, the ratio of a number and 20. Again, just going to line out a number and put x. So the ratio of x and 20 would just be x over 20. All right, so let's look at a few problems with division. So we have the quotient of a number and 13 is 18. Find the number. So again, wherever I see a number or the number, I'm just going to replace this with our variable x. And again, for completeness, I'm just going to say down here we want to let x be equal to our unknown number. So the quotient of x and 13, that's just x over 13. Then we have is, right? In this context, it means equals. Then we have 18. So to find the number, let's just solve the equation. We'll multiply both sides by 13. And we'll get what? This cancels. We'll get x is equal to 234. Right? 18 times 13 is 234. So when we say find the number is going to be 234 because the quotient of 234 and 13 is 18. All right, now we have a number divided by 8 is 17. Find the number. So again, for a number or for the number, I'm just going to put my variable x. So x divided by 8. So x divided by 8. Is, again, this means equals. So we have equals, and then we have 17. Again, find the number or find x. So let me write down here that we're going to let x be equal to our unknown number. Again, just for completeness. And so to solve the equation here, I'm just going to multiply both sides by 8. 17 times 8 is 136. So these guys cancel. You get x equals 136. So that's going to be my unknown number. Again, if 136 is divided by 8, the result is 17. Okay, so 136 again is the number. For all the problems we looked at, we used is for equals, but there's other things you can see. So it's basically any phrase that implies sameness. Okay, so some examples would be, again, we use is. So 5 times a number is 7. So again, if you line this out and you put x here, 5 times x is, okay, that is means equals. So 5 times x is or equals 7. Then here, we just have the word equals. So 4 added to a number equals 17. So that's pretty straightforward. Line out your number and put x. 4 added to x, which is x plus 4, equals 17. Then we have is the same as. So a number less 5 is the same as twice the number. So let's line this part out here and put x. Let's line out this part here and put x. So x less 5, that's x minus 5, is the same as. Okay, that's basically us saying equals, right? It's implying sameness. So is the same as is equals. And then we have twice x, so 2 times x. All right, let's go ahead and take a look at 2 examples that kind of tie everything together. And in the next lesson, we'll start looking at some common application problems, again, that deal with linear equations in one variable. So when 2 is multiplied by a number, and then 8 times the sum of 11 multiplied by the number and 1 is subtracted away, the result is the same as -6 times the sum of 10 and 10 times the number. Find the number. So this is a lot more complex than the little simple ones we looked at earlier. We're just kind of putting things together. So let's go through. And again, I'm just going to let x be equal to my unknown number here. So I'm going to highlight everywhere I see a number and just put x there. So everywhere I see a number or the number. So let's read back through. When 2 is multiplied by x, and then 8 times the sum of 11 multiplied by x, and 1 is subtracted away, the result is the same as. So we know this part right here where we say is the same as, that's going to be equals. -6 times the sum of 10 and 10 times, again, for the number, I'm going to put x, and then find the number, I'm going to put x here. All right, so let's read back through this now. So we have when 2 is multiplied by our number x, so I'm going to put 2x. Then we have and then. So and then means afterwards. We have 8 times the sum of. So whenever you have the sum of in this type of problem, you're going to multiply 8 by a set of parentheses, okay, because you're going to have a sum. So I'm going to put 8 out here times a set of parentheses. I don't know what's going to go inside yet, but I'm just going to set that up. So 8 times the sum of, you've got 11 multiplied by our x. So we've got 11x, and then and 1. So and 1. And now it says is subtracted away. So this was subtracted away from our 2x. So let's just read through this part again and make sure we got it. So when 2 is multiplied by x, so we have our 2x, and then 8 times the sum of 11 multiplied by x and 1 is subtracted away. So 8 times the sum of, we have 11x and 1. So 8 times the sum of 11x and 1, that's what we have here. And again, that's subtracted away. So that's why we have minus 8 times the quantity, 11x plus 1. Then we have the result is the same as. So we know this is equals. Then we have -6 times the sum of. So again, I'm going to put -6 here. If I have times the sum of something, I'm going to use parentheses. So then we have 10 and 10 times x. So 10 plus 10x. And this is basically going to be our equation, right? So again, to go through this part again, we have -6 times the sum of. So -6 times the sum of 10 and 10 times x. So -6 times the quantity 10 plus 10x is what that translates to. Okay, let's go ahead and solve this equation. So I'm going to have my 2x here, and then I'm going to distribute the -8 to each term. So you would have minus 88x, and then minus 8. And this equals, I'm going to distribute the -6 to each term. So -60 plus -60x. On the left side, I can clean up because 2x minus 88x would be -86x. Then you have minus 8 is equal to -60 plus -60x, or you can just put -60x. Whatever you want to do, doesn't matter. Let me kind of get some room going here. So let's go ahead and add 60x to each side of the equation. Let's add 8 to each side of the equation. So we know that this is going to cancel here, and this is going to cancel here. -86x plus 60x is -26x. And this equals -60 plus 8 is going to be -52. Now, if I divide both sides of the equation by -26, I'm going to get that x is equal to +2. Okay, so 2 is my unknown number. So let's go back up. Let's write this as our unknown number, and let's check this. So when 2 is multiplied by 2, so 2 times 2 is 4, and then 8 times the sum of 11 multiplied by 2 and 1. So we're going to have 8 multiplied by the sum of 11 times 2, which is 22, and 1. So 22 plus 1 is 23. 23 times 8 is 184. So we'd have 184 here. Now it says that this is subtracted away. So 4 minus 184 is going to be negative 180. And it says the result is the same as. So we're going to put equals here. You've got -6 times the sum of, you've got your 10 and 10 times x. And again, x is 2. So you'd have negative 6 times the sum of, you would have 10 plus, 10 times 2 is 20. So 10 plus 20 is 30. So you'd have negative 6 times 30, which is negative 180. So the same value is on the left as we have on the right. So 2 is our correct solution here, right? That's going to be our unknown number. All right, let's take a look at one more of these. So we have when a number is divided by 4 and then added to 3, the result is the same as 7 less than the sum of the number and 1. Then find the number. So again, wherever I see a number, so where we see a number here, and then the number here, and then the number here, I'm just going to put x in each place. And then again, for completeness, I'm just going to say we're going to let x be equal to our unknown number. Okay? So reading back through now, when x is divided by 4, so that's x over 4, and then added to 3, so then just plus 3, the result is the same as, so that means equals, right? So I can just kind of highlight this where it says is the same as, and I can just put equals there. So this will be equals here. It says 7 less than the sum of x and 1. So we want the sum of x and 1, which is x plus 1. And then we want 7 less than that. So just subtract 7 away from that. And this will be our equation. Okay, so let's copy this. And we'll just come down here to a fresh page so we're not in the way of everything. And what I'm going to do is just kind of clean up first. So I'm going to add 1 and negative 7. 1 plus negative 7 or 1 minus 7 is going to be negative 6. So I would have x over 4 plus 3 equals x minus 6. And I can subtract 3 away from each side of the equation. Kind of make that a little better. And let me go ahead and cancel this. So we have x over 4 is equal to x minus, if we have negative 6 minus another 3, or negative 6 plus negative 3, you're going to get negative 9. So this is x minus 9. And then now I can clear this denominator here by multiplying both sides of the equation by 4. So these would cancel. I just have x on the left. On the right, you'd have 4 times the quantity x minus 9. So that's 4x minus 36. Okay, so to solve this guy for x, what I'm going to do is I'm going to subtract 4x away from each side of the equation. So that's going to cancel. X minus 4x is going to be negative 3x. And this equals negative 36. So now we can divide both sides of the equation by negative 3. And we're going to get that x is equal to 12. So let's go back up. So we're going to say that our unknown number is 12. So 12 here. Okay, so let's check. When 12 is divided by 4, that would give me 3, right? 12 divided by 4 is 3. And then added to 3, so 3 plus 3 would be 6. We say the result is the same as, or equal to, 7 less than the sum of, you'd have x as representing the number, so 12 and 1. So the sum of 12 and 1 is 13. And if I had 7 less than that, I would have 6. So again, same value on the left as you have on the right. So you can say that 12 is in fact the correct solution. That's your unknown number. In this lesson, we want to review applications of linear equations and talk about consecutive integer problems. All right, so once again, when we have an application problem that involves setting up and solving a linear equation in one variable, we have a little 6-step procedure we can use. So for solving a word problem, the first thing we want to do is read the problem and determine the question, or again, questions to be answered. Then we want to assign a variable to represent the unknown. And then in these type of problems, we can always express any other unknowns in terms of this original variable. Then we're going to write an equation. This will be based on the situation given. We're going to solve the equation. Then we're going to write the answer in terms of the question, or again, the questions being asked. Then lastly, we're going to check the answer using the words of the problem. We always want to make sure that our answer is reasonable. All right, so let's just jump in and look at a problem. These problems are very easy to understand and solve, so you really shouldn't have too much of an issue with them. So 2 pages that face each other in a book have a sum of 663. What are the page numbers? So to get an idea of what's going on here, if you think about a book and you think about 2 pages that face each other, you could say this page is 1 and this page is 2, right? They're going to differ by 1. Or you could say that this page is, let's say, 500 and this page is 501. Something like that. So we know that the smaller page could be represented with a variable like x. So let's let x be equal to the smaller page. Okay, let me make that better. Okay. So then what can we say about the larger page? Well, it's just one more, right? In the instance where we had 1 and 2, 1 was the smaller, 2 was the larger. It's just a difference of 1, okay? So what I can say is that we could say then x plus 1 is the larger, okay, the larger page. Okay, so what we're told is that the sum of the pages is 663. So it's very easy to solve this. I just take my smaller page, which is x, and I add it to my larger page, which is x plus 1, and this equals 663, okay? So all I got to do now is just solve my equation. Very, very easy. So if I just remove the parentheses here, because I don't really need them, x plus x is 2x, and then plus 1 equals 663. Let's go ahead and subtract 1 away from each side of the equation. We know this will cancel, and you'll have 2x is equal to 662. Let's now divide both sides of the equation by 2 so that we can isolate the variable x. So we know that this will cancel with this, and I'm going to end up with x is equal to 662 divided by 2 is 331, okay? So again, when you work with a word problem, you can't just say x equals 331 and turn in the test, right? You got to make sense of it. So let's erase all this. I'll show you on our little picture what's going on. All right, so if we come back up here, again, we said x was equal to 331. This is the smaller page. So in our book, we could say this page here is 331, and then the next page, the page that faces that one, is going to be 332, okay? And you could check that. Is the smaller page 331? Well, if the larger page is 332, if you sum those two amounts together, you do get 663, okay? So everything is consistent with what we're told in the problem. So let's go back up. Again, what are the page numbers? So to answer that question, we could say the page numbers are, again, 331 and 332. Okay, nice and simple. All right, let's take a look at another one. So the sum of 3 consecutive even integers is 30. Find the integers. So in this particular case, you've got to understand what it means by saying consecutive even integers. So with that, we're talking about, again, even numbers are numbers that are divisible by 2, right? So this is 0, 2, 4, 6, 8, 10, 12, things like that. So if I want consecutive even integers, it could be 2, 4, 6, 8, 10, something like that. It could be starting at 12, so 12, 14, 16, 18. Whatever number you start at, you're just increasing by 2 each time to get to the next even integer, okay? So if I want 3 consecutive even integers, I can let the smallest just be x. So let x be equal to the smallest even integer. Okay, let me make these e's a little better. So what can we say about the middle one? Right, we have a smallest, we have a middle one, and we have a largest. Well, again, I'm just increasing by 2. If I started at 2 and I went to 4, I'm increasing by 2. Right, then if I go to 6, I'm increasing by 2 again. So we can say then x plus 2 is our middle even integer. Okay, let me make that better. And then what? We could say then if I add another 2, so x plus 2 plus another 2 would be x plus 4. So x plus 4 would be the largest even integer. Okay, let me make these better. So we're told the sum is 30, right? It's right here. So all we really have to do is take x, which is the smallest even integer, add it to x plus 2, which is the middle even integer, and add that to x plus 4, which is the largest even integer, and set that to 30, solve that equation, and we'll be good to go. So we have x plus 2 plus x plus 4 You could wrap these in parentheses to kind of separate them if you want, but it really serves no purpose, so I'm not going to do that. And this is equal to 30. So let's solve this guy real quick, and we'll have our answer. So x plus x plus x is 3x. And then 2 plus 4 is 6. So plus 6, this equals 30. Let's go ahead and subtract 6 away from each side of the equation. And this is going to cancel. We're going to have 3x is equal to 30 minus 6 is 24. And then I want x by itself, so let's divide both sides of the equation by 3. And we'll get what? This cancels with this. You've got x is equal to 8. Okay, so let's erase everything. Again, the smallest even integer was represented with x, so we know that's 8. So then the next even integer would be what? We add 2 to that, so we get 10. And then add 2 to that to get to the largest, and that would be 12. Okay? So the integers would be 8, 10, and 12. Is that consistent with the problem? 8 plus 10 is 18, and then 18 plus 12 is 30. So we're basically good to go, right? And they're all even numbers, and they're in a consecutive sequence. So I can just say, find the integers. The integers are, we'll say 8, 10, and 12. All right, let's take a look at another one. And this one kind of trips students up, so you just want to pay close attention here. So the sum of 5 consecutive multiples of 7 is 245. Find the multiples. So the idea here, if you don't remember what a multiple is from pre-algebra, just note that there's multiple definitions of this. But essentially, if I take the number 7 and I multiply it by an integer, so by 1 or 2, or it could be -7 or whatever I want to multiply it by, as long as it's an integer, the result there is a multiple of 7. So generally in pre-algebra or a lower level algebra course, you kind of restrict this to multiplying the number, which in this case is 7, by whole numbers, which are 1 or larger, right? So I would say multiples of 7, you'd have 7 times 1 is 7, then 7 times 2 is 14, then 7 times 3 is 21, right? So on and so forth. So if I start with 7, then I increase by 7, I get to 14, increase by 7, I get to 21, so on and so forth. So I go 28, 35, 42, 49, right? This would continue forever. Now, in this particular case, all we need to understand is that each time I go to the next multiple in the sequence, I just add 7, right? So to get from 7 to 14, I add 7. To get from 14 to 21, I add 7. So if the sum of 5 consecutive multiples of 7 is 245, the first multiple could just be x. So let's say let x be, you say this is the smallest or the first multiple. You'd say of 7. So then each time I increase to the next multiple, I'm just going to add 7, right? Just to follow this pattern. So we could say then x plus 7 is what? It's the next number in the sequence. So we would say the next largest. Okay. And then following this pattern, you're just going to keep adding 7. So we could say then x plus 7 plus 7, or x plus 14, would be what? It would be your next largest. So you just keep going until you have 5 of these guys. So we would say then, let me make that e better. You'd have x plus 14 plus 7, which is x plus 21, is again the next largest. So you have 1, 2, 3, 4. You need one more. So then we could say x plus 28 is now going to be your largest. Let me write that out. So this would be your largest. And I'll be specific here and say multiple of 7. Okay, so now what do we want to do? We're told the sum of these guys is 245. So essentially what I got to do is just take x plus 7 plus x plus 14 plus x plus 21 plus x plus 28 and just set it equal to 245. Solve that for x and I'll have my answer. Okay, pretty easy overall. So again, I have x plus the next guy in the sequence is x plus 7 plus the next guy in the sequence is x plus 14 plus the next guy is x plus 21. And then lastly, the largest is x plus 28. You've got 1, 2, 3, 4, 5 multiples that you're representing. This is equal to 245. Okay, so on the left side, x plus x plus x plus x plus x is 5x. So it's 5x. And then plus, You've got 7 plus 14 plus 21 plus 28, which is 70. Okay, so then this equals 245. If I want to solve this for x, I'm going to subtract 70 away from both sides of the equation. So this guy's going to cancel. You'll have 5x is equal to 245 minus 70 is going to give me 175. And now what we can do is divide both sides of the equation by 5. So we can isolate x. And we'll get that x is equal to 175 divided by 5 is 35. Okay, so let's make sense of this. So x is 35. Let's go back up. So we said x was the smallest multiple of 7. So the next largest would be plus 7. So we would get 35. Add 7, you would get 42. Again, keep adding 7. So you get to 49. You would get to 56. And then finally, you would get to 63. So these are your multiples of 7. So let's erase this. All right, so let's say the multiples of 7 are, again, you have 35, 42, 49, 56, and 63. Now, if you sum these, you get 245, right? We know that they're multiples of 7. That's very easy to see. But if we sum these, do we get 245? Well, 35 plus 42 is 77. Then if I add 49, I get 126. Then if I add 56, I get 182. And then finally, if I add 63, I do get 245. So when I sum these numbers, I do get 245. So my solution here is correct. All right, let's take a look at one more problem. So if 6 is subtracted from the largest of 3 consecutive odd integers and then multiplied by 2, the result is 23 less than the sum of the smallest and twice the middle integer. What are the integers? So when you get a problem like this, you just have to stop and go step by step, okay? If you try to go too fast, you might miss a part. This is one of the ones that's just meant to kind of confuse you. So the first thing is, it says consecutive odd integers. Think about the fact that if you have consecutive even integers, it's 2, 4, 6, 8, 10, right? So on and so forth. Odd integers are integers that are not divisible by 2. So if they're consecutive, it's going to differ by 2. So something like 1, 3, 5, 7, 9. I'm just increasing by 2 once I start with an odd integer. So to kind of model this, let's let x be the smallest odd integer. And then we can say that x plus 2 is going to be the middle one. So this is the middle odd integer. I'm going to run out of room, so let's take this to another page. And so we can also say then x plus 2, which would be x plus 4, is the largest, okay, the largest odd integer. Okay, so now that we've modeled the odd integers, that sequence, let's go back up and let's think about what it's saying. If 6 is subtracted from the largest of 3 consecutive odd integers, okay, so 6 is subtracted away from the largest. So the largest we said was x plus 4. So 6 subtracted away, we'd have x plus 4 minus 6, which would translate into x minus 2. Okay, so let's just write that. So let's put this as x minus 2. And it says, again, if 6 is subtracted away from the largest of 3 consecutive odd integers, which we've already done, and then, okay, so it's done after the fact, multiplied by 2. So we're going to multiply this guy by 2. This is a quantity. X minus 2 is a quantity. So I've got to multiply the quantity x minus 2 by 2. Then it says the result is. So that always means equals. So again, the result is you have 23 less than the sum of the smallest and twice the middle integer. Okay, so this is a lot to unpack. So we know that we're subtracting 23 away from something because it says the result is 23 less than. So let's go back here. I'm just going to put minus 23 out here because we're going to do something and then we're going to subtract 23 away. Now, it says the sum of the smallest, which we said was x, and twice the middle integer. The smallest, which we said was x, and twice the middle integer. We want that sum. The middle integer is x plus 2. So again, I've got to use some parentheses here. So let me kind of drag this over. So 2 times this quantity x plus 2. Okay? So let's read through this again and make sure we understand where this came from. So again, if 6 is subtracted from the largest of 3 consecutive odd integers and then multiplied by 2. So essentially, we started with the x plus 4 is the largest odd integer. We subtracted away 6. That's how we got x minus 2. And then we multiplied by 2 to get the left side. Then it tells us the result is. So that's where we got our equal sign from. If you say the result is, you're basically saying is equal to. So on the right side, we have that it's 23 less than the sum of the smallest, which we represented with x, and twice the middle integer. Now the middle integer is x plus 2. So twice the middle integer is 2 times the quantity x plus 2. So that's where you got this from. The sum of the smallest integer, which is x, and twice the middle integer, which is 2 times x plus 2. So we sum those two together, and then we need to subtract 23 away from that because it says the result is 23 less than, okay? So now that we have this set up, again, these are kind of a pain to get to this point, but once you have it, it's pretty easy. You're just solving an equation. So clean up on the left, 2 times x is 2x, then minus 2 times 2 is 4. This equals, you have x plus 2 times x is 2x, and then plus 2 times 2 is 4, and then minus 23. Okay, so let's think about this. On the left side, nothing I can do. On the right side, I can take x and add to 2x. That would give me 3x. And then 4 minus 23 is negative 19. Again, over here, I'm just going to write 2x minus 4. Nothing's going to change. I'm going to subtract 3x away from each side of the equation, and I'm going to add 4 to each side of the equation. So what's going to happen is this guy right here is going to cancel, and this guy is going to cancel. 2x minus 3x is negative x, and this equals negative 19 plus 4 is going to be negative 15. Now, to get x by itself, I can multiply both sides by negative 1 or divide both sides by negative 1. Makes no difference. You're going to get that x is equal to 15. Okay, so let's erase all this. So remember, x was the smallest odd integer. So if we go back up, what are the integers? We'll say the integers are, let me make the e better. So we have 15. The next one would be 17, right, if it's consecutive odd integers. And then the last one would be 19. So let me put and 19 here. So and 19. Okay. Does this make mathematical sense? Normally with these problems, you just get a straight sum, so it's very easy to check. With this one, you have to do a little bit of work. So if 6 is subtracted from the largest of 3 consecutive odd integers, so the largest is 19. If I take 6 away, I'd have 13. Then it tells us, and then multiplied by 2. So 13 multiplied by 2 is 26. So this is 26. And it says the result is, so this is equal to, so we have 23 less than the sum of the smallest. So the smallest is what? It's 15 plus twice the middle integer. The middle integer is 17. So if I take 2 and multiply it by 17, I get 34. And again, it's 23 less than this. So I'm going to subtract 23 away from this sum. So 15 plus 34 is 49. So you would have 49 minus 23, which is 26. Right? You end up with the same value on the left as you do on the right. So we've successfully completed checking this guy. Right? We can say our answer is correct. The integers are going to be 15, 17, and 19. In this lesson, we want to review applications of linear equations and look at some examples of age problems. So again, whenever we're working with an application problem that involves a linear equation in one variable, we can use our little 6-step procedure. So for solving a word problem, we have that we want to read the problem and again determine the question or questions to be answered. Then we want to assign a variable to represent the unknown. With these problems, we're going to express other unknowns in terms of this variable. Then we're going to write an equation. This is based on the situation given to us in our problem. And then we're going to solve the equation. Then we're going to write the answer in terms of the question or again, questions asked. And then lastly, we're going to check the answer using the words of the problem. We always want to make sure the answer is reasonable. So for age word problems, this is another extremely common type of word problem in algebra. This type of problem is generally going to give us the sum of the ages of family members, friends, or some group of associated people, and it's going to ask us to find their individual ages. Now, it doesn't always set up this way, but that's the most common scenario. All right, so let's take a look at the first example. So we have that Albert, Jamie, and Jessica are siblings and have a combined age of 50 years. So Jessica is 3 times as old as Albert, but half as old as Jamie. How old is each sibling? So this is our main question here, right? How old is each sibling? So we need to find out how old is Jamie, how old is Albert, and how old is Jessica, okay? So we are only given the fact that they have a combined age of 50 years, and we've given some comparisons here. It tells us Jessica is 3 times as old as Albert, but half as old as Jamie. So to solve this, we know what we're trying to find. Let's assign a variable. Let's let x be equal to, since Jessica is involved in both comparisons, let's let x be equal to Jessica's age. Now, what can we say about Albert's age and what can we say about Jamie's age? Well, we're told here specifically that Jessica is 3 times as old as Albert. So if Jessica is 3 times as old as Albert, that means Albert is 1/3 the age of Jessica. So then x, which is Jessica's age, over 3 would be equal to Albert's age. Now, we're also told that she's half as old as Jamie. So if Jessica is half the age of Jamie, that means Jamie is 2 times as old as Jessica. So I can say then 2 times x, again, x is Jessica's age, so 2 times that would be Jamie's age. Okay, so this is Jamie's age. Now, we have everything set up here. We have everything modeled. How do we get an equation going so we can get a solution? Well, essentially, we have a combined age of 50 years, so I can take Jessica's age, which is x, add that to Albert's age, which is x over 3, and add that to Jamie's age, which is 2x, and I can set that equal to 50, right, their combined age. So let's go ahead and set that up. So we would have x plus x over 3 plus 2x is equal to 50. What I can do to clear this denominator is multiply everything by 3. So I would have 3x plus, if I multiply x over 3 by 3, I would just have x, and then plus 2x times 3 is 6x, and this equals 50 times 3 is 150. Okay, so basically I just multiplied both sides of the equation by 3, again, so I can clear this denominator here. So now 3x plus x is 4x, plus 6x is 10x, so you get 10x is equal to 150. Let's divide both sides of the equation by 10, and we get that x is equal to 15. So if x was Jessica's age, that tells me that Jessica is 15 years old. So let's go back up. So again, x is 15, so Jessica is 15. And then we know that Albert is 1/3 of the age of Jessica, right? It's 15 over 3, which is 5. And then Jamie is twice the age of Jessica, so it's 2 times 15 or 30. So to answer this question, we can say that Jessica is 15, comma, we'll say Albert is 5, and we'll say Jamie is 30. Okay? Now you can check this to make sure it makes sense. So again, Albert, Jamie, and Jessica are siblings and have a combined age of 50 years. So is 15 plus 5 plus 30 50? Yes. 15 plus 5 is 20, 20 plus 30 is 50, so you're good to go on that part. Then it says Jessica is 3 times as old as Albert. So Jessica is 15, Albert is 5. 15 is 5 times 3, so we're good to go there. And then half as old as Jamie. 30 is Jamie's age. Again, Jessica is 15. 15 is half of 30, so you're good to go there. So this checks out. Jessica, again, is 15, Albert is 5, and Jamie is 30. All right, let's take a look at one that's a little bit more challenging. So we have that 9 years ago, Steve was 1/3 of Larry's current age. The difference between Larry's age and Steve's age is the same as Max's age 11 years ago. If their combined age is 131 years, how old is Steve, Larry, and Max? So we want to find out how old is Steve, Larry, and again, Max. So I'm going to jump right in and let a variable like x represent the current age of Larry. Okay, so let me go down here. So we have lots of room. So let's let x be equal to Larry's current age. Now, what can we say about Steve? Well, it says specifically that Steve was 1/3 of Larry's current age 9 years ago, okay? So I have to think about the fact that 1/3 of Larry's current age is 1/3 x, but this is Steve's age 9 years ago. So I've got to add 9 on top of that to get back to our present day in time. So for Steve's age, we could say then 1/3 x, so 1/3 of Larry's current age, then plus 9, right? Because this part right here is Steve's age 9 years ago. So I've got to add 9 to that to get his current age. So this would be Steve's current age. Now let's think about Max now. So it tells us that the difference between Larry's age and Steve's age is the same as Max's age 11 years ago. Okay, so the difference between Larry's current age, which is x, and Steve's current age, which again is this 1/3 x plus 9. Notice that I'm using brackets here because I've got to subtract the whole thing away. This is the same as Max's age 11 years ago. So to get his current age, I've got to add 11 to this amount, okay? So this would be then, we'll say this guy right here, let me just kind of slide this down. We'll say this is Max's current age. Okay, and I might run out of room, so let me make that a little bit better. So Max's current age. Okay, so now it also tells us in the problem that their combined age is 131 years. So essentially, just like I did in the last problem, I can sum the ages and set it to 131, and I'll get a solution. So I would have x, which is Larry's age, plus 1/3 x plus 9, which is Steve's current age. And then plus, you have x minus, you have this inside of brackets, 1/3 x plus 9, and then plus 11, which again is Max's current age. This is all equal to 131. So let me copy this. We're going to go down to a fresh sheet of paper. So let me just kind of clean this up. We have x plus 1/3 x plus 9 plus x. Use your distributive property here. So you'll have minus 1/3 x, then minus 9, then plus 11, and this equals 131. Now what do you notice here? 1/3 x minus 1/3 x, that's gone. 9 minus 9, that's gone. X plus x is 2x. And then plus 11 equals 131. If I subtract 11 away from each side of the equation, I'm going to get that 2x is equal to 120. Divide both sides of the equation by 2. We're going to get that x is equal to 60. So remember, x was Larry's current age. So Larry is 60. So Larry is 60. We can say that Steve, again, he's 1/3 times 60, which is 20, plus 9, which is 29. And then for Max, we basically have 60 minus 29, which is 31, and then plus 11, which is 42. So his is going to be 42. All right, let's go back up. So let's write our answer here. Again, Larry is 60. So Larry is 60. Then we can say Steve is 29. And Max is 42. Again, we can check this. So it says 9 years ago, Steve was 1/3 of Larry's current age. So if we go 9 years ago, Larry's current age is 60. So 1/3 of that is 20. Okay, so Steve is 29. 9 years ago, he would have been 20, and that is 1/3 of Larry's current age, which again is 60. Then it says the difference between Larry's age and Steve's age, the difference between 60 and 29 is 31. And it says this is the same as Max's age 11 years ago. Well, again, Max is 42. 11 years ago, he would have been 31. So that checks out as well. Then it says their combined age is 131. Well, 60 plus 29 is 89. Then if I add 42, I do get 131. So everything checks out here. We can say that Larry is 60, Steve is 29, and again, Max is 42. All right, let's take a look at one more. So we have 3 friends, John, Clyde, and Beth all attend the local school. The school accepts students from age 5 to age 20. This week, the school set up a fair in which the minimum age is 12 years old to attend. So now we're told in 1 year, Clyde will be 3 times as old as John is today. And then 1 year ago, Beth was 1/2 as old as Clyde is today. If the difference of Clyde's age and John's age is the same as Beth's age in 2 years, find which of the friends can attend the fair. Okay? So we're trying to find which of the friends, so we have Beth, Clyde, and John, can attend the fair. Remember, it tells us that you can only attend the fair if you're at least 12 years old, right? You need to be 12 years old to attend. So we're trying to find out which of these individuals are at least 12, right? Because if you're 12, you can go to the fair. If you're older than 12, you can go to the fair. And if you're less than 12, you can't go to the fair. So let's think about a variable to represent one of their ages. And then we can go through and model the rest of the ages based on that variable. So it tells us that, again, in 1 year, Clyde will be 3 times as old as John is today. And it tells us 1 year ago, Beth was 1/2 as old as Clyde is today. So since Clyde is involved in both comparisons there, let's just go ahead and let X be Clyde's current age. And let's do this on a fresh sheet. So let's let X be equal to Clyde's current age. Okay, so what can we say about John's age? Well, it says in 1 year, Clyde will be 3 times as old as John is today. So that means if I take Clyde's current age, which is X, and I add 1 to it, right, because it's in 1 year, that amount, X plus 1, would be 3 times the age of John, right? So X plus 1 is 3 times the age of John. So I can just divide by 3 to get John's current age. So we can say then X plus 1 over 3 is John's current age. Okay, so what can I say about Beth's current age? So if we think about this, 1 year ago, Beth was 1/2 as old as Clyde is today. So half of Clyde's age today is 1/2 times, again, Clyde's age is represented with X, so it's 1/2 X. Now, this is Beth's age not today, but a year ago, okay? A year ago, she was 1/2 as old as Clyde. So if I think about 1/2 X, that's Beth's age 1 year ago. If I add 1 to that, that's Beth's current age. So we would say that then X over 2, which again is her age a year ago, then plus 1 would be her current age. So this would be Beth's current age. So in most of these problems, you're given a sum, right, of all the ages. But in this case, you're not. You have to use something else to get your equation, and it's this sentence right here. So if the difference of Clyde's age and John's age is the same as Beth's age in 2 years. So the difference of Clyde's age and John's age would be Clyde's age minus John's age. So let's set that up first. So Clyde's age is X. So this is X, and then minus John's age is X plus 1 over 3. Now I'm subtracting this whole thing away, so let me just put it in brackets so we don't make a sign mistake. And then we're saying is the same as, so that's equals. Here we're told Beth's age in 2 years. So her current age is X over 2 plus 1. So X over 2 plus 1. In 2 more years, you would just add another 2 to this amount. So let's copy this. We're just going to take it to a fresh sheet of paper, and we can solve this guy. So we have X, and then you have your minus here. You can distribute this. You can go ahead and set this up as X over 3 plus 1 over 3. And then if I had a minus out in front of that, then I would have what? I would have X minus X over 3, and then minus 1/3, okay? Then this would be equal to, let me just kind of drag this back up. You have your X over 2. 1 plus 2 is 3, so plus 3. Now, if I want, I can multiply both sides of the equation by 6, right? That would be the LCD. So if I did that, I would have 6x minus, if I have 6 times x over 3, the 6 would cancel with the 3 and give me a 2, so this would be 2x. Then minus, if I have 6 times 1/3, that's 2. This equals, if I have x over 2 times 6, again, 6 divided by 2 would be 3. 3 times x is 3x. And then plus 6 times 3 is 18. Okay, so now here on the left, I have 6x minus 2x, which is 4x. And then minus 2 equals 3x plus 18. Let me scroll down and get some room going. So now I can subtract 3x away from each side of the equation. So this is going to cancel. I can add 2 to both sides of the equation. This is going to cancel. 4x minus 3x is x, and this is equal to 18 plus 2, which is 20. So x is equal to 20. Now x was Clyde's current age, so he's 20. John's current age was what? It's 20 plus 1, which is 21, divided by 3, which is 7. Beth's current age is 20 divided by 2, which is 10, plus 1, which is 11. So it doesn't ask for their ages. It wants us to find out who can attend the fair. So we know that Clyde is the only one that can attend the fair because the minimum age is 12, right? Beth can't go because she's 11, and John can't go because he is 7. So only Clyde can attend. So that's the only information we need to know. It's, again, find which of the friends can attend the fair. And once more, you can only attend if you're 12 or older, right? So let's go back down and say that only Clyde can attend the fair. Okay. Now, if we think about this, we can go back and check. So in 1 year, Clyde will be 3 times as old as John is today. We said that Clyde was 20. We said John was 7. So in 1 year, Clyde will be what? He'll be 21. And that is 3 times as old as John is today because John is 7. So that checks out. Then it says 1 year ago, Beth was 1/2 as old as Clyde is today. So a year ago, Beth would have been 10 years old. And that is half as old as Clyde is today because he is 20. Okay, so that checks out. Then it says if the difference of Clyde's age and John's age. So the difference between 20 and 7, Clyde's age and John's age, is 13. That is the same as Beth's age in 2 years. She's currently 11. In 2 years, she's going to be 13. So that all checks itself out. So our answer here is correct. Only Clyde can attend the fair because, again, he's the only one that's at least 12 years old. In this lesson, we want to review applications of linear equations. We're going to look at mixture word problems. So again, when we're working with applications of linear equations, we have a little 6-step procedure that we can use. So for solving a word problem, we have as our first step, we want to read the problem and determine the question, or again, questions to be answered. Then we want to assign a variable to represent the unknown. We're going to express other unknowns in terms of this variable. Then we're going to write an equation, okay, based on the scenario we're given. Then we're going to solve the equation. Then we want to write the answer in terms of the question, or again, questions being asked. Then lastly, we're going to check the answer using the words of the problem. This one right here, number 6, the last step is very important. You want to make sure your answer is reasonable. So of all the word problem types that we encounter in elementary algebra courses, usually mixture problems give students the most trouble, right? When you're in that section on applications of linear equations. The key to understanding mixture problems is understanding how to find the pure amount of a substance in a mixture. To accomplish this task, we can multiply the rate of concentration as a decimal by the amount of the solution, okay? This will give us the pure amount of a substance in a mixture. So let's look at a simple example. So a local bar serves Pebble beer, which is 9% alcohol. So I'm just going to highlight this because they gave us a percentage. So 9% alcohol. If one serving is 20 ounces, let me just highlight that. So it's 20 ounces. How much pure alcohol is in each serving? So obviously this is what we want to answer here. How much pure alcohol is in each serving? So all I need to do is take the amount of one serving, which is 20 ounces. Forget about the ounces part for a minute, just the number 20. And it's 9% alcohol, okay? So all I need to do is multiply the 20 by 9% as a decimal, which is 0.09. If I do that calculation, I'm going to get 1.8, okay? So what this tells me is that this Pebble beer here is going to be 1.8 ounces of pure alcohol. So let me erase this and I'll write a nice little sentence. And we'll say that Pebble beer has 1.8 ounces of pure alcohol per serving. Okay, so a very simple example, just something we need to understand how to find the pure amount of something in a mixture or substance. So in this case, we have a beer. It's 9% alcohol. We want to know the pure amount of alcohol in the full serving, which is 20 ounces. Again, we take the rate of concentration, which is 0.09 as a decimal. We multiply it by that serving, which is 20 ounces, and that tells us we have 1.8 ounces of pure alcohol in each serving. All right, let's look at a typical word problem now. So we have that Mary is throwing a party and wants to serve fruit punch, which is 22% pure fruit juice. She currently has 2 gallons of cherry smash fruit punch, which is 50% pure fruit juice. How many gallons of bubbleberry fruit juice, which is 14% pure fruit juice, must be added to create her desired fruit punch? So understand what we're trying to find here. We're trying to find out how many gallons of this bubbleberry fruit juice, which again is 14% pure fruit juice, that's got to be added to create her desired fruit punch. And again, her desired fruit punch is 22% pure fruit juice. Okay, that's what we want. So let's get a little idea of what's going on. She has these 2 fruit punches that she's mixing together. One is the cherry smash, and the other is the bubbleberry. Okay, so you can see that little image here. So she's mixing them together to get this final mixture here. And the final mixture is going to be 22% pure fruit juice. Okay, so that's the goal. So let's let a variable like x be equal to the amount of the bubbleberry fruit punch in gallons. Okay, so that's the amount she's going to use in gallons. So we'll say the amount, let me kind of erase that. So we'll say the amount of the bubbleberry fruit punch used, and this is going to be in gallons. Okay, in gallons. All right, so once we know that X is representing the amount of bubbleberry fruit punch used in gallons, what else do we need? Well, we already know the amount of cherry smash. It tells us that in the problem. It tells us that she has 2 gallons of cherry smash. Okay, so let's go down to a little table and organize this information. So for our table, up here we're going to put the gallons. So this is going to be the gallons. This is going to be our concentration percentage as a decimal. And this amount right here is going to be our pure fruit juice. Okay. Then for our products over here, we're going to have the cherry smash and we're going to have the bubble berry. Okay. So those 2 products. Now it tells us in the problem the number of gallons of the cherry smash is going to be 2. And then we said the number of gallons of bubble berry that we're going to use is going to be represented with our variable x. What is the percentage of pure fruit juice in cherry smash? So let's go back up. So cherry smash, it tells us, is 50% pure fruit juice. 50% pure fruit juice. Whereas bubble berry is 14% pure fruit juice. Okay, so let's fill this part in. So cherry smash, again, is 50% fruit juice. So as a decimal, that's 0.5, okay? Bubble berry is 14% pure fruit juice. So as a decimal, that's 0.14. Now, as we just saw in our simple example a minute ago, all we need to do to get the amount of pure fruit juice here is multiply across. So for cherry smash, if I have 2 gallons of my fruit punch and it's 50% pure fruit juice, the amount of pure fruit juice in gallons there is going to be 2 times 0.5 or 1. Okay. Then for the bubble berry, I just got to multiply across again. So I have X gallons, it's 0.14 or 14% pure fruit juice. So the amount of pure fruit juice there is 0.14 times X. Okay. And again, this is in gallons. Now, we have this final row here that represents our mixture, our desired mixture. So we'll say this is our final mixture, okay? So the number of gallons will be what? Well, we only have gallons coming from 2 sources, right? We have the cherry smash and the bubble berry. So I can just add these. I would have X gallons coming from the bubble berry, then plus 2 gallons coming from the cherry smash. Now, the percentage is given to us in the problem. It tells us that the final mixture, again, is 22% pure fruit juice. So this has to be 0.22. And so the pure fruit juice in gallons would be what? It would be 0.22 times this quantity of X plus 2. All right, so let's stop here. From this point, it's very easy to set up an equation. We know that the amount of pure fruit juice in gallons in the final mixture comes from two sources. It comes from this source right here. You've got 1 gallon coming from your cherry smash, and then you've got 0.14x gallons coming from your bubble berry. That has to be equal to the pure fruit juice in gallons in the final mixture. This 0.22 times the quantity x plus 2. So that's where we're going to get our equation. We're just going to set this up. So we will have 1, again, the amount of pure fruit juice in gallons from cherry smash, plus you're going to have your 0.14x, which again is the amount of gallons of pure fruit juice in the bubble berry. And we're going to set this equal to the amount of pure fruit juice in the final mixture, which is 0.22 times the quantity x plus 2. Okay, so once we've set up an equation, it's very easy. So you have your 1 plus 0.14x is equal to, use our distributive property, we'll have 0.22x, and then plus 2 times 0.22 is 0.44. And then to solve this guy, I'm just going to go ahead and subtract 0.14x away from each side of the equation. And I'm going to subtract 0.44 away from each side of the equation. And what's that going to give me? So we know that this would cancel. We know that this would cancel. So 1 minus 0.44 is 0.56. So the left side is 0.56. And this is equal to 0.22 minus 0.14 is 0.08. And then times x. If we finish this up by dividing both sides by 0.08, we're going to get 7. Okay? So x here is going to be equal to 7. Now, let's make sense of this. We said that x was the amount of bubble berry fruit punch used in gallons. So we know that x is equal to 7. So she needs to use 7 gallons of bubble berry fruit punch. Okay? So let's go back up and let's answer our question now. So we'll just say that she needs to use 7 gallons of bubble berry fruit punch. Now, let's check this. Let's make sure the answer is reasonable. She's throwing a party and wants to serve fruit punch, which again is 22% pure fruit juice. She currently has 2 gallons of cherry smash fruit punch, which is 50% pure fruit juice. And again, it asks how many gallons of bubble berry fruit juice, which is 14% pure fruit juice, must be added to create her desired fruit punch. Well, we know if she's using 7 gallons of bubble berry fruit punch, and it's 14% pure fruit juice, then essentially she's getting 0.98 gallons of pure fruit juice from the bubble berry. So this comes from the bubble berry. Now, we're told, again, in the problem directly, that she's using 2 gallons of the cherry smash, and it's 50% pure fruit juice. So 2 gallons times 0.5 is again 1. So add that to 1. This is from the cherry smash. So this amount should be equal, this 1 plus 0.98, which is 1.98, should be equal to the amount of pure fruit juice in the final mixture. So in the final mixture, she's going to have 7 gallons of bubble berry plus 2 gallons of cherry smash. So that's 9 gallons. And again, it's 22% pure fruit juice. And 9 times 0.22 is 1.98. So we're good to go, right? This is your final mixture. You basically have said that the amount of pure fruit juice coming from the bubble berry and the cherry smash is equal to the amount of pure fruit juice in the final mixture, and it is 22% pure fruit juice, so we're good to go. She needs to use 7 gallons of bubble berry fruit punch to make her desired fruit punch mixture. All right, let's take a look at another one. So Double Yield Farmers Market sells 24-ounce bags of mixed nuts that contain 43% peanuts. To make this product, they combine Rowlet mixed nuts, which contain 30% peanuts, and True Nut mixed nuts, which contain 50% peanuts. How much of each should be used to make their product? So again, another straightforward kind of question. How much of each? So we're saying how much of the Rowlett mixed nuts and how much of the True Nut mixed nuts should be used to make their product, which again is a 24-ounce bag of mixed nuts that contains 43% peanuts. Okay, so in this case, we don't know an amount for either, right? So we have to kind of get that. We're working with ounces. So the total amount in the final mixture that they sell is 24 ounces. So let's use that information to create a variable. So let's let x be equal to the amount in ounces of, we'll just go ahead and say Rowlett mixed nuts used, okay? Now, because the total mixture in the end is 24 ounces, we know that if we subtract away x, again, the amount in ounces of Rowlett mixed nuts used, what's going to happen is 24 minus x can represent the amount of the True Nut mixed nuts that's going to be used, right? So if we put then, we'll say 24, again, the total amount of ounces of the final mixture, minus x, which is the amount in ounces of Rowlett mixed nuts used. So this is going to be equal to the amount in ounces of the True Nut mixed nuts used, okay? So once we've kind of modeled this, we can go down to the little table and set things up, just like we did in the last example. So on the left, let me put the names. So you have your Rowlett, mixed nuts, you have your True Nut, and we're going to have a final product. So we'll have a final, you could say final mixture or final product. Okay, let me make that a little better. So again, final mixture. So up here we'll have our ounces of mixed nuts. And then we're going to have our concentration percentage of peanuts. So this is the percentage as the decimal. And then we're going to have pure peanuts in ounces. So this is pure peanuts. And again, this is in ounces because we're working with ounces. All right, for the ounces of mixed nuts, we know for Rowlett, we represented this with x. And for True Nut, we represented this with 24 minus x. For the final mixture, we know it's 24, okay? That's given to us in the problem. Now the percentages, let's go back up. We're told that the final mixture is 43%. So this would be 43% or 0.43 as a decimal. Then we're told that Rowlett mixed nuts has 30% peanuts and True Nut has 50% peanuts. So let's go back down. So Rowlett is 30%, so 0.3 as a decimal. True Nut is 50%, so 0.5 as a decimal. And again, to get the amount of pure peanuts, we just multiply across. If it's 30% peanuts and it's X number of ounces, the ounces of pure peanuts would be 0.3 times X. Again, if it's 50% peanuts and there's 24 minus X ounces, the pure peanuts would be 0.5 times the quantity 24 minus X. And then for the final mixture, if it's 43% peanuts and there's 24 ounces of mixed nuts, well, I can multiply 0.43 times 24 to give me 10.32. This is the amount in ounces of pure peanuts in the final mixture. Now again, we can set up an equation in the same way that we did in the last problem. We basically think about the fact that the amount of pure peanuts coming from the Rowlett mixed nuts plus the amount of pure peanuts coming from the True Nut mixed nuts has to be equal to the amount of pure peanuts in the final mixture. So all I've got to do is take this 0.3x and add it to my 0.5 times the quantity 24 minus x, and then set this equal to my 10.32. So let's solve this and we'll be good to go. So we have our 0.3x plus 0.5 times 24 is 12. Then minus, you have 0.5 times x, which is 0.5x. This equals 10.32. 0.3x minus 0.5x is going to give us a negative 0.2x. Then you have your plus 12 equals 10.32. Let's go ahead and subtract 12 away from each side of the equation. And this is going to cancel. You have your negative 0.2x is equal to, if I do 10.32 minus 12, I get negative 1.68. So negative 1.68. As a final step, let's divide both sides by negative 0.2. And then this cancels with this. We'll have that, let me kind of make a border here. We'll have that x is equal to negative 1.68 divided by negative 0.2 is going to be 8.4. Okay, so 8.4. So let's go back up. So this is going to be 8.4. And then 24 minus 8.4, or 15.6, is going to be the amount in ounces of true nut mixed nuts used. So let's go back up. We'll make a nice little sentence here. We'll say that they should use 8.4 ounces of rowlet make that better. Again, mixed nuts. And you have 15.6 ounces of true nut mixed nuts. So true nut mixed nuts. Okay. So again, they should use 8.4 ounces of rowlet mixed nuts and 15.6 ounces of true nut mixed nuts. All right, so to check this, the first thing you want to do is make sure that the number of ounces coming from rowlet mixed nuts and the number of ounces coming from the true nut mixed nuts match up. So you've got 8.4 ounces coming from rowlet mixed nuts and 15.6 ounces coming from the true nut mixed nuts. That does give you 24 ounces, okay? 15.6 plus 8.4 would give you 24. So you're good to go there. If, again, we have a 24-ounce bag that's 43% peanuts, we know there's 10.32 ounces of pure peanuts in that product. Now, this comes from what? It comes from the rowlet mixed nuts, which is 30% peanuts. So 8.4 times 0.3 is going to give us 2.52. And then it also comes from 15.6 ounces of true nut mixed nuts, which is 50% peanuts. So 15.6 times 0.5 is 7.8. So if you take the 7.8, the amount of pure peanuts coming from true nut mixed nuts, and you add that to the 2.52, again, the number of ounces of pure peanuts from the rowlet mixed nuts, you do get your 10.32, or again, the number of ounces of pure peanuts in your final product for the double yield farmers market. So we can say our answer here is correct. Again, they should use 8.4 ounces of rowlet mixed nuts and 15.6 ounces of true nut mixed nuts. All right, let's take a look at one more of these. So Jacob wants to make 17.5 gallons of a 44% acid solution. To do this, he will mix a 60% acid solution and a 25% acid solution. How much of each solution must he use? Again, very simple problem. The key to understanding this here, again, is to think about the final mixture. It's 17.5 gallons of a 44% acid solution. So basically we have 17.5 gallons, 44% of it is pure acid. Now, this can only come from what? Two sources here. We've got a certain number of gallons, which is unknown at this point, of a 60% acid solution, and then a certain number of gallons, again, unknown at this point, of a 25% acid solution. Now, if we let a variable like x be equal to the amount in gallons of the 60% acid solution that we're going to use, then what can we say about the amount of the 25% acid solution we're going to use? Again, the total amount in gallons is 17.5. So we could say then 17.5. Again, the total amount in gallons of the final solution minus x. Again, the amount in gallons of the 60% acid solution we're going to use. This is going to be equal to the amount in gallons of the 25% acid solution and let me just drag this to another page so it's nice and clean. So let's go down to a little table real quick and let's kind of set this up. So we know that we want to have gallons of the acid solution. So this is gallons right here. We know we want a percentage concentration basically of acid. And then we're going to have the amount of pure acid. Okay, and of course, this is going to be in gallons. Now we have our 60% acid solution. We have our 25% acid solution. And then we have our final mixture. Okay, so the number of gallons for the final mixture is given to us as 17.5 in the problem. We assigned our variable x to represent the amount of gallons for the 60% acid solution. Let me make that clear because that looks like 66. And then we said that 17.5, again, the amount in gallons of the final mixture, minus x, the amount of gallons for the 60% acid solution that we're using, is going to be the amount of the 25% acid solution that we're going to use, okay? So we have the number of gallons modeled for each. The percentage is very easy because it's off to the left, right? So this one right here is going to be 0.6 as a decimal, right? That's 60%. And this one right here would be 0.25 as a decimal. That's 25%. So the final mixture, we are told, is 44%. Again, Jacob wants to make 17.5 gallons of a 44% acid solution. So as a decimal, 44% is 0.44. So to get the amount of pure acid in gallons for each, I would just multiply across. So I have x gallons and it's 60% pure acid. So 0.6 times x is 0.6x. I have 17.5 minus x gallons. It's 25% pure acid. So 0.25 times the quantity, 17.5 minus x. And then my final mixture is 44% acid, and it's 17.5 gallons. If we multiply those together, you get 7.7. So this is the amount of pure acid in the final mixture. It's 7.7 gallons. Now, for our equation, again, we use a similar format. We think about the amount of pure acid coming from the 60% acid solution, which is 0.6x, plus the amount of pure acid coming from the 25% acid solution, which is 0.25, times the quantity 17.5 minus x. And this has to be equal to the amount of pure acid in the final mixture, right? So 7.7. Okay, so let's solve this equation and we'll be good to go. So we have that 0.6x plus 0.25 times 17.5 is 4.375. And then minus 0.25 times x is 0.25x. And this equals 7.7. Okay, so let's clean up on the left. 0.6x minus 0.25x is 0.35x. So 0.35x. And then if I subtract 4.375 away from each side, what will I get? Well, we know this would cancel. So we'll say this is equal to 7.7 minus 4.375 is 3.325. All right. So to finish this up, let's divide both sides of the equation by 0.35. So we'll get x is equal to 9.5. Okay, so let's go back up. So again, we said that x was the amount in gallons of the 60% acid solution. So this is going to be 9.5. And then 17.5 minus 9.5 is going to give me 8. So there's 8 gallons of the 25% acid that's used. So let's go back up. And to answer this, we'll say he should use 9.5 gallons of the 60% acid solution, along with 8 gallons of the 25% acid solution. Again, very easy to check. First, you would say, is 9.5 plus 8, the gallons coming from each source, if you add those together, is that 17.5, right? The number of gallons in the final mixture that he has. Well, yes, it is, right? 9.5 plus 8 is 17.5. So that part checks out. All right, now next, remember, he has 7.7 gallons of pure acid in the final solution. That came from multiplying 17.5, the number of gallons in the final mixture, times 0.44, again, 44% as a decimal. That gives us 7.7 gallons of pure acid in the final mixture. So that comes from two sources. From one source, he has 9.5 gallons, that's 60% acid. So that would be 5.7 gallons of pure acid. Then lastly, he has 8 gallons, that's 25% acid. So 8 times 0.25 is 2. So if you add 2 to 5.7, you do get 7.7, right? So you've checked the amount of pure acid in the final mixture, that matches up, and you've checked the number of gallons of the final mixture, that matches up. So we can say our solution here is correct. He should use 9.5 gallons of the 60% acid solution, along with 8 gallons of the 25% acid solution. In this lesson, we want to review applications of linear equations, and specifically we're going to look at motion word problems. All right, so let's just go through our procedure real quick on how to solve a word problem. This is just a general guideline, something you can use as you're solving your problems. So the first thing is just to read the problem and determine the question, or in some cases questions, to be answered. The next thing is to assign a variable to represent the unknown, express other unknowns in terms of this variable. Then we want to write an equation. Then we're going to solve the equation. Then we're going to write the answer in terms of the question or the questions being asked. And then lastly, we're going to check the answer using the words of the problem. All right. So for motion word problems, a lot of you who took lower level algebra courses got a lot of experience with these. It's a very common type of word problem. They rely on the understanding of the formula d, or distance, is equal to r for rate of speed times t, the time traveled. This is a very intuitive formula. Think about being on a road trip, and let's say your rate of speed is 80 miles per hour. So let's say this is 80 miles per hour, and I'll just write 80. And then you do this for, let's say, 10 hours. How far did you go in terms of miles? Well, you just multiply. The rate of speed is 80. The amount of time is 10. 80 times 10 is 800. So your distance is 800 miles, okay? So it's a very intuitive formula, something you can kind of work out in your head if you just kind of can't remember the distance formula. Think about being on a road trip and saying, okay, if I'm going at this rate of speed for this amount of time, well, I can multiply those two numbers together to get my distance. All right, let's look at our first example. So we have that Heather left school and drove toward the ocean. Daniel left 1 hour later and drove at a speed that was 15 miles per hour faster than Heather. After 2 hours, Daniel caught up with Heather. What was Heather's average speed? So this is what we need to answer here. What was Heather's average speed? That's the key. Take the second to look at the problem and understand the question that you're being asked. That's where a lot of students really, they read the problem, they don't really understand what they're being asked, so they're like, what do I do? Okay, that's what you've got to understand. What was Heather's average speed? So now we're ready to kind of go through the problem. And the first thing that I'm going to do is just let a variable. You can let it be x, or it could be y, or z, whatever you want to use. Doesn't matter. So let x be equal to, what am I looking for? I'm looking for Heather's average speed. So let's let x be equal to Heather's average speed. Okay, and this is going to be in terms of miles per hour, because that's what we're working with in the problem. Now we need to model other unknowns in terms of this variable x. So we have Heather's average speed modeled, but we don't have Daniel's average speed modeled. Well, Daniel, it tells us in the problem that he's driving 15 miles per hour faster than Heather. Okay, well, if Heather's average speed is x, then we can say that x plus 15, okay, that amount there, is going to be Daniel's average speed. Okay, so this is Daniel's average speed. Okay, let me make those a little bit better. All right, so with this information, we can take this to a table, okay? And I'm going to show you this table real quick. This is something you can use to kind of organize your thoughts, okay? So in this case, I'm going to put the names on the left. So I can just kind of put it as the names if I want, and that's going to go down like this. So let's put H for Heather, and let's put D for Daniel. To the right here in the top, I'm going to put D for the distance. And this is equal to my R, which is the rate of speed, multiplied by my T, which is the amount of time traveled. So we already know for Heather, her rate is X, and for Daniel, his rate is X plus 15. Okay, what about the time? Let's go back up and see if we can figure that out. So it tells us in the problem specifically that Daniel left 1 hour later, okay, so he drives for an hour less than Heather does when they catch up, okay, or when they're at the same point. So it says after 2 hours, Daniel caught up, and it also says he left 1 hour later, okay? So that means that Daniel was driving for 2 hours, because it says specifically, after 2 hours, Daniel caught up. And it tells us also that, again, because Daniel left 1 hour later than Heather, that Heather was driving for an hour more, so she was driving for 3 hours. So I can fill this out and say Heather was driving for 3 hours, Daniel was driving for 2. Now, I can get the distance by multiplying these two together, okay? So in other words, the distance that Heather travels is the amount of time she travels for times the rate of speed that she travels at. So 3 times x is 3x. That's my distance for Heather. 2 times the quantity x plus 15 is my distance for Daniel. Now, let's go back up and see how we can figure out an equation. If we think about this, remember, they leave from the same point. Heather left school and drove toward the ocean. Daniel left 1 hour later, okay, so he's leaving from the same point. Now, they catch up, meaning they go to the same point when they're caught up, okay? So they leave from the same point, they go to the same point, so that means that Heather and Daniel drive the same distance. They do it in a different amount of time, but they drive the same distance. So what I can say here is that the distance for Heather, which is 3x, is going to be equal or the same as the distance for Daniel, which is 2 times the quantity x plus 15. So once we've set this up, it's basically a breeze from here. We would use our distributive property on the right. This is 2x plus 30. On the left, we still just have 3x. Let me go ahead and subtract 2x away from each side of the equation. This is going to cancel. I'll have that x is equal to 30. Okay, so this is another big problem. A lot of students get x equals 30 and they stop, right? We're used to just saying, hey, this is my answer, x equals 30. With word problems, you've got to go back up and make sense of your answer. So x equals 30 tells me that Heather's average speed was 30 miles per hour, okay? And that also tells me that Daniel's average speed was 45 miles per hour because his is expressed as x, which is 30 plus 15. 30 plus 15 is 45. So let's erase this and say, what was Heather's average speed? We can say Heather's average speed was 30 miles per hour, okay? And you can check this pretty easily. You can say, are the distances equal? Well, if Heather drives at 30 miles per hour for 3 hours, she's going to go 90 miles, right? Again, distance equals rate of speed, which is 30, times time traveled, which is 3. 30 times 3 is 90. So when you think about the units, it's going to be 90 miles. For Daniel, he drives for only 2 hours, but he does it at 45 miles per hour. 2 times 45 is also 90, so you can say this is the correct answer. Heather's average speed was 30 miles per hour, and again, although it doesn't ask for it in the problem, we can say Daniel's average speed was 45 miles per hour. All right, let's look at another one. So we have that Aya left the mall and traveled toward her beach home at an average speed of 50 miles per hour. Jeff left the mall at the same time and traveled in the opposite direction with an average speed of 60 miles per hour. How many hours before they are 330 miles apart? So this is what we need to answer. How many hours before they are 330 miles apart? So let's label our kind of table down here. So we have our names going down. Let me make that a little bit better. So we have Aya and we have Jeff, okay? And then for this part right here, we have our distance is equal to rate times time. Okay, so what are we given in the problem? We're told that Aya's average speed is 50 miles per hour and Jeff's average speed is 60 miles per hour. So for Aya, the rate of speed is 50. For Jeff, it's 60. Do we know the time in each case? No, we're not given that. Okay, and in fact, what we need to find is how many hours before they are 330 miles apart. Meaning they start at one point and one drives in one direction, another drives in the opposite direction. And we want to know how long before kind of the distance between them is 330 miles, okay? So let me make that better. So what we want to do is let a variable like x be equal to the amount of hours that they're each traveling for before they are 330 miles apart. So time in hours, we could say to get to 330 miles apart. Okay, let me make that a little bit better. So each of them are going to drive for that amount of time. So we can go down here and we could say that this is x and this is x. Now, the distance that Aya travels is 50 times x or 50x. The distance that Jeff travels is 60 times x or 60x. In the last problem, we set the distances equal to each other. But that's not going to work here because what we're saying is that the sum of the distances, the amount that Aya travels plus the amount that Jeff travels, is going to be 330 miles, right? 50x plus 60x needs to be 330 miles, okay? So if we solve this, 50x plus 60x is 110x, and this equals 330. We divide both sides of the equation by 110, and we're going to get that x is equal to 3. All right, so let's erase this, and let's say, since x was 3, and x represents the amount of hours for them to get to 330 miles apart, we'll just say it takes 3 hours for them, meaning Aya and Jeff, for them to be 330 miles apart. Okay? And that would be your answer there. And you can think about why that makes sense. If Aya drives at a speed of 50 miles per hour for 3 hours, she's basically going, let's say from this point to here, she's going 150 miles. Okay? If Jeff goes the opposite direction, he starts here and goes this way, well, he's going to go a little bit further because he's going faster. 60 miles an hour times 3 hours would be 180 miles. Okay? So the distance between them now, from here where Jeff is to here where Aya is 180 plus 150, which is going to be 330. All right, let's look at one more. So Jason can drive to Farmwood in 2 hours. If he takes the bus, it takes twice as long. If the average speed of the bus is 25 miles per hour slower than Jason's car, how far away is Farmwood? Okay, so what are we asking? We're asking for how far away is Farmwood, meaning what is the distance from wherever Jason starts to Farmwood? Okay, well, we know that there's 2 situations. There's one where he takes a car, and there's another where he takes a bus. So let's go down here. So to start filling in the table, we'd have one scenario, which is a car, and another, which is a bus. So this just represents the vehicle. So I just put V for that. Again, we're still going to have our D for distance is equal to R for rate of speed times T for time traveled. So let's go back up. We're told that Jason can drive to Farmwood in 2 hours. So by car, the trip takes 2 hours. So the time by car, we're going to put 2 there. And then if he takes the bus, it takes twice as long. So 2 times 2 would be 4. So if he takes the bus, it's 4 hours. Now, in terms of the rate of speed, we're not given that. We're only told that the speed of the bus is 25 miles per hour slower than Jason's car. Okay, so let's let a variable like x be equal to the car's average speed. And again, this is in miles per hour. Now we can model the speed of the bus based on this, right? If x is the car's average speed, since the bus is going 25 miles per hour slower than the car, we can say x minus 25 can represent the bus's average speed. So we'll say the average speed of the bus, okay? All right, so x is the car's average speed, x minus 25 is the average speed of the bus. So rate of speed for the car is x, rate of speed for the bus is x minus 25. Now we know for distance we multiply. So 2 times x is 2x, and over here we'd have 4 times the quantity, x minus 25, okay? Now, we know that the distance is equal, right? Jason can drive to Farmwood in 2 hours. If he takes the bus, it takes twice as long. So the distance is going to be the same. So to solve this one, I can just set this distance that he travels by car of 2x equal to the distance of the bus, which is 4 times the quantity x minus 25. All right, so let's scroll down, get some room going. So we have 2x on the left is equal to 4 times x is 4x, and then minus 4 times 25 is 100. Let's go ahead and subtract 4x away from each side of the equation. That cancels. 2x minus 4x is negative 2x. This equals negative 100. Let's go ahead and divide both sides by negative 2. And we're going to get that x is equal to 50. Okay? So what does that mean? X equals 50. We don't stop there. We've got to go back up. So x is the car's average speed. So that means the car was traveling at 50 miles per hour. Okay? The average speed of the bus is 50 minus 25, or 25 miles per hour. But that still doesn't answer the question. It didn't ask what was the speed of Jason's car. It asked how far away is Farmwood. Well, all we have to do now is say, since Jason can drive to Farmwood in 2 hours, and he's driving at 50 miles per hour, 50 times 2 is 100. So that means Farmwood is 100 miles away. So Farmwood is 100 miles away. Let me erase all this. Okay. You can check that pretty easily. Again, if he can drive to Farmwood in 2 hours and he's going at 50 miles per hour, that's 100 miles. If the bus is 25 miles per hour slower than the car, 50 minus 25 is 25. It takes him twice as long. It takes him 4 hours. 25 times 4 is also 100. So either way, he's going 100 miles. So that's consistent with our problem, right? Farmwood is 100 miles away. In this lesson, we want to review applications of linear equations and look at bill and coin problems. All right, so again, if we're solving application problems that involve a linear equation in one variable, we can use our little 6-step procedure. So again, for solving a word problem, we want to read the problem and determine the question or questions to be answered. Then we want to assign a variable to represent the unknown. We want to express other unknowns in terms of this variable. Then we want to write an equation, again, based on the situation given in our problem. Then we're going to solve the equation. Then we're going to write the answer in terms of the question or, again, questions asked. And lastly, we're going to check the answer using the words of the problem. We just want to make sure our answer is reasonable. So another very common problem type that occurs when we're solving applications of linear equations involves denominations of money. Okay, so these might be referred to as dollar word problems. You might hear them called coin word problems, just based on the situation given. Okay, and essentially all you're doing here, you're normally given a value for all of the coins or all of the bills, and you need to find the individual amounts. So how many of, this type of coin do you have, or how much of this type of bill do you have, so on and so forth. So let's jump in and look at the first example. So we have Heather, a store clerk, has a total of $910 in her cash register. This amount comes from only 3 types of bills: $20 bills, $5 bills, and $1 bills. Now it says the clerk has double the amount of $20 bills as she has $5 bills, and half the number of $1 bills as she has $5 bills. Find the amount of each type of bill in her register. So this is a very, very straightforward problem. We just need to find, as it says here, the amount of each type of bill in her register. So how many $5 bills, how many $1 bills, and how many $20 bills. And again, this is based on the fact that there's a total value of $910 in the register. Okay, so let's let a variable be equal to one of our unknowns. Since the $5 bill is involved in both comparisons, let's let x be equal to that, right? Because it says the clerk has double the amount of $20 bills as she has $5 bills, and half the number of $1 bills as she has $5 bills. So let's let x be equal to the amount, or you could say the number of $5 bills in her register. All right, so what can we say about the number of $20 bills and the number of $1 bills? So if we go back up, it says here specifically The clerk has double the amount of $20 bills as she has $5 bills. So if I take the number of $5 bills, which we modeled as x, and I double that, or if I multiply it by 2, that would give me 2x, and that would be the number of $20 bills that she's going to have. Let's put then, we'll put our 2x is equal to the number of $20 bills. Okay, so we go back up. For the number of $1 bills, it says half the number of $1 bills as she has $5 bills. So if I take half of x, or just 1/2 x, that's going to represent the number of $1 bills. So we'll say then, again, we're going to do 1/2 times x, or you can put x over 2, whatever you want to do, is equal to the number of $1, let me make that better, again, $1 bills. Okay, so how do we get an equation going? We've modeled all of our kind of unknowns, but we need an equation to get a solution. So let's go back up. Now it says a store clerk has a total of $910 in her cash register. Where the problem comes in, a lot of students at this point, they're used to kind of summing what they have and setting it equal to that value. So you see a lot of people do this. They'll go, okay, x plus 2x plus 1/2 x is equal to 910. This is not the correct equation. Why is that the case? Well, what I have on the left here is going to be the total amount of bills that she has, right? Between the $5 bills, the $20 bills, and the $1 bills. What I have on the right is a value, okay? So it's not the same. These two would not be equal. So suppose you had 6 $20 bills in your wallet or purse. How would you find the value there? You wouldn't say you just have 6 bills. You would say that you have 6 times 20, or $120, okay? It's, in other words, going to be found by multiplying the quantity of bills, which is 6, by the value of each bill, which is 20, which gives us 120, right? That's how we got the value. So we're going to basically do the same thing. To get our 910 total value, we need to take the number of $5 bills and multiply it by 5, plus the number of $20 bills, multiply it by 20, plus the number of $1 bills and multiply it by 1. So let's do this with a nice little table. Let's go down here. And essentially what I'm going to have here is the quantity of bills. And what I'm going to have here is the value per bill. And what I'm going to have here is the total value. Okay, pretty straightforward. So we have our $20 bills. Let's just label this as 20. And we have our $5 bills. We'll label that as 5. And we have our $1 bills. We'll just label that as 1. So the quantity of bills, again, if I go back up, I know that the $5 bills are labeled with X, the $20 bills are labeled with 2X, and the $1 bills are labeled with 1/2 X. So the quantity of bills, for the $5 bills, it's X. For the $20 bills, it's 2X. And for the $1 bills, it's 1/2 X. Or again, you can do X over 2. Now the value per bill, that's pretty easy. Just look all the way to the left. This one's going to be 20. This one's going to be 5. And this one's going to be 1. Okay, that's pretty straightforward. Then to get the total value, I just multiply across, right? This times this will be equal to this, okay? So 2x times 20 would be 40x. X times 5 would be 5x. And then 1/2 x times 1 would be 1/2 x. So now I have something that I can set up an equation with. I have the total value of the 20s, which is 40x, plus the total value of the 5s, which is 5x, plus the total value of the 1s, which is 1/2 x. And this is equal to, again, the 910, that amount of dollars, which is the total value in her cash register, okay? So you've got to go through and make this setup here. Otherwise, you're not going to get the right answer by just going through and saying, okay, I have 2x plus 1/2 x and setting that to 910, because you're not setting a value equal to a value, okay? That doesn't work. So let's go ahead and solve this guy. I'm just going to copy this and go to a fresh sheet. All right, so what I can do, 40x plus 5x is 45x. Then plus 1/2 x equals 910. If I want to clear that denominator, let's multiply both sides of the equation by 2. So the 45x, if I multiply that by 2, I get 90x. Then plus 1/2 x times 2 would be just x. And this equals 910 times 2 would be 1820. And now 90x plus x would just be 91x. So let's write this as 91x. To get x by itself, I divide both sides of the equation by 91. And I'm going to find that x is equal to 20. Okay? So again, we're not done. We have to go back and make sense of this. So x equals 20. So x was the number of $5 bills, so that's going to be 20. Then 2x is the number of $20 bills. 2 times 20 is 40. Then 1/2 x is going to be the number of $1 bills. So 1/2 times 20 is 10. Okay, so let's go back up and write our answer. So what we're going to say is that there are 20 $5 bills. And then you have 40 $20 bills. And you're going to have 10 $1 bills in her, let me make that better, register. All right, so let's check this and make sure it makes logical sense. So it tells us that, again, she has a total value of $910 in her cash register. So $25 bills is $100. Let me just line this up and put this as 100. 40 $20 bills is $800. And 10 $1 bills is $10. So sum those amounts. 100 plus 800 plus 10 is 910. So this part's a check. Okay, that works out. It says this amount comes from 3 types of bills: $20 bills, $5 bills, and $1 bills. Good to go there. The clerk has double the amount of $20 bills as she has $5 bills. Again, she has 25s and she has 40 20s, so we're good there. And then it says she has half the number of $1 bills as she has $5 bills. You've got, again, 25s and you've got 10 ones, so good to go there. So everything checks itself out. We can say our answer here is correct. We'll go ahead and just state this again. There are 20 $5 bills, 40 $20 bills, and 10 $1 bills in her register. All right, let's take a look at another one. Again, these are pretty easy overall. So James, a local vendor, has a total of $5,600 in his carry bag. This amount comes from $20 and $100 bills only. If he has a total of 80 bills in his bag, how much of each type of bill does he have? So in other words, what we're trying to find here, it says how much of each bill does he have? We want to know how much of the $20 bills does he have and how much of the $100 bills does he have, because again, he only has those 2 types of bills in the bag. And again, another thing to highlight here is that he has a total of $5,600 and there's only 80 bills in the bag. Okay, so let's let a variable represent one of the unknowns. It could be the $20 bills or it could be the $100 bills. The key to understanding this problem is knowing that if he has a total of 80 bills in the bag, whatever I let x represent, then 80 minus x is going to represent the other one. So in other words, if I let x be equal to the number of $20 bills, then because, again, there's only 80 bills in the bag, it has to be true that we could say 80, the total number of bills, minus x, the number of $20 bills, has to be equal to the number of $100 bills. Okay? Let me make this a little bit better. Okay, so now that we have both of our unknowns kind of modeled, let's think about how we can get an equation going. So again, just like with the last problem, we're given a value, okay? But we've modeled things as kind of an amount of bills that we have. So we have to, again, go through, set up a little table, and relate the values. So let's go down here. And again, I'm going to say I have quantity of bills. I'm going to say value per bill. And I'm going to say total value. Again, if I take the quantity of bills times the value per bill, I will get the total value. So here I'm going to have my $20 bills, and here I'm going to have my $100 bills. So we said that the quantity of bills for 20s, we represented that with X. And the quantity of bills for hundreds, we represented that with 80 minus X. Now the value per bill for a 20 we know is 20. We know the value per bill for 100 is 100. And we just multiply across. So to get the total value for the $20 bills, it would be X times 20 or 20X. To get the total value for the $100 bills, it would be 100 times 80 minus X. So 100 times the quantity, remember you're multiplying by the whole thing, 80 minus X. Okay, so now we have the total value of the 20s and the total value of the hundreds, and we can sum those amounts and set it equal to the total amount that he has, which is $5,600. So in other words, I would have 20X plus 100 times the quantity 80 minus X. And again, this is set equal to the total value of his carry bag, which is $5,600. So let's copy this and go to a fresh sheet. So on the left, I have my 20X, and then plus, you've got 100 times 80, which is going to be 8,000. Then minus 100 times X is 100X, and this equals 5,600. So 20X minus 100X is negative 80X. And then again, you have plus 8,000. This equals 5,600. And now I'm going to subtract 8,000 away from each side of the equation. So I'm going to have negative 80X is equal to, if I have 5,600 minus 8,000, that's going to be negative 2,400. To get X by itself, I'm going to divide both sides of the equation by negative 80. So we know these cancel. You're going to get that X is equal to 30. Okay, so let's take this result here, back up. Again, we said X was the number of $20 bills, so this is going to be 30. We said 80 minus X, or 80 minus 30, or 50, is the number of $100 bills. Okay, so we have our solution. Let's go back up. And now let's answer this guy. So we can say there are, again, 30 $20 bills and 50 $100 bills. To check this is very easy. You'd want to make sure the value works out. So 30 times 20 is 600. So the value from the 20s is 600. And then 50 times 100 is 5,000. Okay? So the value from the $100 bills is 5,000. 5,000 plus 600 is 5,600. So you're good to go there. Now the next thing you want to check is, does the amount of bills from the 20s plus the amount of bills from the hundreds give me 80 bills, which is what's in his bag. So there's 30 20s and 50 hundreds. 30 plus 50 is 80, so you're good to go there as well. So again, our answer is that there are 30 $20 bills and 50 $100 bills. All right, let's take a look at one more problem. And this is one that's going to be a little bit tedious. So we have Becky, a math teacher at a local elementary school, has a jar of mixed change in her classroom. The jar only contains pennies, nickels, dimes, and quarters, and has a total value of $89.50. She tells her class that the first person to correctly state the quantity of each type of coin present in the jar can take the jar home. Now, she states that there are 4 times as many quarters as pennies and 6 times as many dimes as pennies. Additionally, if the number of pennies was increased by 10, there would be 3 times more nickels than pennies. Find the quantity of each type of coin in the jar. So this one is tedious because you have 4 coins involved. You have pennies, nickels, dimes, and quarters. So that's the unknown here. Again, we're trying to find the quantity of each type of coin in the jar. So how many pennies, how many nickels, how many dimes, how many quarters. So let's start out by just modeling our unknowns. So let's let X be equal to the number of pennies. And we're going to do that because it's involved in all the comparisons. So it's just easier if you do that. So what can we say about the number of nickels, the number of quarters, and the number of dimes? So it tells us to start that there are 4 times as many quarters as pennies and 6 times as many dimes as pennies. So if there's 4 times as many quarters as pennies, that means we could say then 4x, or 4 times the number of pennies, which is x, is equal to the number of quarters. then we can also say, again, since it told us that there are 6 times as many dimes as pennies, well, if there's X number of pennies, 6 times that amount would be 6X, so that's going to be my number of dimes. So 6X is equal to the number of dimes. Okay, so what can we say about the nickels? So what can we say about the nickels? So then it tells us if the number of pennies was increased by 10. So I have X number of pennies. If I increased it by 10, that would be X plus 10. There would be 3 times more nickels than pennies. So in other words, if I increase the number of pennies by 10, again, if I take X, the number of pennies, I add 10 to it, if I multiply that amount by 3, that's how many nickels I would have. So again, if I multiplied 3 times the quantity X plus 10, this would be equal to the number of nickels. Okay, so now that we have everything modeled, again, we're told the total value of all the coins in our jar. At the start of the problem, that's going to be $89.50. So again, we got to think about the value of each coin. We're going to sum the values of all the coins, and that should be equal to $89.50. So let's use a little table. All right, so let's set this up in the normal way. So we have our quantity of coins. And then we have our value per coin. And then we have our total value. Okay, let me make that better. And again, if I multiply the quantity of coins by the value per coin, I'm going to get the total value for that set of coins. So again, I have pennies, which I'm just going to put a P for, or you could put 0.01. I have nickels, which I'm going to put an N, and I'll just put 0.05. I have dimes, which I'll put a D for, and then 0.1, or 0.10 if you want that. And then I have quarters, which I'll put a Q for, and this is 0.25. So quantity of coins. If we go back up, again, X is the number of pennies, 4X is the number of quarters, 6X is the number of dimes, and 3 times the quantity X plus 10 is the number of nickels. So for pennies, this was X. For nickels, this was 3 times the quantity X plus 10. For dimes, this was 6X. And for quarters, this was 4X. Now the value per coin is pretty simple. For pennies, it's 0.01. For nickels, it's 0.05. For dimes, it's 0.1, or you can put 0.10, whatever you want to do. And then for quarters, it's 0.25. So again, the total value I just multiply across. So for pennies, it's X times 0.01, or 0.01X. For nickels, it's 0.05 times 3, which is 0.15, then times the quantity X plus 10. Now you can simplify this here, or you can wait till later. Let's just simplify it here. 0.15 times X is 0.15X, and then 0.15 times 10 is 1.5. So let's put 0.15X plus 1.5. And then for dimes, it's 6X times 0.1. So that's 0.6X. And then for quarters, it's 4X times 0.25, which is 1X, or just X. Okay, so if we sum these total values for each, then what we're going to get is a value that is equal to $89.50. So in other words, if I take 0.01X, the value of all pennies, and if I add it to 0.15X plus 1.5, the value of all nickels, and I add it to 0.6X, the value of all dimes, and I add it to 1X, the value of all quarters. I'm just going to write X. This is equal to, again, the total value of the jar, which is $89.50. Okay, so let's copy this and go to a fresh sheet. So 0.01 plus 0.15 is 0.16. If I add 0.6 to that, I get 0.76. And then if I add another 1, again, this has an implied coefficient of 1, then I get 1.76. So the left side would be 1.76x. And then don't forget about this guy. So plus 1.5, this equals 89.50, or just 89.5 if you want. Now, if I subtract this 1.5 away from each side of the equation, this will cancel here. You have 1.76x is equal to 89.5 minus 1.5 is 88. Now to get x by itself, I'm going to divide both sides by 1.76. So we know that this is going to cancel, and you'll have that x is equal to 88 divided by 1.76 is 50. So this is our answer here, but again, we've got to go back and make sense of it. All right, so we know that x represents the number of pennies, and again, we found that x was 50, so there are 50 pennies. Then 4 times x is the number of quarters. Again, x is 50. 4 times 50 is 200, so there's going to be 200 quarters. Then 6x is the number of dimes. Again, x is 50. 6 times 50 is 300. So there's 300 dimes. And then lastly, 3 times the quantity x plus 10 is the number of nickels. So x again is 50. 50 plus 10 is 60. 60 times 3 is 180. So there's 180 nickels. So let's go ahead and write our answer. So find the quantity of each type of coin in the jar. We can say that there are 50 pennies, 180 nickels, 300 dimes, and then lastly, we'll say and there's 200 quarters. 200 quarters. We could say in her jar. Okay. So there are 50 pennies, 180 nickels, 300 dimes, and 200 quarters in her jar. So let's check this. So it tells us there are 4 times as many quarters as pennies. You've got 50 pennies and 200 quarters, so that checks out. So I'll just put a check there. Then we're told there's 6 times as many dimes as pennies. You've got 300 dimes and 50 pennies, so that checks out, right? 300 is 6 times 50. And then additionally, if the number of pennies was increased by 10, so if we went from 50 to 60, there would be 3 times more nickels than pennies. Well, yeah, if I had 60 pennies, I have 180 nickels. 60 times 3 is 180, so we're good to go there as well. Now, the last thing to check is the value. If I have 50 pennies, that's 0.5 or 50 cents. If I have 180 nickels, that's 180 times 0.05. It's basically $9. If I have 300 dimes, it's basically 300 times 0.1. That's going to be $30. And then if she has 200 quarters, that's 200 times 0.25, which is going to be 50. Okay? So 50 plus 30 is 80. 80 plus 9 is 89. Plus 50 cents is going to be $89.50. So we're good to go on our value, right? If we add everything up, we do get $89.50, which again is what it told us in the problem. So we could say our answer here is correct. There are 50 pennies, 180 nickels, 300 dimes, and 200 quarters in her jar. In this lesson, we want to review applications of linear equations and look at some simple interest problems. So again, when we're solving applications of linear equation problems, we can use this little 6-step procedure to help us out. So for solving a word problem, we have that we want to read the problem and determine the question, or again, questions to be answered. We want to assign a variable to represent the unknown. And then with these type of problems, you're going to be able to express other unknowns in terms of this variable. Then we're going to write an equation. We're going to solve the equation. We're going to write the answer in terms of the question or questions asked. And then we're going to check the answer using the words of the problem. So this part right here, the last part, just make sure your answer is reasonable. All right, so for today's problems, we're going to be using the simple interest formula. So the simple interest formula goes like this. We have I, which is the amount of simple interest earned, is equal to P, which is the principal or amount invested, times R, which is the rate as a decimal, times T, which is the time, which is generally given to us in years. But it could be months, it could be weeks, it could be whatever they give to you, okay? But generally, it's going to be years. Now, one thing we need to understand before we move on is kind of the difference between simple interest and compound interest. We will look at examples that deal with compound interest later on in the course. We need to kind of build some concepts before we deal with that. For right now, we'll be dealing with just simple interest. So with simple interest, I only earn interest on the principal or the original amount invested. With compound interest, I earn interest on interest. So let's look at a very simple example. Let's say that my original amount that I invest is $1,000. Okay, so this is my account balance with each of these. Okay, so one is a savings account with simple interest, one's a savings account with compound interest. And let's say each of them pays me 10%. Okay, so it's 10% in each case, so no difference. At the end of year one, let's just assume they hold the money for a year, and at the end of the year, they give us our interest payment. So at the end of year 1, then this guy right here, 10% of 1,000 is 100, so my balance is $1,100. Same thing when it's compounding. I didn't get any interest dropped in there yet, so it's still $1,100. Now, at the end of year 2, what's going to happen is I'm going to have a difference, right? Because this guy, I just get paid on the original amount that I invested, which is 1,000. So I get my 10% again, which is just $100. So this guy's going to go to $1,200, okay? So that's where it is with simple interest. With compound interest, they're now going to say, okay, you get 10% of the balance. So the balance is $1,100. So I'm going to get 10% of that, which is $110. So I'm going to get $1,210 as a balance, okay? So the difference here is that I have $1,200 from simple interest, or $1,210 with compound interest. Because my interest that was earned, which was $100 at that point, earned interest of 10%, okay? $100, 10% of that is $10. So that's where you're going to get the difference in the account balance, okay? So simple interest, you only earn interest on the original amount invested. Compound interest, you earn interest on the full balance, or you could say you earn interest on your interest. All right, so let's look at a simple example here just to kind of get our feet wet, and then we'll look at 2 kind of typical problems that you'd see. So Nathan invests $10,000 in a savings account, which pays 3% annual simple interest. What is the total amount of simple interest earned at the end of a 2-year period? So again, for this guy right here, you can almost do this mentally. You can say what? This is I, simple interest earned, equals P, which is the principal, times R, the rate is a decimal, times T, the time, in this case, in years. Mentally, I can say, okay, $10,000 times 3% as a decimal is 0.03. So if you do that, 10,000 times 0.03 is 300. And so it's basically $300 a year for 2 years. 300 times 2 is 600. So he would earn $600 for the 2-year period. But to plug it into the formula, to kind of make it official, you would substitute in a 10,000 for P, because that's your principal or amount invested. You would substitute in a 0.03 for your rate. Okay, it's always as a decimal. And you would substitute in a 2 for the time period. In this case, that stands for 2 years. Okay, so again, make sure that the rate is in terms of years if you're dealing with years. Okay, so we have 10,000 times 0.03, which is 300, times 2, which is 600. So you can say that your I, or your simple interest earned, is 600. And again, we can answer this. Let me just erase everything. We have our answer now. We'll make a nice little sentence and say that Nathan earned $600 at the end of 2 years. Okay, and lots of different sentences that you can construct to answer this. You're just looking for something that addresses what they asked. Okay, so it says, what is the total amount of simple interest earned at the end of a 2-year period? And we just said Nathan earned $600 at the end of 2 years. Perfectly acceptable. Okay, let's look at a typical problem now, one where we have to set up kind of our full array of steps. So Jason has $70,000 to invest and wants to earn an overall rate of 9% annual simple interest. So he has $70,000 to invest, and he wants to earn an overall rate of 9% annual simple interest, okay? Let's go down and look at the next part. So he wants to invest part of the money in a savings account, which pays 8% annual simple interest. The rest of the money will be placed in a corporate bond fund, which pays 12% annual simple interest. Then here's the question. To meet his investment goal, which again was up here, he has $70,000 to invest and wants to earn an overall rate of 9% annual simple interest. That's the investment goal. So to meet his investment goal, how much should be invested at each rate? So to earn 9% on $70,000, how much should he put in the savings account and how much should he put in the corporate bond fund? All right. So we've read the problem. We understand what we need to do. Let's let a variable like x be equal to the amount he invests in one of these guys. Doesn't matter which one you choose. You can say x is the amount he invests in the savings account, or you can say x is the amount he invests in the corporate bond fund. It makes no difference. So I'm going to come down here and say we're going to let x be equal to the amount invested in the bond fund. Let me put in the bond fund. Okay. So then what can we say about the amount invested in the savings account? Well, we're told that Jason has a total of $70,000 to invest, and he only puts it in either the savings account or the bond fund. So if X is representing the amount that's put in the bond fund, then 70,000 minus X has to be the amount that he put in the savings account. So 70,000, which is the total amount, minus X, which is the amount invested in the bond fund, is going to be equal to the amount invested in the savings account. Okay, nice and simple. Let me make that better. Okay, so now that we have kind of our variable set up and the other unknown is expressed in terms of that variable, we're going to move into our next step, which is to basically set up an equation. To do that, I'm going to make a little table. A lot of times I think it's a little bit helpful if you're unfamiliar with solving word problems to set up a table. Some people don't do it. They feel like it's a waste of time, but it can be helpful. So let's just go ahead and do it. So we're going to write our simple interest formula up here on the top. So I, the simple interest earned, is equal to P, the principal or amount invested, times R, the rate as a decimal, times T, the time. Then for this guy right here, this is going to be the investments. So I'll just put I and V for investments. So you have the savings account and you have the corporate bond fund. So I'll just kind of initial those. So we know that for the amount invested or the principal, the bond fund we said was X. So let's put an X here. For the savings account, we said it was 70,000 minus X. Now, the rate is given to us in the problem. It says the savings account pays 8% annual simple interest, and it says the corporate bond fund pays 12% annual simple interest. So the savings account, again, is 8% or 0.08 as a decimal. The bond fund is 12% or 0.12 as a decimal. Now, what about the time? Well, basically, we're dealing with a scenario where the time is just going to be 1. So if we go back up, you can see that it basically says in the first part of the problem, Jason has $70,000 to invest and wants to earn an overall rate of 9% annual, which is yearly, simple interest. So what are we doing for 1 year, right? 1 year period. So we can go back down and just put a 1 for each time period. You can basically get rid of it because multiplying by 1 just leaves something unchanged, right? But we'll just leave it there for kind of completeness. So we know that I, the simple interest earned, is the product of the principal times the rate times the time. So at the bottom, it's pretty easy. I would just have 0.12x. For this guy right here, it's kind of hard to fit this, but we're going to have 0.08 times the quantity, 70,000 minus x. So let me kind of scooch this part up so it's out of the way. So I'm going to put 70,000 minus x. It's just going to bleed into the next column. I can extend the column, but it's going to kind of make everything go crazy. So let's just leave it like that. And we can now kind of think about how we can use this information. So I have the simple interest earned from the savings account, which is 0.08 times the quantity 70,000 minus x. And then I have the simple interest earned from the corporate bond fund, which is 0.12x. So if I sum these amounts together, this needs to be equal to what? Well, again, it tells us that he has $70,000 to invest, and he wants to earn an overall rate of return of 9%. So the sum of the simple interest from those two investments has got to be equal to 70,000, which is the principal, times the rate, which is 0.09, times the time, which is 1. Okay, so you can just leave that off. So let's go through. We've set up our equation now, and let's just solve this guy. So 0.08 times 70,000 is 5,600. Then minus, you'd have 0.08 times x, then plus 0.12x, and this equals 70,000 times 0.09 is 6,300. So 6,300. So negative 0.08x plus 0.12x is going to be 0.04x. So you'd have 5,600 plus 0.04x is equal to 6,300. Then I can subtract 5,600 away from each side of the equation. That'll cancel. If I have 0.04x is equal to 6,300 minus 5,600 is 700. Okay? So the last step here to get x by itself is to divide both sides by 0.04. I'll get x is equal to 17,500. Okay, so let's take this back up. So this is where you really need to, again, think about a sentence you can write, because you don't just put x equals 17,500 and turn in the test. Okay, you've got to make sense of it in terms of the problem. So x was the amount invested in the bond fund. So we know that's $17,500. Then 70,000 minus x, so 70,000 minus 17,500, or 52,500, is the amount invested in the savings account. So this is 52,500. So now we're ready to go back up and answer this in terms of the question being asked. How much should be invested at each rate? Well, we can say that Jason should invest $52,500 in the savings account and $17,500 in the bond fund. Okay. So Jason should invest $52,500 in the savings account and $17,500 in the bond fund. Okay. So how can we check this to make sure that it's accurate? Well, again, if we go back to the beginning of the problem, Jason has $70,000 to invest. So let's check that first. Is the amount that he put in the bond fund plus the amount that he put in the savings account equal to 70,000? 52,500 plus 17,500 does equal 70,000. So that part is a check. So this is good to go. Now he wants to earn an overall rate of return of 9% annual simple interest. So 70,000 earning 9% annual simple interest would mean that he's earning $6,300 a year in annual simple interest. Okay, so let's check that against what he's going to earn with the two investments. So he's going to earn 8% with the savings account, and he's going to earn 12% with the corporate bond fund. So let's go back up. We have 6,300 as the amount that he's earning, and we're going to check. So we have 52,500 in the savings account, which is earning 8%. So that would give me $4,200 a year. And then he put 17,500 in the bond fund, which is earning 12%. So that would give him $2,100. Okay. So if you sum these two amounts together, the $4,200 he gets from the savings account and the $2,100 he gets from the bond fund, he's going to get the $6,300 he's looking for in annual simple interest. So we can say this problem does check out. And again, Jason should invest $52,500 in the savings account and $17,500 in the bond fund. All right, let's take a look at one more of these. So Jennifer recently retired and needs $6,000 per year in supplemental income from investments. So she has $50,000 that will be invested in both junk bonds, which pays 15% annual simple interest, and commercial paper, which pays 7% annual simple interest. How much money should be invested in each? So again, let's go back up. Again, she retired and needs $6,000 per year in supplemental income. So she needs $6,000. She has $50,000. So that's going to be her principal. And that will be invested in, again, both junk bonds. The junk bonds are going to pay 15% annual simple interest, and the commercial paper is going to pay 7% annual simple interest. So how much money should be invested in each? Okay, that's what we're trying to answer. So let's let a variable like X be the amount that she invests in, let's just say the commercial paper. You can put it as either, but I'm just going to go with the commercial paper. So let's go ahead and do that real quick. So let's let X be equal to the amount invested in commercial. And let me just abbreviate that because it's kind of hard to write all that. So I'm just going to put commercial paper as C period P period. So then what can we say about the amount that's put into junk bonds? Well, again, the total amount she's investing is $50,000. So we can say then $50,000 minus X is going to be the amount invested in junk bonds. So I'll put J period B period, okay, for junk bonds. So let's take this information to a table, just like we did in the last example. So for our investments, these are going to go down. You have your junk bonds and you have your commercial paper, okay? And again, we have our simple interest formula. I, the simple interest earned, is equal to P, the principal, times R, the rate, times T, the time, okay? Now in this case, we're talking about an annual basis. So time is just going to be 1 for each of these, okay? So very, very simple. For the rate, we know that for the junk bonds, they pay 15%, so 0.15. We know for the commercial paper, it pays 7%, so 0.07. Again, you've always got to express the rate as a decimal. And then the principal, or the amount invested in each of these, we just modeled that. We said X is the amount invested in the commercial paper, and 50,000 minus X is the amount invested in the junk bonds. So the principal, or again, the amount invested in the commercial paper is X, and the amount invested in the junk bonds is going to be 50,000 minus X. Okay, so my simple interest earned, again, all I've got to do is multiply in the rows. So I would have principal of 50,000 minus X times a rate of 0.15 times 1, which really doesn't change anything. So you basically have 0.15 times the quantity, 50,000 minus X. Again, hard to kind of fit that in the column. And then over here, it's pretty easy for the commercial paper. It's just going to be 0.07 times X. Again, you can multiply by 1, but it doesn't really change anything. Now, we are told that she wants to earn $6,000 per year in supplemental income from investments. Okay, so what do we know? We know that the interest she's going to earn from the junk bonds is 0.15 times the quantity, 50,000 minus X. Then if we add that to the interest she's going to earn from the commercial paper, which is 0.07X, this has to be equal to 6,000, okay, because that's what she needs to earn. So let's go ahead and solve this equation. Very, very easy. 0.15 times 50,000 is 7,500. And then minus 0.15 times X is 0.15X. Then plus 0.07X, again, is equal to 6,000. If we combine like terms here, you'd end up with negative 0.08X. So 7,500 minus 0.08X is equal to 6,000. I'm going to subtract 7,500 away from each side of the equation. That's going to cancel. Let me get some room going. So on the left, I'm just going to have my negative 0.08X. On the right, I'm going to have negative 1,500. We'll finish this up by dividing both sides of the equation by negative 0.08. So this is going to cancel with this, and I'll have that X is equal to 18,750. So 18,750. Okay, so that's our answer for X. But again, we're not done. We've got to make sense of that. So again, X was the amount invested in commercial paper. So we know that's $18,750. And then we said that 50,000 minus X, which is $31,250, is going to be the amount invested in the junk bonds. So 31,250. Okay, so let's go back up and make a nice little clean sentence. So Jennifer should invest $31,250 in junk bonds. I'll just abbreviate it. And $18,750 in commercial paper. Okay? So you can check this pretty easily by going back to the original statement where it said Jennifer recently retired and needs $6,000 per year. Okay, so that's what she has to earn. So just check the simple interest from the two investments. Again, from the junk bonds, she's got $31,250 invested, and she's getting 15% on that. So times 0.15, that's going to give you what? That's going to give you $4,687.50. Okay, so this is what she earns from the junk bonds. I'm just going to put junk bonds. Okay, this is what she earns in yearly simple interest. Then from the commercial paper, she's going to earn 7% on $18,750. So if I had $18,750 times 0.07, I would get $1,312.50. So $1,312.50. So all you have to do to check this problem is sum these two amounts together. Does it give you 6,000? The answer to that is yes, right? If I add $4,687.50 to $1,312.50, I will get $6,000. So that does tell me my solution is correct, that Jennifer should invest $31,250 in the junk bonds and $18,750 in the commercial paper. In this lesson, we want to review applications of linear equations and look at percent problems. So when we're in our section on applications of linear equations, again, we can use a little 6-step procedure to get a solution for our word problem. So for solving a word problem, again, the first step is just to read the problem and determine the question or questions to be answered. Then the next step is to assign a variable to represent the unknown. Again, with these type of problems, you're going to express other unknowns in terms of this variable. Then we're going to write an equation that expresses the situation we're given, right, based on the scenario in the problem. Then we're going to solve that equation. Then we're going to write the answer in terms of the question or, again, questions asked. And then lastly, and most importantly, we're going to check the answer using the words of the problem. We always want to make sure that our answer is reasonable. All right, so for solving percent word problems, it's a very easy case scenario. It's one of the easiest types of problems that you deal with when you're talking about applications of linear equations, okay? So essentially, as long as you understand how to convert between a decimal and a percentage, you're basically good to go, okay? So we have that Kristen works as a cashier for a local clothing store. After a busy shift, she had a total of $16,277.17 in receipts. So this amount included the 8.5% state and local sales taxes. Now, if the sales tax rate had been 10%, how much would she have collected in state and local sales taxes? So this is what we need to figure out. Again, if the sales tax rate had been 10%, in this problem, it was 8.5. So if it had been 10%, how much would she have collected in state and local sales taxes? So that's what we need to find out. So to attack this problem, it's very, very simple. You have two amounts that you're going to work with. The first amount is the $16,277.17 in receipts, and the second amount is the 8.5% state and local sales taxes. So think about what this means. She's got this amount in total receipts, so it included the state and local sales tax, okay? So think about this. You have a pre-tax amount of goods sold, so you have some pre-tax amount of the goods sold, plus you have the taxes that are collected. And when we sum these two amounts together, we get this value here, this $16,277.17. So what I'm going to do is I'm going to let a variable like x equal the pre-tax amount of all the goods sold. So let's go down, and I'm just going to say we're going to let x be equal to the pre-tax amount of goods sold. Okay, so again, if I go back to what I wrote there, I said that the pre-tax amount, which we labeled as x, right, this will now be x, plus the tax amount, which how can we get that? Well, if she sold X amount of goods and the tax is 8.5%, well, then all I have to do is multiply 8.5% times that pre-tax amount, right, which is X. Now, you do that as a decimal. So 8.5% as a decimal is 0.085. So plus 0.085 times x. That would give me my 16,277.17. So it's very easy to get our equation. Let me kind of arrow that up there. And I'm just going to copy this because it's kind of busy here. So let me remove that from here. And let me just kind of throw that down here so we can just get some thought processes going. And we see that, again, the pre-tax amount is x plus the tax amount, which is 0.085, which, again, is 8.5% as a decimal, times x, which is the pre-tax amount. That gives me the tax. You sum those two amounts together, and, again, you get our total receipts, which is $16,277.17. So on the left side, I can just sum this, right? So this is basically 1x plus 0.085x. So this would be 1.085x. Let me make that 8 a little better. And again, this is equal to this $16,277.17. Now, if I want x by itself, just divide both sides by 1.085. Again, over here, 1.085. I'm going to do that with a calculator, and I'm going to end up with x is equal to 15,002. Okay? So let me erase everything other than my x. Okay, I don't need any information anymore because I basically found what I need. The pre-tax amount of goods sold. So this is $15,002. Okay? Now, it doesn't ask us for this information in the problem. If we go back up, it specifically says if the sales tax rate had been 10%, how much would she have collected in state and local sales taxes? So they don't care that it's $15,002 in sales pre-tax, right? They don't care about that at all. They want to know, again, if the sales tax rate had been 10%, what would she have collected in state and local sales taxes? So I would just multiply this by 0.10. That's 10% as a decimal. That's very easy to do. I just moved my decimal point one place to the left. So you would have $1,500.20. Okay? So $1,500.20. That's going to be your answer. So I'll say she would have collected. So it's going to be $1,500 and then 20 cents. Okay, so she would have collected $1,500.20. You can put in, I'm just going to put sales taxes. So sales taxes. Okay, so to check this is pretty easy. If she had $16,277.17 in total receipts, and again, this included the 8.5% state and local sales taxes, well, if I started with, again, the $15,002 in pre-tax goods sold, if I added in the 8.5% tax on that, one way that I could do that is I could multiply 15,002 by 1.085, okay? And that would give me the 16,277.17. So that part would check out. Now, I know that it's $15,002, okay? That's pre-tax goods sold. Again, if the sales tax rate had been 10%, all you got to do is move the decimal point one place to the left, okay, to multiply by 0.1, 10% as a decimal, and you would end up with this $1,500.20, again, in sales taxes. Okay, so our answer here is correct. Again, she would have collected $1,500.20 in sales taxes. All right, let's take a look at another one. So we have here that James took a few friends to lunch and paid a total of $141.45, including sales tax and tip. If the state and local sales taxes were 8% and he gave a 15% tip on the pre-tax amount, what was the price of his lunch before tax and tip? So this problem sets up in a similar way, but what we want to find out is what was the price of his lunch before tax and tip? So before he gave the tax and the tip, what would the amount have been? So again, just like the last problem, we have a pre-tax, pre-tip amount, or we could say the original amount of the food. So the original amount. Then you have plus the tax and then plus the tip, and this equals this 141.45. So let's bring this down to a fresh sheet. So the original amount, I'm just going to call that X. So let X be the original amount of the food. Okay, this is before tax or tip. So if I have X plus my tip and plus my tax, again, I'm going to get this 141.45. So we said that the tax, if we go back up, was 8% and the tip is 15%. So the tax, again, is 8%. So that's 0.08 times X, right? That's 8% as a decimal, 0.08. Again, multiply that by X. That's going to give you the tax. Okay, and again, this is the original amount. Or you could say pre-tax, pre-tip amount, whatever you want to do. Then plus, I've got to get my tip, and the tip is 15% of the original amount. So that's 0.15, which is 15% as a decimal, times X. So this is your tip. So this equals, you've got your 141.45. If I sum everything on the left, just combine like terms, what's going to happen is I'll have 1x plus 0.08x plus 0.15x. So 1 plus 0.08 plus 0.15 is going to be 1.23, and then times x. And again, this equals 141.45. Divide both sides of the equation by 1.23. And what are we going to get? We're going to get that x is equal to 115. Okay? So that was the price of his food before, again, the tax and the tip. So we'll say that James's lunch was $115 before tax and tip. Okay? And again, pretty easy to check this. If you think about the $115 before tax and tip. So if he had $115, his tip would have been what? It would have been 15% of that. So 15% of 115 is 17.25. So you'd have 115 plus 17.25. That's your tip. And then plus your sales tax, that's 8%. If you did 8% of 115, you would get 9.2. So if you add those three amounts together, you will get the 141.45. Okay, so that tells us our solution here is correct. James's lunch, again, was $115 before tax and tip. All right, let's take a look at one more problem. Again, these are very, very easy problems. So Evelyn works as a sales floor associate at a local hardware store. She receives a weekly salary of $800 along with an 11% commission on all of her sales. So last week she earned $1,350 from her salary and commission. What is the dollar amount of the merchandise that she sold? So this is what we're trying to find out. What is the dollar amount of the merchandise that she sold? Okay, pretty easy. So again, she receives a weekly salary of $800 and she gets an 11% commission on all of her sales. Okay. Again, last week, this is what she earned. She earned $1,350. So the key to understanding this is that she's going to get that $800 as a salary no matter if she sells $0 or $1 million. Okay, it doesn't matter. She's getting a weekly salary plus commission. So if she got $1,350, I need to subtract the $800 away to find out what her commission was. So I would do $1,350. Again, the total amount she got minus the $800, which is kind of the salary or the set amount she gets no matter what. So if we subtract this away, this comes down 5, borrow here, 13 minus 8 is 5. So she's got $550 from commission. So $550 from commission. Okay. So how much was her commission rate? Again, it was 11%. Okay, so it's 11% for the commission rate. So what this means is that she has some amount of goods sold. Let's just say it's X. So let X be equal to the amount of goods sold, okay, by her. So if I take X and I multiply it by 11%, that would give me the amount of commission she made, which we know is $550. So as a decimal, 11% is 0.11. So 0.11, then times X, again, the amount of goods she sold, should be equal to $550. Okay, that's, again, the amount of commission she received. If I divide both sides of the equation by 0.11, I'm going to get that X is equal to 5,000. Okay, so this is what she sold in merchandise. Okay, if she sold $5,000 worth of stuff and she got an 11% commission on it, she would get $550 in commission. You can check that in your head. 5,000 times 11% is 550. Again, that's what we said she got in commission. So let's go ahead and write our solution as a sentence. Just change my marker here, and I'll say that she sold $5,000 worth of merchandise. If you want to check this, it's pretty easy. You can check it almost in your head if you wanted to. Again, she got a total of $1,350 from her salary and commission. It says right here that her salary was $800. Okay, so again, take the salary out. That's going to give you $550 that she got from commission. Now, if she sold $5,000 worth of merchandise and she gets an 11% commission, again, you can check that really quickly and say, okay, well, 5,000 times 0.11 would give you $550. So our answer here is correct. Again, she sold $5,000 worth of merchandise. In this lesson, we want to review applications of rational expressions, and specifically here we're going to look at some motion and some work rate problems. So at this point you should be pretty comfortable with solving word problems, and although some problems in this section will not result in linear equations, we can still rely on our little 6-step procedure that we used in our section on applications of linear equations. So again, for solving a word problem, the first thing we want to do is read the problem and determine the question or questions to be answered. Then the next thing we want to do is assign a variable to represent the unknown. And for the scenarios we're going to have today, we can express other unknowns in terms of this variable. Then the next thing we want to do is write an equation, and this is based on the scenario we're given. Then we want to solve the equation. Then we want to write the answer in terms of the question or, again, questions asked. Then lastly, we want to check the answer using the words of the problem. Just make sure that things are reasonable. So if you're in the section on applications of rational expressions, the most common problems you're going to see are going to be work rate problems, or some people call them rate of work problems, or you're going to see motion word problems, right? These involve, again, the distance formula. Distance equals rate of speed times time traveled. Okay, so we talked about this formula when we looked at applications of linear equations, so we see it again. Okay, and we'll see this throughout our course many times. So again, if you don't know the formula, d for distance is equal to r for rate times t for time. So if I'm going 40 miles per hour and I do this for 3 hours, I multiply 40 times 3, that gives me my distance of 120 miles. Okay, so this would be 120 in that case. So pretty easy formula to understand, very, very intuitive, and we're just going to use it to kind of solve this first problem. So the Conner River has a current of 8 miles per hour. Find the speed of Lauren's boat in still water if it goes 210 miles downstream in the same time it takes to go 98 miles upstream. Okay, so what are we being asked for? We're being asked to find the speed of Lauren's boat in still water. Okay, this is what we need to find. Now we're given a lot of information to help us find this. It tells us the Conner River has a current of 8 miles per hour. It also tells us that her boat can go 210 miles downstream in the same time it takes to go 98 miles upstream. So when you get these type of problems, you need to understand the difference between still water, upstream, and downstream. Okay, so the way these problems work, if you're in still water, basically there's no current. Okay, if you're going upstream, you are fighting the current. Okay, so you have to subtract the speed of the current away from the speed of the boat in still water. If you're going downstream, the current is pushing on you. Okay, so you're going with the current, and so now you need to add the speed of the current to the speed of the boat in still water. Okay, so we'll talk about that more in a second. For right now, our next step is to what? Is to assign a variable to represent the unknown. Our unknown here is the speed of Lauren's boat in still water. So I'm just going to let x be equal to that. So let's let x be equal to the speed of Lauren's boat in still water. Okay, so that's water with no current. All right, so let's take this down to a little table so we can organize our information. So the first thing I'm going to do is put my distance formula up here. Again, d stands for distance, and this is equal to r, which stands for rate of speed, multiplied by t, which stands for time traveled. Okay, again, if I'm moving at 40 miles per hour and I do this for 3 hours, 40 times 3 is 120, so I know I would go 120 miles. Okay, it's a very intuitive formula. So I'm just going to put my two scenarios over here on the left. So we have upstream and we have downstream. Okay, so what am I told in the problem? Again, my rate in still water is unknown. That's what we're trying to find. But we expressed it as x. So I'm going to put x here and I'm going to put x here. Now, in the case where I'm going upstream, again, I'm fighting the current. The current is 8 miles per hour. So I've got to subtract 8 away from the speed of the boat in still water. So I subtract 8 away from x. In the case of going downstream, it's the opposite, right? The current's pushing on me. So I'm going to add 8, or again, the speed of the current, to the speed of the boat in still water. So for upstream, my rate is x minus 8. For downstream, my rate is x plus 8. Now, What about the distance? Well, it specifically tells us that the boat goes 210 miles downstream in the same time it takes to go 98 miles upstream. So my distance for downstream will be 210, and my distance for upstream will be 98. So for downstream, it's 210. For upstream, it's 98. Okay, so now what about the time? Well, to do the time, what we can do, we can solve the distance formula for time. So again, distance is equal to rate of speed times time traveled. Okay, so if I divide both sides by r, what's multiplying t there? We know that this would cancel with this, and I basically have that time is equal to distance over rate. So right now I have a distance and I have a rate for each scenario. So if I divide my distance by my rate, I'm going to have my time modeled. Okay, so let me erase this. So for upstream, my distance is 98 and my rate is x minus 8. So the time, again, is distance divided by rate. So it's going to be 98 divided by x minus 8. For downstream, again, my distance is 210 and my rate is x plus 8. So my time for downstream will be 210 over x plus 8. Now, it tells us in the problem, let me go back up, that the boat can go 210 miles downstream in the same time it takes to go 98 miles upstream. So all we have to do is set the two times equal to each other, because again, in the problem, it tells us that it's the same. It says in the same time, okay? So I can take 98 over x minus 8. So 98 over x minus 8. That's the time for going upstream. And set this equal to my time for going downstream, which is 210 over x plus 8. So let me just copy this. We'll go to a fresh sheet. So how can we solve this? We already know how to solve rational equations. It's very, very easy. In this particular case, I don't need to multiply both sides by the LCD, right? The LCD would be x minus 8 times x plus 8. I could multiply both sides by that, but a quicker method here would be just to cross multiply. So you take this guy right here, multiply by this. You take this guy right here, multiply by that. So essentially what I'd have is 98 times the quantity x plus 8 is equal to, you'd have 210 times the quantity x minus 8. So I could just start by using my distributive property on each side. But one thing you want to see here is that 98 and 210 are each divisible by 14, right? So to make this a little easier on myself, I'm going to divide both sides of the equation by 14. Remember, this is multiplication here. So this is legal to cancel. 98 divided by 14 is going to give me 7. So I'd put a 7 here. Then 210 divided by 14 is going to give me 15. And now I have smaller numbers to work with, so it's just going to make my life a lot easier. So 7 times x is 7x, and then plus 7 times 8 is 56. This equals 15 times x is 15x, and then minus 15 times 8 is 120. Okay, so let me scroll down a little bit, get some room going. I can subtract 15x away from each side of the equation, and I can subtract 56 away from each side of the equation. So we know that this is going to cancel, and this is going to cancel. 7x minus 15x is going to give me negative 8x. And this will be equal to negative 120 minus 56 is negative 176. If I finish this up by dividing both sides by negative 8, right, the coefficient of x there, what I'm going to get is this cancels with this. I'll have x is equal to 22. So this is what we're looking for. I can't just put x equals 22, obviously. I've got to answer my question. But x tells me the speed of Lauren's boat in still water, which is exactly what we want to know, right? So it's going to be 22 miles an hour. So I can say this is 22 here. And let me go up and just answer my question. So I can just say that Lauren's boat has a speed. Let me make this better. Of 22 miles per hour in still water. So how can we check to make sure we got the right answer? Well, again, if we go back to the fact that time is equal to distance over rate, we can just kind of think about the scenario we're given. For the downstream scenario, we know that her distance is 210 miles, and we know that her rate of speed is the speed of the boat in still water, which is 22, plus the speed of the current, which is 8, so that's going to be 30. So 210 divided by 30 would be 7. So this is her downstream scenario. It took her 7 hours to go 210 miles. Now, the other scenario, let me just set this up over here. We know that she goes 98 miles, going at a rate of speed. Remember, if it's going upstream, it's going to be 22, the speed of the boat in still water, minus 8, okay, the speed of the current, which is going to be 14. Okay, so this is 14, and we know that 98 divided by 14 is 7. So this is true, right? It took her the same amount of time to go 210 miles downstream, right, 7 hours, that it takes to go 98 miles upstream, again, 7 hours. So our answer here is correct. Again, we can say that Lauren's boat has a speed of 22 miles per hour in still water. All right, now let's move on and talk about rate of work problems, otherwise known as work rate problems. So essentially, these are very easy problems to solve once you understand how to kind of set them up. And they just deal with the rate of speed at which a job can be completed, given the individual work rates from the people performing the job. Okay, so again, very, very easy. If you understand the distance formula that we just used in the last problem, then you could understand this formula I'm going to give you here today. So the distance formula, again, is d for distance is equal to the rate of speed, r, times t for time travel. Okay, very intuitive. Again, if I go 40 miles per hour for 3 hours, 40 times 3 is what? It's 120. So I know I've gone 120 miles. Okay, very intuitive, very easy to understand. The same thing goes when we work with work rate problems or rate of work problems. So instead of D, you have A, which stands for the amount of work completed. And we think about this in terms of jobs completed. So it could be 1 jobs completed in pretty much every scenario that I've seen. But if you wanted to extend that and say, okay, we have 2 jobs completed, 11 jobs completed, 2 million jobs completed, whatever that is, okay? But A here stands for the amount of work completed. This is equal to R, which is your rate at which the work is done, okay? Otherwise known as a work rate. That's how these problems get their name, okay? Then times T, which is our time, and that's the amount of time that you're working for. So let's say, for example, my rate of work, and this will make more sense when I explain in a minute, is 1/4, okay? And I multiply this by a time of 8. What does that give me? We know that 8 times 1/4 is 2. So what does this mean? My work rate tells me how much of the job I can complete in 1 unit of time. So let's say, as an example, I'm working with hours, and let's say I was painting a house. So it takes me 4 hours to paint the house. Well, in 1 hour or 1 unit of time, I'm done with 1/4 of that job. If I work at this rate for 8 hours, okay, I continue at 8 hours, I'm going to paint 2 houses, right? Okay, that's all that's saying. If I change this to 4, then this just becomes 1, right? So if I work at a work rate of 1/4 of the job per hour, and I do this for 4 hours, well, then I've got 1 completed job. Now, in almost every case, or in every case that I've ever seen, A is going to be 1. So basically what you want to focus on here, and let me erase this, we don't need this information anymore. This R here is your rate of work or your work rate. That's what you're focused on in the problem. So I'm going to divide both sides of the equation by T. That's what's multiplying R. So I can isolate, and I'll say that R, my work rate or rate of work, is equal to 1/T. So this is very important. You probably want to write that down in your notes if you're taking notes. This is what we're going to use in almost every scenario to get an answer, okay? So you've got to know that if you're working on a problem like this and you want your work rate, just take a 1 and divide it by the amount of time it takes to complete the job. So again, in the case where we could paint the house in 4 hours, well, I would get a work rate. My R would be equal to 1/, takes 4 hours to complete it, so 1/4. And all this is telling me is that in 1 unit of time, or 1 hour, I've completed 1/4 of the job, okay? As another example, suppose it takes me 15 minutes to wash my car, okay? In 1 unit of time, which is now 1 minute, because we're working with minutes, then I've done 1/, again, it took me 15 minutes to complete it, so 1/15, or 1/15 of that job is completed, okay? So that's the general idea behind these problems. And now let's kind of jump in and look at one. All right, so working alone, it takes Heather 30 minutes to wash the car. Jacob can wash the same car in 45 minutes. How long would it take Jacob and Heather to wash the car if they work together? All right, so the first thing I'm going to do here, just like we always do, is just find out what are they asking us to find. Well, the question we need to answer here is how long would it take Jacob and Heather to wash the car if they work together? This is a pretty typical scenario. So you have their individual rates of work, right? We know that Heather takes 30 minutes to wash the car. We know that Jacob takes 45 minutes to wash the car. But hey, if they work together at the same speed that they're working at when they do it individually, how long would it take for them to wash the car? Okay, so that's what we're trying to figure out. So what I'm going to do is I'm going to let a variable like x be equal to that. So I'm going to go to the next page, and I'm just going to say that we're going to let x be equal to the amount of time. And I'm just going to say to complete the job. To complete the job. Right? But if you wanted to be more detailed, you could say the amount of time to complete the job when Jacob and Heather work together. Okay? And of course, since we're working with minutes here, the units are going to be minutes. Okay? So you got to make sure of that, because in some of these problems, you have crossovers between minutes and hours. You could have minutes and seconds, so on and so forth. But for this one, it's very easy. We're just working with minutes. All right, so let's go down to a little table. And we're going to organize some information. And then once you see this, in the next few problems, you're going to go right through it. Okay, very, very simple. So, of course, we have Jacob and we have Heather. Now, the first thing I'm going to write is the rate of work. So, the rate of work. And before we started this problem, we talked about how to get it. It's 1 over the amount of time they take to complete the job. So I'm going to put a 1 over and then blank for each one. Let's go back up. So for Heather, it takes 30 minutes to wash the car. So her rate of work would be 1 over 30. Again, for every minute that passes, she's done 1/30th of that job. For Jacob, his is going to be what? It takes him 45 minutes to wash the car, so it's going to be 1 over 45. Every minute that passes, he's going to be done with 1 over 45, or 1/45th of that job. So let's go down. Again, for Jacob, he's got a work rate of 1 over 45. For Heather, she's got a work rate of 1 over 30. Okay, so now I'm going to put time working together. So time working and then together. Now, we modeled this on the page up as x, the amount of time to complete the job. Again, this is working together. So I'm just going to put this as x here and x here. Okay, it's the same in each case. Now, the next thing you need is the total contribution of each person. How much of the car does Jacob get done in this amount of time? How much of the car does Heather get done in this amount of time? So I'm just going to write this as total contribution. Okay, so to get this, we can just multiply, right? Because if you want to know the amount of work that Jacob performed, I just multiply my R times my T, right? My A, the amount of work that's performed, is R, the rate of work, times T, the time that you're doing that work for. Well, I've got my rate of work. I've got my time that I'm working for. So my contribution here, or the amount of work that's being performed for Jacob, is 1 over 45 times x. You could write it as 1 over 45 times x, or you could write it as x over 45, which is probably a little better. Same thing goes for Heather. It's going to be x over 30, right? Just multiply across. Very, very easy. And now what we need to understand is that between Jacob and Heather, they're going to complete one job, okay? So the equation here is very easy to set up. Jacob's contribution, which is x over 45, plus Heather's contribution, which is x over 30, is going to be equal to 1. Again, that's for one completed job. So the first time you see this, it might not make a whole lot of sense. But again, after you solve like 2 or 3 of these, you're going to find that these are the easiest problems in the world to solve. So let's copy this. So what I'm going to do to clear these denominators, I'm going to multiply both sides of the equation by the LCD. The LCD, if I look at the denominators, I got 45 and 30, it's going to be 90. So I'm going to use my distributive property here. 90 times x over 45. 90 divided by 45 is 2. 2 times x is 2x. Then plus 90 divided by 30 is going to be 3. Then times x is 3x. And this equals 90. Sum on the left, so 2x plus 3x. If I combine like terms there, I get 5x. This equals 90. Divide both sides of the equation by 5. And we're going to find that x is going to be equal to 18. So 18 is the number of minutes that they each have to work when they're working together to complete the job, right? So if we go back up, again, we said amount of time to complete the job. That's when they're working together. And of course, this is in minutes. So let me just say that they work for 18 minutes to complete the job. Okay. You can answer a whole lot of different ways there. That's just a very simple sentence to say they work for 18 minutes to complete the job. Now, is it correct? How can we check this? Well, we can take the fractional amount that Heather does and the fractional amount that Jacob does and add those together and see if it equals 1. So we know that if we go back down, A is equal to R times T. I'm going to put two scenarios. A equals R times T. So how much or what amount of the job does Heather do? Well, remember her R, her rate of work is 1 over 30. And she works for T minutes. And again, we found that the time that they're going to work together, which we labeled as X, was going to be 18. So essentially I'm going to put this as times 18. That's going to give me the amount of work that she does. So between 18 and 30, I have a common factor of 6. So if I divide 18 by 6, I get 3. If I divide 30 by 6, I get 5. So I get 3/5 there. So this is going to be 3/5. That's the amount of work that she completes. Now, for Jacob, he's a little bit slower. So his rate of work is 1 over 45. And the time is the same, right? Because they work the same amount of time when they're working together. So this is 18. Each here is divisible by 9. 45 divided by 9 would be 5. 18 divided by 9 would be 2. So this is 2/5. Now, if you go ahead and take the amount of work that Jacob completes, which is 2/5, that's what he does in 18 minutes, and you add that to the amount of work that Heather completes, she's got 3/5 of the job that's completed, right? That's what she does in 18 minutes. You do get 1, right? 2/5 plus 3/5 is 5/5. 5/5 is 1. So we can say our answer here is correct. They work for 18 minutes to complete the job. All right, very easy overall. Let's take a look at another one. So working together, James and Nathan can mow a yard in 24 minutes. When James mows the yard by himself, he takes 4 times longer than Nathan. How long would it take for each person to mow the yard if they were working alone? So in the last problem, we knew their individual rates of work, right? We knew that for Jacob, he could wash the car in 45 minutes. For Heather, she could wash the car in 30 minutes. But we didn't know, or we could say we had to find how long it would take if they worked together. In this case, we know how long it takes when they work together, right? It tells us right here it's 24 minutes. But we don't know how long it takes them individually, okay? So that's the question here. How long would it take for each person to mow the yard if they were working alone? So how long does it take for James? How long does it take for Nathan? So we're specifically told that James takes 4 times longer than Nathan. So let's let X be equal to the amount of time it takes for Nathan to mow the yard by himself. So the time for Nathan, and I'm not going to write the rest. You can write the rest if you want, but it's just the time for Nathan to, again, mow the yard by himself. So then because James takes 4 times longer, again, it tells us that right here, when James mows the yard by himself, he takes 4 times longer than Nathan. What I can do is just multiply 4 times X to get the time for James. So I could say then 4X is equal to the time for James. Okay, let's go back to our table and kind of organize. So again, we have Nathan and James. So we have Nathan and we have James. And again, we have the rate of work, and we have the time working together. And then we have their total contribution. So for the rate of work, remember, it's 1 over the amount of time it takes for that person to complete the job. So if it takes me 4 hours to paint a house, again, the rate of work is 1 over 4. That's how much I'm going to do in 1 unit of time. So in an hour, I'm going to do 1/4 of the job. Here, we know for Nathan, this is in terms of minutes, he can complete 1 over X amount of that job every minute, okay? So for James, it's going to be 1 over 4X every minute. So for Nathan, it's 1 over X. For James, it's 1 over 4X. The time working together. It tells us that in the problem. It tells us specifically that James and Nathan can mow a yard in 24 minutes. That's, again, when they're working together. So each person is going to work for 24 minutes in this scenario. So what's their contribution? Again, you just multiply. This is the rate of work. This is the time working. So 24 times 1 over X. You can do just 24 over X to make it simpler. And then here it's 24 over 4X which we could simplify. 24 over 4 is 6. So I could just say this is 6 over x. Now, how do we get an equation going? Well, we know that when we sum the amount of work done from both of them over this, again, 24-minute period, they've completed one job. So the amount of work that Nathan does is 24 over x. The amount of work that James does is 6 over x. If I add these two amounts together, I should get one completed job. So let's copy this. All right, so what can I do here? Well, I can multiply both sides of the equation by x, right? That would be the LCD. So I'll multiply this by x, and this by x. So essentially, this is going to cancel, this is going to cancel. You'll basically just have what? 24 plus 6, which is 30, is equal to x. So that's really a piece of cake. We've immediately found that x is 30, and we know that x was the time for Nathan. So this is going to be 30 minutes. And then for James, it's going to be 4 times that, or 120 minutes. If you wanted to put that in terms of hours, you could. That's 2 hours. If you didn't know that, it's okay. You can put it in terms of minutes, right? It doesn't matter. So I'm just going to say that Nathan can mow the yard in 30 minutes. So Nathan can mow the yard in 30 minutes. And then I'll say while James can do it, and you can say 2 hours or 120 minutes. I'll just say 120 minutes because the problem was given in minutes. But again, you can put 2 hours. It's the same thing. So does this make sense? Let's kind of scooch up just a little bit. So again, working together, James and Nathan can mow a yard in 24 minutes. So we know that. When James mows the yard by himself, he takes 4 times longer than Nathan. So according to our answer, James does it in 120 minutes and Nathan does it in 30 minutes. So if this is correct, we're good to go, right? Because it is 4 times. 30 times 4 will give me 120. So that part does check out. We just need to make sure that they can work together and get it in 24 minutes. So again, think about this. The amount of work that Nathan does is he's going to do 1 over 30 of that job every minute. So he's going to do this, again, if they work together for 24 minutes. And then if I add to this how much James does. So he's going to do 1 over 120 of that job for every minute, and he's going to do that for 24 minutes. If I sum these amounts, I should get 1. This is the amount that Nathan does all the way to the left. Then we have plus. Again, we have the amount that kind of James does over here. Again, if I sum them, I should get 1. So how can I reduce this here? Well, I can divide both by 6. That would give me a 4 here and a 5 here. For this one, 120 divided by 24 is 5. So I can cancel this with this and put a 5 here. So you've got 4/5 of the job, which is what Nathan's going to do, plus 1/5 of the job, which is what James is going to do. You sum those two amounts together, you get 5/5 or 1, again, for one completed job. So our answer here is correct. Nathan can mow the yard in 30 minutes, while James can do it in 120 minutes, or again, 2 hours. Okay, so pretty easy overall. Let's look at one that's a little bit more challenging, but again, it's not so much because these problems are really easy. So Claire's empty swimming pool can be completely filled from a garden hose in 30 hours. Her outlet pipe can completely drain a full pool in 120 hours. If for some reason both the garden hose and the outlet pipe are turned on at the same time, how long would it take to completely fill Claire's empty pool? So the question we need to answer here is, how long would it take to completely fill Claire's empty pool? Given these two competing forces, you've got one kind of hose pipe that's filling the pool, and then you've got an outlet pipe, or you could say a drain pipe, that's emptying the pool. So they're kind of working against each other. You can think about this as if you're filling your kitchen sink, okay, and you got the water on full blast, but you hold the stopper just up just a little bit, right? So some of the water can drain. So if the amount of water coming in is more than the amount of water going out, eventually you're going to fill your sink, right? But it's just going to take longer than if you had the sink kind of all the way stopped up, okay? So that's the idea of what's going on here. So how can we model this? Let's just say we're going to let x be equal to the amount of time it would take to completely fill Claire's empty pool. So I'm just going to say let x be equal to the amount of time to fill the pool. Okay. Let's go down to the kind of table. Let's organize some stuff. So we've got our hose that's filling the pool, and then we've got our outlet pipe that's trying to drain it. And let me be more specific here and just put garden hose. So garden hose, because that's what it says in the problem. Now, again, we're going to have our rate of work. We're going to have our time working together. And then we're going to have our total contribution. So we know one thing so far, it's the time working together is x, because we just let a variable represent that. So this is x and this is x. The rate of work, let's go back up. We've got to find the garden hose and the outlet pipe. So the garden hose can fill the pool in 30 hours. So every hour it's done 1 over 30 of that job. So the rate of work is 1 over 30. So I'll put 1 over 30. Now, the outlet pipe, which is trying to drain the pool, that's its goal, okay? So every hour, since it takes 120 hours to do this, it's done 1 over 120 of that. So I'll put 1 over 120. So that's the rate of work. Now, the contribution works a little bit differently here because they're competing forces, right? You can kind of think about the garden hose as filling it. So I'm going to put a positive 1 over 30 times x, or you can just put x over 30. Really, you can think about the outlet pipe as fighting against this, right? You can think about what it's doing as subtracting away. So you can put this as a minus x times 1 over 120, which would be x over 120. So if you sum these two amounts together, you should set it equal to 1 and solve that equation. So I would have x over 30. I'll just put minus, or you can put plus, negative, doesn't matter. I'll put minus x over 120. I'll set that equal to 1. So in other words, the total contribution, or the total amount of water that goes in from the garden hose, minus the total contribution, or the total amount of water that gets pulled out from the outlet pipe, when that's set equal to 1, the value for x is going to tell me the amount of time it takes for them to complete that job, again, working together. So let me copy this. So what I want to do is just multiply both sides by the LCD, which is going to be 120. Pretty easy to do. So I know that I'm going to distribute this to each term inside the parentheses. 120 divided by 30 is 4, right? So I'd have 4x minus 120 divided by 120 is 1. So I just have x there. This equals 120. 4x minus x is 3x. This equals 120. Divide both sides of the equation by 3. And you're going to find that x is equal to 40. So that tells us what? It tells us that the garden hose and the outlet pipe can both be left on, and the pool is going to go from completely empty to completely full in 40 hours. Let's go back up. So it would take 40 hours to fill the pool. Okay, so let's check this. So again, I go back to my formula of A equals R times T. So think about this for each scenario. You have another one over here. So what I'm going to do is I'm going to say the garden hose, how much water does it put in? So we think about the rate. Again, it does a full job in 30 hours. So the rate is 1 over 30. When they work together, again, they're going to work for 40 hours. So the amount that's going to be done is what? I can divide both of these by 10. This will be 3, and this will be 4. So it's going to be 4/3 that's going to be completed. So 4/3 of the job is completed. Now I'm subtracting away what gets completed by the outlet pipe. What's going to get drained away here? So the rate there, again, it accomplishes the whole thing in 120 hours. So it's 1 over 120. And then the time, again, it's going to go for 40 hours. So 120 divided by 40 is 3. So this would be a 3, and this would be a 1. So basically, this is 1/3. So does this make sense? Yes, it does. If the garden hose completes 4/3 of the job in 40 hours, and the outlet pipe completes 1/3 of the job in 40 hours, well, 4/3 minus 1/3 gives me 3/3 or 1. Again, what's happening here is the garden hose is filling a pool and then another third of a pool. Okay, so 4/3. Then the outlet pipe is taking a third away, right? It's taking that extra third away, so you're left with 3/3 or just one full pool. Okay, so we can say our answer here is correct. It would take 40 hours to fill the pool. In this lesson, we want to review applications of linear systems. All right, so over the course of the last few lessons, we've kind of talked about systems of linear equations in 2 and 3 variables. Now we're just going to look at some kind of application problems or some word problems that come up in this section. And then from here, we're just going to be dealing with kind of matrices. All right, so let's start out with the first problem. So we have that a health bar is made from a corn mixture, an egg mixture, and a vegetable mixture. 1 ounce of the corn mixture contains 0.25 grams of protein, 0.3 grams of carbohydrates, and 0.4 grams of fat. The egg mixture contains 0.4 grams of protein and 0.2 grams of both carbohydrates and fat. Lastly, the vegetable mixture contains 0.2 grams of protein, 0.1 grams of carbohydrates, and 0.3 grams of fat. How many ounces of each mixture should be used to create a health bar that contains 22 grams of protein, 18 grams of carbohydrates, and 28 grams of fat? So just like any other word problem that we've kind of worked on before, the very first thing you always want to do is figure out what are you being asked to find. A lot of times you'll struggle because you're kind of flopping around through information, you're not specific on what you need to find. So you need to key in on that, and you need to say, okay, I want to find how many ounces of each mixture. Okay, so remember we had the corn mixture, the egg mixture, and the vegetable mixture, and should be used to create a health bar that contains 22 grams of protein, 18 grams of carbohydrates, and 28 grams of fat. Okay, so we have 3 unknowns, right? We need to know, again, how many ounces of the corn mixture we're going to use, how many ounces of the egg mixture we're going to use, and how many ounces of the vegetable mixture we're going to use to kind of create this health bar with these specifications. So let's go ahead and label these 3 as X, Y, and Z. So let's let X be equal to the amount in ounces for the corn mixture. And then we'll say Y can be equal to the amount in ounces for the egg mixture. And just to keep this short, I'm just going to leave mixture off. And then we'll also say then for Z, we're going to say the amount in ounces for the vegetable mixture. So I'm just going to put VEG to kind of abbreviate that. Okay, so the best way to kind of look at this type of problem is with a table. You don't need one, but it definitely helps. So I've already kind of pre-drawn one for us. So I'm going to show you how you can fill out the information here and then get some equations going and get a solution. So the first thing is, let's talk about the different kind of mixtures you have. You have the corn mixture, you have the egg mixture, and you have the vegetable mixture, okay, which I'm going to abbreviate VEG. Then we're given the amounts of protein, carbohydrates, and fat. So I'm just going to put protein, just PRO, carbohydrates, CAR, and then for fat, just FAT. Of course, that spells fat, but for the other ones, they're abbreviated. Okay, then we also want to put in a total here, and this will make sense once we kind of have the information going. So what I can do is I can look up, back in the problem, the statistics for how much protein, carbohydrates, and fat each one of these guys have. I'm just going to fill in my table. So let's go back up. So for the corn, for every ounce, it's got 0.25 grams of protein, 0.3 grams of carbohydrates, 0.4 grams of fat. So we've got 0.25 for protein, 0.3 for carbs, and 0.4 for fat. All right, for the egg mixture, we have 0.4 grams of protein and then 0.2 grams for both carbohydrates and fat. So we've got 0.4 and then 0.2 and then 0.2 again. Then lastly, for our vegetable mixture, we've got 0.2 grams of protein, 0.1 grams of carbohydrates, and 0.3 grams of fat. So we've got 0.2 for the protein, 0.1 for the carbohydrates, and 0.3 for the fat. Now I have a column here for the total, and what I'm going to do here, notice how going across, it's all protein, right? It's the protein for the corn, the eggs, and the vegetable. We want to know what the protein total is going to be from these 3 sources. And again, it's based on the requirement that's given to us when we're building this health bar. If we go back, we see that it needs to be 22 grams of protein, 18 grams of carbohydrates, and 28 grams of fat. So for the total there, for protein, it's going to be 22, right? Just going across. For carbohydrates going across, the total needs to be 18. And for fat going across, the total needs to be 28. Okay, so this is how we're going to get our equations, because what we know is that the protein only comes from three sources, right? It comes from corn, eggs, and vegetables. The number of ounces of this corn mixture I use, so that's going to be X times this kind of 0.25, which is the number of grams, okay, of protein per 1 ounce. So this amount here would tell me the amount of protein I'm getting from just the corn, okay? But I need to reach this amount, so I'm going to add to this the amount of protein I get from the egg, so that's 0.4 times Y, okay? Then plus, additionally, the amount of protein I'm getting from the vegetables, so 0.2 times Z. This has to be equal to 22, okay? Because that's the only place the protein's coming from. The same thing's going to happen with the carbohydrates and the fat. We can just go across. So I can say that 0.3 times X plus 0.2 times Y plus 0.1 times Z is equal to 18. And I'm going to run out of space here, so let me scroll down. I'm going to cut this off. But remember that the kind of column here is for corn, then this guy is for egg, and this guy is for vegetables. So we're just going to copy. We have 0.4X plus 0.2Y plus 0.3Z equals 28. Okay, so that's all we really need to do. So let's just cut this away from here. We're going to take a fresh sheet, and let's solve this system real quick and get our solution for our problem. Now, you can work with decimals if you want. If you have a calculator, it's fine. A lot of people don't like working with fractions or decimals. So I'm just going to transform this into a kind of decimal-free equation in each case. I'm just going to go ahead and multiply kind of everything by 100. So what I'd have is 25x plus 40y plus 20z equals 2,200. Okay, I just multiplied everything there by 100 so that I could clear all the decimals. Okay, so this one's gone now. And then for this one, I'm going to do multiplying everything by just 10, because that's all you need. So this would be 3x plus 2y plus 1z equals 180. So let's erase that. And then for this one, I only need 10 as well. So I'm going to have 4x plus 2y plus 3z equals 280. Okay, so let's erase this and let's scooch this up. So again, when you work with a linear system with three variables and you're not using a matrix, the first thing you want to do is kind of look at these equations. So I'm just going to label this as 1, 2, and 3. You just want to pick two of them, and then from the two, you want to eliminate one of the variables. So if I look at these equations, it looks like it's pretty easy to eliminate the variable y, okay? Because I have 2y here and 2y here. So from 2 and 3, I can really quickly eliminate y by just multiplying one of the equations by -1. And I'm going to start with 1 and 2 and just multiply equation 2 by -20. So I'm going to keep equation 1 as it is. So 25x plus 40y plus 20z. And this equals 2,200. And again, for equation 2, I'm going to multiply both sides by -20. So -20 times 3x would be -60x. -20 times 2y would be -40y. And you see that now I have opposite coefficients on y. The -20 times z is going to be -20z. And this equals -20 times 180 is going to be -3,600. Okay? Now again, for this process to work, you want to have this kind of in the format where all the variable terms are on one side and your constants on the other. That way, when you add the two left sides and you set it equal to the two right sides, you're adding like terms. So 25x minus 60x is going to be -35x. Then this is going to cancel, and so is this. So this would be equal to, I've got 2,200 minus 3,600, which is -1,400. Okay, so let me erase this information. I don't need it anymore. You could really call this equation 4 if you wanted to. So I could say this is equation 4. -35x is equal to -1,400. So from this, I can just solve for x right away. We kind of got lucky because two things dropped out. So I'm going to divide both sides by -35. And I'm going to find that x is equal to 40. Okay. So at this point, I know that x is 40. So let me erase this and just put equation 4 as saying that x is equal to 40. Okay, so that's one of my equations. Now, I can't really do anything with x equals 40 because I still have two unknowns. So I'm still going to eliminate the same variable, but it's worth noting that when you have this situation, I can eliminate either z or I can eliminate y, okay, from equation 2 and 3 or from equation 1 and 3. And what that's going to do is it's going to give me a linear system with kind of two variables. I already know that x is 40, so I can immediately just plug in and figure out what y is or what z is, again, based on what I choose to eliminate. What I'm going to do is I'm just going to stay consistent, and I'm going to eliminate y again, and I'm going to do that from 2 and 3. So what I'm going to do is I'm going to multiply equation 2 by -1. So I'm going to have negative 3x minus 2y minus z equals negative 180. Again, I just multiplied everything by -1. I'm going to keep equation 3 as it is. So 4x plus 2y plus 3z, and this equals 280. And again, I have opposite coefficients on my variable y. I have -2 and +2. So when I add the left sides, this is going to cancel, right? So negative 3x plus 4x is going to be x. And then we have negative z plus 3z, which is plus 2z. This equals negative 180 plus 280 is 100. So let's erase this. And again, we already know from our equation 4 that x is going to be 40. So I'm going to call this equation 5 now. And I'm going to plug a 40 in for x there. So I have 40 plus 2z equals 100. And let me subtract 40 away from each side of the equation. This cancels. And this will become 60. So let me kind of clean this up a little bit. We essentially just have 2z equals 60, divide both sides by 2. And of course, we find that z is equal to 30. Okay? So let me erase all of this now. We don't need any of this information anymore. I'm just going to put over here that x equals 40 and z equals 30. And now we just need to find y. Okay, and that's pretty easy to do. Just plug into any of the original equations, a 40 for x and a 30 for z, and figure out what y is. So it looks like it's pretty easy to work with this second equation, or this middle equation. So 3 times x, 3 times 40, plus 2y plus 1 times z, z is 30, so just plus 30, equals 180. Okay, well 3 times 40 is 120, 120 plus 30 is 150. So let's erase this and put 150. Then if I subtract that away from each side, this cancels. You'll have 2y is equal to 30. Divide both sides by 2. You get y equals 15. Okay, so y equals 15. All right, so let's erase everything and we can state our answer. So let me copy this real quick and let me just paste that here. So we remember that x is the amount in ounces of the corn mixture we're going to use, and that's going to be 40. Okay, so we're going to use 40 ounces of the corn mixture. And then we know that y was the amount of the egg mixture we're going to use. That's going to be 15 ounces. And we know that z is the amount in ounces of the vegetable mixture. That's going to be 30. Okay, so let's write this as a nice little sentence. So we will say that they should use, again, the corn mixture was x and x was 40. So 40 ounces of the corn mixture with, you're going to have, again, 15 ounces. Remember, y was the amount of kind of egg mixture, and we had y equal to 15. So 15 ounces of the egg mixture. And then z was the amount of the vegetable mixture they used, and that was 30. So and 30 ounces of the vegetable mixture. Okay. So they should use 40 ounces of the corn mixture with 15 ounces of the egg mixture and 30 ounces of the vegetable mixture. All right, let's look at a simple interest problem. So James has a total of $200,000 to invest and wants to earn a total of $4,900 in annual simple interest. After meeting with a financial planner, he decides to spread the money into 3 different investments. So James will invest in a REIT, which is a real estate investment trust, which pays 3% annual simple interest, a bond fund, which pays 2.5% annual simple interest, and a savings account, which pays 1.5% annual simple interest. If he invests $80,000 less in the savings account than the sum of the other 2 accounts, how much was invested at each rate? So pretty easy problem overall. Again, when you start these, you want to figure out what you're being asked to find. So we just need to find how much was invested at each rate. remember, he had a total, if we go back up, of $200,000 that's invested, and he wants to earn this amount right here. So we want to set up kind of three variables to represent the three unknowns. We need to know how much he's going to invest in the REIT, or again, the real estate investment trust, the bond fund, and then also the savings account. So let's go ahead and let our variables like X, Y, and Z represent those. So X can be the REIT, okay, that's the amount he invests in that. And then we can say Y will be equal to the bond fund, okay, the bond fund. And then Z can be equal to the savings account. Okay, so we need to get three equations to solve for this kind of three unknowns that we have here. So let me go down and let's think about the first equation. Okay, the first equation is pretty easy. You know that the amount that he invests is $200,000. Okay, and he invests this with three different kind of investment vehicles. So it must be true that X plus Y plus Z equals 200,000. So that can be my first equation. X plus Y plus Z equals 200,000. Okay, that's an easy one because again, the amount he invests in the REIT, which is X, plus the amount he invests in the bond fund, which is Y, plus the amount he invests in the savings account, which is Z, has to be equal to 200,000 because that's what he puts in to all three. Now for the next one, we can read the problem and it tells us specifically that he invests $80,000 less in the savings account, okay, than the sum of the other two accounts, okay? So the savings account was Z and the sum of the other two accounts were X and Y. So if I sum that, that's X plus Y. So it's 80,000 less than X plus Y. So for equation 2, Z, again, the amount he invests in the savings account is equal to the sum of X plus Y. This is the amount he invests in the other two. So the REIT and the bond fund minus 80,000, right? Because it's $80,000 less than this amount here. Now for the third equation, we need to think about the interest, okay, the interest. So to do that, let's set up a little table. So what we're going to have is our REIT, we're going to have our bond fund, and we're going to have our savings account. And then we're going to have the amount invested, or you could say the principal. We're going to have our rate, and this is as a decimal, and then we're going to have our interest, okay? Now we're working with simple interest, it's not compounding, okay? So most of you already know, because we talked about this earlier in the course, the simple interest formula is I, which stands for the amount of simple interest earned, is equal to P, which is the principal, okay, the amount invested, times R, which is the rate as a decimal, times the time. And generally speaking, this is going to be in years, okay, unless they tell you it's in months or something like that. But most of these problems, it's going to be years, okay? Now, in this case, we're talking about on an annual basis, so it's 1 year. So because T would be a 1, you can just drop it out. And you could say that the interest earned, which is this column right here, okay, is going to be equal to the product of these two. The amount invested, or the principal, multiplied by the rate, okay, as a decimal. Okay, so let's erase this real quick and let's see if we can get this information. So specifically, it tells us the REIT pays 3% annual simple interest, the bond fund pays 2.5% annual simple interest, and the savings account pays 1.5% annual simple interest. So for the rate, for the REIT, it's going to be 3% or 0.03 as a decimal. And then for the bond fund, it's going to be 2.5% or 0.025 as a decimal. And then for the savings account, it's 1.5% or 0.015 as a decimal. Now, for the amount invested, remember, this is unknown. X is used to represent the amount invested in the REIT. Y is used to represent the amount invested in the bond fund. And Z is used to represent the amount invested in the savings account. So again, the product of these two would give me the simple interest earned over the course of a year. So 0.03 times X, 0.03 times X is the simple interest earned from the REIT. 0.025 times Y, okay, is the simple interest earned from the bond fund. And 0.015 times Z is the amount of simple interest earned from the savings account. Now, what do we do with this information? How do we make an equation? Well, if you were paying attention to the first part of the problem, it tells us specifically he wants to earn $4,900 in annual simple interest. Now, the $4,900 can only come from these kind of three sources. So I know that the interest from the REIT, which is 0.03x, plus the interest from the bond fund, which is 0.025y, plus the interest from the savings account, which is 0.015z, has to be equal to that amount, okay, that $4,900. So let's copy this. This is going to be our third equation. So again, if you don't like working with decimals, you can clear them. For this one, you've got 3 decimal places here and here. So you've got to multiply everything by 1,000, okay, by 1,000. So this guy would move 3 places to the right, so it would be 30x. So it would be 30x. This guy would be 25y. So plus 25y. Then this guy would be 15z. So plus 15z. And then this guy, again, if this is right here, let me kind of scooch this down so we have room. I'm moving everything 3 places to the right. So I put a 0 here, a 0 here, and a 0 here. This would go 1, 2, 3 places to the right. So I would end up with 4,900,000. Okay? So now that we have our 3 equations, we can solve the system and figure out the answer. Now, for equation 2, you really want to set this up into the format of, ax plus by plus cz equals d. Okay, all the variables on one side, the number, the constant on the other. So I can really just drop the parentheses from here. And essentially what I'd have is, if I move each of these over here, I would just subtract them away. I would have negative x minus y plus z. Okay, so negative x minus y plus z is equal to, and it's going to be negative 80,000. Okay, so it's really easy to use elimination to get rid of either x or y from the kind of first 2 equations. So let's just choose to get rid of x. You'll notice that both of these are going to drop out. So it's going to be a nice, easy scenario for us. So for equation 4, what I'm going to do is I'm going to add equation 1 and equation 2 together. So x plus negative x, that's gone. Y plus negative y, that's gone. Z plus z is 2z. And this will be equal to 200,000 minus 80,000 is 120,000. And of course, if we divide both sides by 2, we'd find that z is equal to 60,000. So we already know what z is, right? Or the amount that he invests in the savings account. What about y and x? So we're going to pick another 2 equations. So again, we can do 1 and 3 or 2 and 3. And we're going to eliminate, you can do either x or y. Okay, it doesn't matter. You just eliminate either x or y so that you can plug in for z and figure out what the other one is and then back substitute again. So from 2 and 3, let me just go ahead and eliminate x. So let me scroll down and get some room going. So equation 2, it's already negative, but let me multiply it by 30. So I would have negative 30x minus 30y plus 30z, and this equals, if I took negative 80,000 and multiplied it by 30, negative 8 times 3 is negative 24. And then I have this many zeros, so 1, 2, 3, 4, and then I'd add one more 0. So this would end up being negative 2,400,000. Okay, so then I'm just going to copy equation 3 as it is. So 30x plus 25y plus 15z equals 4,900,000. Okay, so let me scroll down and get some room going. And we know that this is going to go away. Negative 30y plus 25y is going to be negative 5y. And then plus 30z plus 15z is going to be 45z. And this equals, if I take negative 2,400,000 and add that to 4,900,000, I'm going to get 2,500,000. Okay, and we'll call this equation 5. Again, I already know what z is, so what I'm going to do is I'm going to plug in for z here. It's going to plug that in, and I'm going to find out what y is. So I have negative 5y plus 45 times 60,000, okay, is equal to 2,500,000. Okay, so 45 times 60,000 is 2,700,000. So I would have negative 5y plus 2,700,000. Okay, and this equals 2,500,000. Let me scroll down a little bit. So we already know if I subtract 2,700,000 away from each side, this is going to cancel. I'll have negative 5y is equal to 2,500,000 minus 2,700,000 is going to give me negative 200,000. So negative 200,000. If we then divide both sides by -5, I'm going to find that y is equal to 40,000. Okay, 40,000. So what's x going to be? Well, if I just plug into this first equation, which is pretty easy to work with, I can easily find out that x is going to be 100,000, right? And you can eyeball that and see 60 plus 40 is 100, right? So it's going to be 100 grand. And then if you had 200 there, well, I'm missing 100, right? That's how I did it in my head. But again, you can plug it in, it doesn't matter. So x plus y is 40,000 plus you have your z, which is 60,000. This equals 200,000. And again, you know that this sum here, 40,000 plus 60,000 is 100,000. So this is 100,000 here. And if I subtract 100,000 away from each side, this goes away from here. And over here on the right, it's going to be 100,000. Okay? So we get that x is 100,000, y is 40,000, z is 60,000. So that means that he invests 100,000 in the REIT, he invests 40,000 in the bond fund, and then 60,000 in the savings account. All right, so let's write that real quick. And I'm going to make a nice little concise answer and just say that he invests $100,000 in the REIT, or again, the Real Estate Investment Trust. And then he put $40,000 in the bond fund. And he put $60,000 in the savings account. All right, for the last problem, we have that on Monday, Jennifer went to the store and spent a total of $7.45 on 3 one-gallon containers of milk and 2 cartons of eggs. Later that day, her husband Jim stopped at the same store and spent $6.45 on 2 one-gallon containers of milk and 3 cartons of eggs. When Jim got home, he realized his error and decided to only return the milk, as it would expire too quickly for them to consume. How much will Jim receive as a refund? Okay, so this is what we're trying to figure out. How much will Jim receive as a refund? Now, this is given the fact that he's only going to return the milk, okay? He's not returning the eggs, he's just returning the milk. And we don't know the individual prices for anything. We're only told that, Jennifer goes to the store and she spends $7.45 on 3 one-gallon containers of milk and 2 cartons of eggs. And then later on, Jim goes to the same store. Okay, so we're going to assume it's the same price for the milk and the eggs. And he spends $6.45. He only buys 2 one-gallon containers of milk and 3 cartons of eggs. Okay, so we've got to figure this out with a system of equations. The unknowns here are going to be the cost for a 1-gallon container of milk and the cost for 1 carton of eggs. So let's let x be equal to the cost for 1 gallon, okay, and this is a 1-gallon container of milk. And then y can be the cost for 1 carton of eggs. Okay, so what can we do with this information? Let's go back up. So we know that Jennifer spent $7.45 on 3 1-gallon containers of milk and 2 cartons of eggs. So the way we can model this, since x is the cost of 1 gallon of milk and she bought 3 of them, then 3 times x would be the amount she spent on milk. Then plus, you have the fact that she buys 2 cartons of eggs. Okay, so 2 cartons of eggs. Y is the cost of 1 carton of eggs. So 2 times y would give me the cost for eggs in that kind of transaction. And again, if I sum these 2 amounts together, I get the amount she spent, which is $7.45. Okay, again, you can clear the decimal if you want. You can multiply everything by 100. So we could say this is 745 is equal to 300x plus 200y. Not necessary if you're working with a calculator, but I'll just do it because your book would probably do it. Then for equation 2, I'm going to do the same thing with Jim. So if we go back up. So for Jim, he spends $6.45 again on 2 1-gallon containers of milk and 3 cartons of eggs. So we would have that 6.45 or $6.45 is equal to, again, he only bought 2 gallons of milk, so 2x, plus he bought 3 cartons of eggs, so 3y. Again, you can multiply everything by 100 and say this is 645 is equal to 200x plus 300y. Okay, so let's erase this and let's drag this up. So we only have a linear system with 2 variables, so pretty easy to work with this at this point after we've been dealing with 3. All right, so we can solve this with substitution if we want, or we can solve it with elimination. I think it's probably better to solve it with elimination, although substitution would probably be just as fast, but let's just use elimination. So what I'm going to do is I'm going to eliminate the variable x, and the way I'm going to do that is I'm going to think about the least common multiple between 300 and 200. So that would be 600, right? If I think about 3 and 2, okay, 3 and 2, the least common multiple would be 6. Just because it's 300 and 200, now it would be 600, okay? So what I'm going to do is I'm going to multiply equation 1 by, let's say, negative 2. So 745 times negative 2 would be negative 1,490. And this equals 300 times negative 2 is negative 600. Then, of course, times x. And then 200 times negative 2 would be minus 400, and then times y. Then for this guy right here, I'm going to multiply it by positive 3, okay? So 3 times 645 is going to be 1,935, and this equals 3 times 200 is 600, then times x, then plus 3 times 300 is 900, then times y, okay? So if we sum the left sides together, we're going to get 445, right? So 1,935 plus negative 1,490 would be 445. On the right sides, this would cancel. Negative 400y plus 900y is 500y. So let me erase this. We don't need this anymore. And let me just kind of slide this up. So let me bring this up. Let me divide both sides by 500. So divide by 500. So I can just erase this and say y equals this. Now this is a fraction. If you want to simplify this quickly, here's how I would do it. I would break this up into 5 times 100, okay, because it's easy to divide by 100. 445 divided by 5 would be 89. So if I cancel this with this, I would have 89. Okay, so I have 89 over 100 now. So we know if we divide by 100, just moving my decimal point 2 places to the left. So this would be 89 here. This would go 2 places to the left, so 0.89. Okay, so that's my y. So y is equal to 0.89. So that's the cost of 1 carton of eggs. So apparently where they live, it's super cheap for eggs. Okay, so then now we need to find out x, and of course I could just plug into either equation 1 or 2. So I'm just going to use equation 1. So 745 is equal to 300 times x plus 200 times, you've got your 0.89. Or again, you can do this in fractional form if you want. Remember, this was 89 over 100, okay? So that allows me to just cancel this with this and get a 2. And then 2 times 89 is 178. Okay, so 178. Let me subtract that away from each side of the equation. That will cancel. 745 minus 178 is going to be 567. So this equals 300x. Let me erase this. And we can use a similar trick again. This will help you if you don't have a calculator, right? So this guy right here, if I divide both sides by 300, I can think about 3 times 100, okay? So what's 567 divided by 3? Well, that's going to be 189. So this would be 189, and I'm going to cancel this down here, over 100, right? So let me erase this. So x is 189 over 100, or again, this moves 2 places to the left. So x is equal to 189, move this 2 places to the left. So 1.89 or $1.89. So that's the cost per 1 gallon of milk. So apparently wherever they live, they have really cheap milk and really cheap eggs. Okay, so this does not actually answer our question. Okay, so this is where a lot of students mess up. They say their answer is it's $1.89 for 1 gallon of milk, and it's 89 cents for 1 carton of eggs, and the teacher marks it wrong, and they wonder why. The reason is you have to read the problem, okay? How much will Jim receive as a refund? He only returns the milk, okay? So how much milk did Jim get? Jim got 2 1-gallon containers of milk. Again, the milk is $1.89 a piece. So all I need to do is take the 1.89, again, that was X, that was the cost per 1 gallon of milk, and multiply it by 2. So multiply it by 2. Again, all you have to do is 189 times 2, and then move the decimal point 2 places to the left. So 189 times 2 is 378. So it's 378. Again, move the decimal point 2 places to the left. You get $3.78. So he will get, or he will receive, if you want to say that, $3.78 for his refund. Again, just for the milk. Make sure you read these problems because they throw kind of curveballs at you to make sure you're paying attention. In this lesson, we want to talk about combinations and permutations. All right, so when we get to this section, a lot of students are going to have difficulty determining whether to use our formula for permutations or whether to use our formula for combinations. Basically, we're going to start out with one here where we say that there are 20 applicants for 3 jobs, a JavaScript developer, a data scientist, and a UI engineer. Well, basically the way that you decide here, you're going to be selecting 3 people out of the 20. So if you have the number of ways of selecting R items out of N items, in this case it's 3 out of 20, and repetition is not allowed because the same person can't get the JavaScript developer job, the data scientist job, and the UI engineer job. It's got to be 3 separate people. Well, you want to consider the fact that if the order is important, you want to use a permutation. If the order is not important, okay, you want to use a combination. So here the order is very important to us because it's a different result if I get a job as a JavaScript developer versus if I get a job as a data scientist, okay? So because the order is important, we want to use our formula for permutations, and that's a real easy formula. It's going to be P like this, and then I'm going to put some parentheses. It's going to be N, comma, R. Okay, the N here is going to be the 20. The R here is going to be the 3. We'll fill that in a minute. This equals, you've got your N factorial over, you've got your N minus R factorial. Okay, so in this case, we're going to have P, and we would say 20 pick 3. Okay, that's how you can read that if you want. And this is going to be equal to 20 factorial over, and I made that a little bit long, so let's fix that. So 20 factorial over, in this case, you'd have 20 minus 3 or 17 factorial, okay? If you want to simplify this, you can. Of course, this key is on your calculator if you're using a TI-83 or 84 or whatever the version is you're using. But let's just go through this one. In the future ones, I'm just going to punch it into the calculator and make it a lot quicker. Let's move this up here. This would be what? It would be 20 times 19 times 18 times 17, so on and so forth. But this part here, because the 17 factorial is going to keep going down to 1, you can get rid of that part and just erase this and say it's 20 times 19 times 18, which is going to be what? Well, 20 times 19 is 380, then times 18 is going to be 6,840. All right, let's look at the next one. So we have the senior class at Denton High School, which contains 60 students, wishes to elect a president, vice president, and secretary. So we're choosing 3 students out of the 60 for these 3 positions. The order is going to matter here, right? If someone gets selected as a president, it's a different result as if they got selected as a secretary. So in other words, let's say that John got picked to be the president, and let's say Larry got picked to be the vice president, for example, and let's say that Steve got picked to be the secretary. Well, if I switch things up, I could have the same 3 students, okay, but they got different positions. That's a completely different result, okay? So in this case, we want to use a permutation, and we remember the formula for that. So I'm just going to type this into my calculator. I'm going to do 60, okay, 60. And then you're going to have that key that says N pick R. So it looks like this, a lowercase n, an uppercase P, and a lowercase r. But I'm going to hit 60, this key right here, and then 3, right? Because there's going to be 3 students selected, president, vice president, and secretary. And if you run that calculation, you're going to get 205,320. So 205,320. And again, if you want to use the proper notation there, you've got this P, and then you've got the first number, that's 60, and then comma 3. Okay, so this is what this is equal to. Again, if you go on your calculator, it's the NPR key. Okay, let's look at another example. So we have the junior class at Bracken High School consists of 250 students. They need to elect 2 representatives for the student council. Okay, well, this is a little bit similar to the last question, but we're going to end up using a different formula here because now the order doesn't matter anymore. Okay, repetition's still not allowed, but the order doesn't matter anymore because let's say John gets the first representative position and Steve gets the second one, well, it doesn't matter if we reverse that and Steve got chosen first and then John did, because they're both going to just be representatives. Okay, so the order doesn't matter here. So we want to use the formula for combinations, and we learned this in the last lesson when we talked about the binomial theorem, right? So we have this formula. It's n choose r. So we have this c and then n comma r here. And this equals your n factorial over your n minus r factorial, and then times your r factorial. Okay, so what ends up happening is we're dividing out the duplicates with this extra part here. Okay, this is all you have to remember, because if you've got this part down from the permutations formula, you're just throwing that extra little bit there in the denominator to divide out the duplicates, and that's how you get your combination formula. Okay, so let's erase this real quick. Let's actually plug in the numbers. I'm going to again use my calculator here, because you would basically be doing this C here with 250, 2. And I'm not going to set this up. You're just going to hit 250 and then go to NCR. And I'm going to get a result of 31,125. Okay, let's look at another example. So a local high school is having a marathon qualifier. There will be a total of 40 runners that will participate. The first 8 people to finish the race will advance to the state championship. Okay, so do I want a permutation or a combination? Does the order matter here? We know that repetition is not allowed, right? Because if I'm in the first position, I can't also be in the third position. But does the order matter? Well, no, not for our result, because it just says the first 8 people. So it doesn't matter if I finished first or 7th, okay? As long as I'm in that top 8, okay, I'm going to advance to the state championship. So we would use a combination here. And again, I would just do C, and then I'm going to put 40, 8. Again, just punch this into your calculator. You're going to do 40, choose 8, and that gives us a pretty big number. It's going to be 76 million, and then you're going to have 904,685. All right, let's just look at one more. So the state championship marathon consists of 40 runners. The top 3 runners will earn gold, silver, and bronze medals. So can we have repetition here? No, right? Because if I finished first, I can't also finish second or third, okay? And then does the order matter? Well, yeah, it definitely matters, right? If I finish in first place, that's a different result than if I finish in second place. In one case, I'm getting gold. In the other case, I'm getting silver. So the order does matter. So I want to use the permutations formula. So I would just use my calculator, or again, you've got this P with this 40, 3, if you want to say it's equal to. You can punch this in your calculator, or again, you can use your little formula. I just think it's easier to punch it in on a calculator, because a lot of these, the numbers are just going to be astronomically big. So if we go ahead and punch up 40, and then you do your NPR key, and then 3, you're going to get 59,280 as a result. In this lesson, we want to look at some probability word problems. So at some point in your algebra course or your pre-calculus course, you're going to come across a small section on probability. And I just want to go through some basic word problems that you're going to see and talk about how we can solve these guys. So I'm just going to jump right in. I'll just kind of explain things as we go. It's a very, very easy topic overall. So Jason flips a coin and then rolls a 6-sided die. What is the probability that the coin lands heads up and, okay, I'm going to highlight that, and the die shows an even number? Okay, so when you deal with these problems, you're going to have problems that say and. So some event occurs and some other event occurs. In this case, one event is flipping a coin and him getting a heads up, and the other event is rolling a die and getting an even number. So a 2, a 4, or 6. Okay, when you hear the word and, you need to be thinking about multiplication. So I would take and use this formula. The probability of some event A and some event B happening, okay, in this case, we'd say the coin landing heads up and also the die showing an even number, is equal to the probability of this event A happening times the probability of this event B happening, okay? Now, this is given the fact that they are independent events, meaning the first event does not impact the result of the second event in any way, shape, or form, okay? If he flips a coin, that does not impact the result of rolling a 6-sided die. Okay, so these are independent events. We can just use this formula as it's given. So what we want to do here is just think about the fact that the probability for flipping a coin And getting a heads up is going to be what? It's going to be a half or 50%. We all know this because we've thought about that throughout life at some point, flipping a coin saying, hey, my odds are 50-50. Well, how do we show this mathematically? Where does that 50-50 or the 50% come from? Well, essentially what you do is you think about the number of different ways that you can get an outcome from flipping a coin. Well, you can basically get a heads up or a tails up, right? So there's two possibilities. So I'll put that in the denominator. And then think about what you're looking for. What's the result? Well, I want a heads up, and that can only happen one way, right? So I would put that number in the numerator. Okay, and as we do more of these, this will make more sense. But essentially, this is the formula you want to use. That's where 1/2 comes from. This is basically the number of favorable outcomes. In this case, a favorable outcome would be landing heads up over the total number of possible outcomes. And the possible outcomes here would be landing heads up or landing tails up. Okay, so I know that's 1/2. So let's just say that this satisfies the probability of event A. Now, what about the probability of event B? Let's say that's the die showing an even number. Well, with a die, if it's 6-sided, it can land on a 1. Let me just kind of write this down here in a different color. A 1, a 2, a 3, a 4, a 5, or 6. So we know that the 2 is an even number, the 4, and the 6. Okay, so 2, 4, and 6, those are even numbers. So how many different favorable outcomes can I have? Well, I have 1, 2, 3 favorable outcomes that are possible out of a total of 6. So I would put 3 over 6, which you can simplify to 1/2, okay? And then you just multiply the two together, and let me just kind of erase this. You multiply the two together, and you get 1/4, okay? Now you can leave it as a fraction and say it's 1/4 for the probability, or you can convert it to a decimal, which is 0.25, and then to a percentage and say it's 25%, okay? So essentially the probability of this Jason guy flipping a coin and getting a heads up, and also taking a die and rolling it and getting an even number is 25%. Okay, let's look at a slightly more challenging problem. And in this case, we're going to have dependent events. So Allison, a teacher at a middle school, has 5 boys and 6 girls in her class. Allison randomly selects 3 different students to walk up and give a presentation. Once the presentation is over, the student will leave for the day. What is the probability that the first student is a boy, the second student is a girl, and the third student is also a girl? So you see the problem here is that these events are not independent, okay? Once she picks a student, and we're looking for her to pick a boy first, okay? Then the next time we want her to pick a girl, and then the next time we want her to pick a girl, but each time she's picking, the class size is changing, right? So the number of boys is changing, the number of girls is changing, whatever it is in that scenario, but the class size is constantly changing, so we have to readjust our probability, okay? So we're still going to think about multiplying the probabilities together, but you use a different formula for this. If it was just 2 things, here it's 3, but let's say it was 2 things. So the probability of A and B, okay, if these guys are dependent, and it's just 2, it would be the probability of A times the probability of B given that A has happened, okay? So given that A has happened, what's the probability of B happening? Okay, and in this case, we're going to adjust it because we have one more thing to consider, because now we're thinking about the probability that the first student is a boy. Okay, so that happens. Then the probability that the next student is a girl. Okay, and then the probability that the third student is also a girl. So again, you have and, so you're thinking about multiplication. Okay, so what is the probability on the first graph that that student is a boy? Well, there's going to be 5 boys. Okay, so there's 5 possible choices in there that's going to be boys out of a total of 5 plus 6 is 11 total students. So the first number we're looking at is, I'm just going to write this down here, 5 over 11. I'm just going to put this as the first, okay? So the second is going to be what? Well, if I go back up, I know that the student leaves. He can't be rechosen now. And there's going to now be what? Well, there's 1 less boy, so there's 4 boys. And there's the same number of girls, but the total number in the class now is 4 plus 6 or 10. Okay, so if I think about picking a girl now, it's going to be 6 girls out of a 10 student classroom. Okay, let me just erase this. So let's go down here and put that. Now it's 6 over 10. Okay, so this is second, you'd say. And now what's going to happen for the third choice when we go back up? Well, now there's, let me just kind of scratch this out again, say this is 4. This is going to go down to 5. There's a total of 9 students, and there's 5 girls. So there's 5 over 9. Okay, let me just erase this again. And now I'll say this is 5 over 9, and this is going to be the third pick. Okay, so the probability of picking a boy on the first run is 5 over 11. Then given the fact that that event has already happened, now there's a 6 over 10 probability of picking a girl. Now, given the fact that both of those events happened, the probability on the third pick that it's a girl is 5 over 9. Okay, so again, to get the final probability, or the probability that all these events happen, so this and, she picks the first student as a boy, and she picks the second student as a girl, and she picks the third student as a girl, it's going to be the product of these probabilities. So before we multiply, notice you can cancel this with this and get a 2 here. And then 6 divided by 2 would be 3. And then 9 divided by 3 would be 3. Okay, so I'm going to put a 1 here. And basically what you'd have is 5 times 1, or 5, over 11 times 3, which is 33. So you have 5 over 33, which is the probability of picking a boy, then a girl, then a girl. All right, so now let's talk about some word problems that involve this or. So when event A happens, or an event B happens. So with this, we're going to be adding now. So when you hear and, you got to be thinking about multiplication. When you hear or, you've got to be thinking about adding. Okay, but there's a trick to this. And let me just kind of go through this with this problem. So Katie has 6 nickels and 7 dimes in her pocket. 5 of the nickels and 1 of the dimes are Canadian. The others are from the US. Suppose Katie randomly selects a coin from her pocket. What is the probability that it is a dime or is from the US? This is the key word here, the or, okay? So what you want to be thinking about is the probability of some event A happening or some event B happening is the probability of the event A happening plus the probability of the event B happening minus, okay, this is important, minus the probability of A and B happening, okay? And I know a lot of people use set notation there, so you might see this as well, okay? So the intersection of A and B. However you want to write it, it doesn't really matter. I'm just going to stick to writing and. I think that's a little bit easier for us to understand. Okay. In this particular case, we don't have something known as mutually exclusive events. Mutually exclusive events are 2 events that can never occur simultaneously. So in this particular case, we don't have that because it says, what is the probability that it is a dime or is from the US? Well, we have dimes that are also from the US, so we have to use this full formula. Okay, if we didn't have dimes from the US, we could knock this part out. Okay, this is going to take out the double counting. So let's go through real quick and think about what's the probability that it's a dime. Well, we know that she has 6 nickels and 7 dimes. Okay, well, 6 plus 7 is 13. So 13 coins overall, 7 of them are dimes. So the probability of having a dime is 7 over 13. Then plus, what's the probability, okay, that the coin is from the US, meaning it's not Canadian? Well, it tells you that 5 of the nickels and 1 of the dimes are Canadian. So 6 out of the 13 coins are Canadian. So 7 out of the 13 are American or US currency. So 7 over 13. 7 plus 7 is 14. 14 over 13 is a number larger than 1. When we deal with probabilities, it's either 0, okay, meaning it's not going to happen, up to and including 1. 1 means it's certain to happen. Anything in between means it may or may not happen, okay? But you can't get a probability less than 0 or greater than 1. That doesn't make any sense, okay? So that would be a red flag if you forgot to subtract this out. So all we need to do to fix this is subtract out the probability of A and B occurring, okay? So how many dimes do we have that are also from the US? Well, let's think about that. We know that there are 7 dimes in her pocket, okay, total of 7. And it says that 5 of the nickels and 1 of the dimes are Canadian. So that means that 6 of the dimes are from the US, okay? So that tells me that I need to subtract away 6 over 13, right? Because 6 of the dimes are from the US. So if I crank this out now, I get 7 plus 7, which is 14. And then 14 minus 6, which is 8. So I get a result of 8 over 13. So that's going to be the probability that she picks a coin that's going to be a dime or it's from the US. Okay, Let's look at another example of this. And now we're going to see mutually exclusive events. So Beth has a fruit basket which contains 4 apples, 4 peaches, and 5 pears. If she randomly selects a piece of fruit, what is the probability that it is an apple or a peach? Again, when you see this keyword or, you're thinking about addition, okay? But in this particular case, you don't need that full formula, okay? Because it's not possible for her to select something that's an apple and a peach at the same time. So again, when you think about the probability of some event A happening or some event B happening, it's the probability of A plus the probability of B, and then minus the probability of A and B occurring. And I didn't write my A there. So A and B. Well, in this particular case, you can get rid of this because it's going to be 0. Again, you cannot have a piece of fruit that's an apple and a peach at the same time. Maybe they're working on that. I'm not sure, but in this scenario, it's not possible. So we just think about the probability of A. Let's say that's where she selects an apple. Well, there's 4 apples out of a total of 4 plus 4 plus 5. 4 plus 4 is 8. 8 plus 5 is 13. So the total of 4 over 13, okay, that's going to be your probability of picking an apple. Then plus, what's the probability of picking a peach? Well, again, it's 4 over 13. So all I have to do is just sum these, and I get 8 over 13. All right, so let's wrap up the lesson by looking at an example where we use our binomial probability formula. So the desks in a classroom are organized into 4 rows and 4 columns. Each day, the teacher randomly assigns you to a desk. You may be assigned to the same desk more than once. Over the course of 5 days, what is the probability that you are assigned to a desk in the front row exactly 3 times? Okay. So if you are dealing with a scenario such as this, where you have repeated independent trials, okay, so this is independent because every day you're randomly assigned to a desk and you can sit where you've sat before. And the outcome in each trial is either a success, meaning in this case you will get assigned to the front row, or a failure, okay? So if you want to find the probability of R successes in N trials, you can use this formula. So let me write this down here. And we'll come back up in a minute. So N choose R, okay, we'll remember that. And then times P raised to the power of R. P is the probability of a success. So on a single day, what's the probability of you getting seated in the front row? I'll get to that in a second. Then times 1 minus this P raised to the power of N minus R. So N is the number of trials. So if we go back up, we know that this is going to happen for 5 days. So over the course of 5 days, so N is 5, and the number of successes we're looking for is R, right? So 3 times is we're looking for that number to happen. So N is 5, and R is 3. Okay, so you're just plugging things in. So you have 5 and 3, okay? Then P is the probability of a success on any given day. Well, if we go back, we know that there's a total of 16 desks, right? 4 rows and 4 columns. 4 times 4 is 16. So in the front row, you're going to have 4 desks. So that means you have a 4 over 16 or 1/4 or 25% probability of getting seated in the front row on any given day. So we're going to put a 1/4 here. You could use a decimal if you want. It doesn't matter. It's going to be the same result in the end. R again is 3. And then 1 minus 1/4. If you're using a fraction, you would do 4/4 minus 1/4, which is 3/4. And then raised to the power of N, which is 5, minus R, which is 3. So this is going to be squared, okay? So once you have this set up, you can just erase this and crank this out. So on a calculator, 5 choose 3 is going to be 10. Then if we think about 1/4 cubed, that's going to be 1 over 4 cubed is 64. Then if we think about 3/4 squared, 3 squared is 9, 4 squared is 16. Can I cancel anything before I multiply? I can just get rid of this. I don't need it anymore. Can I cancel anything? Well, yeah, I can cancel a factor of 2 here and here. So this would be 32, and this would be 5. So 5 times 9 is 45 over, what is 32 times 16? That's going to be 512. So 45 over 512, that's going to be your probability of getting seated in the front row exactly 3 days out of a total of 5 days. In this lesson, we want to think about applications of quadratic equations. So throughout our study of algebra, we often come across word problems or application problems. So far in our course, we've only discussed word problems that involve solving a linear equation in one variable. Now we're going to go one step further and take a look at some word problems that involve quadratic equations. So I want you to recall that we have a little 6-step procedure that we can use for solving word problems. And although we've introduced this method for use with applications of linear equations, we can also use it in this section as well. So let's just kind of recap this 6-step procedure. I think you'll find it useful if you write it down and kind of go through the steps when you're solving the problem. So solving a word problem, we have that our first step is to read the problem and determine the question or perhaps questions to be answered. You always want to make sure that you understand the question, or again, the questions that you're being asked to kind of answer. It helps you kind of format things in a way, well, what am I trying to find? Then the second step is to assign a variable to represent the unknown. And in some cases, we're going to have to express other unknowns in terms of this variable. Then third, we want to write an equation that describes the scenario we're given. And then fourth, we're just going to solve that equation. Then fifth, we want to write the answer in terms of the question, or again, perhaps questions asked. And then the sixth thing, probably the most important, we want to check the answer using the words of the problem. And we want to make sure that the answer is reasonable. Okay, you're going to see in some of the examples we get today, we're going to have some solutions to our equation that we set up that don't quite work in the context of the problem we're given. Okay, and we'll get to that later on. All right, so the first few problems we're going to look at are going to involve the Pythagorean formula. I know that most of you already know about the Pythagorean formula, but just in case you don't, it doesn't hurt for a little bit of a review. So the Pythagorean formula basically shows the relationship between the lengths of the sides of a right triangle. So again, we know we have a right triangle because of this signature mark here. This is telling us we have a 90-degree angle or a right angle. Okay, so if you have a right angle in a triangle, it's known as a right triangle. Now, with a right triangle, we have this special relationship between the sides. Okay, so you have these two shorter sides known as legs. You have this here leg A, which is this kind of vertical measure here. And then you have this leg B, which is this horizontal measure here, okay? And then you have C, which is the hypotenuse, okay? The hypotenuse is always going to be opposite of the right angle, so opposite of this, and it's the longest side. So most of you already know this. The Pythagorean formula tells you that A squared, right, which is basically the measure of leg A, that guy squared, plus B squared, again, the measure of B, leg B squared. If I sum those two amounts together, it's equal to C, which is the hypotenuse, that measure, squared. Okay, this is your Pythagorean formula, and it's true for any right triangle that you come across. So using this Pythagorean formula, basically, if we don't know one of the sides of a right triangle, but we know the other two, we can solve for the unknown. Okay, so let's take a look at our first sample problem. All right, so Jason needs to wash a window in a building that is 12 feet from the ground. To avoid a fence, he decides to rest the ladder against the building. For stability, Jason decides he should place the ladder 9 feet away from the building. How long of a ladder will Jason need? Okay, so the first thing we need to understand, again, is what am I being asked to find? And in this case, it's this little question here, right? So how long of a ladder will Jason need? So we'll just highlight that. That's what we're trying to find. So when we go to assigning a variable, we're just going to let x represent exactly what we're trying to find, which is the measure of Jason's ladder. And this is going to be in feet because we're working with feet in the problem. So let's go down here to a fresh sheet. We're going to say that we're going to let x be equal to the measure of Jason's ladder and of course this is going to be in feet. Okay, so in feet. All right, so I'm not going to write feet every time. I'm just going to work with the number parts. We're just going to understand that we're working with feet. All right, so to help us understand what's going on, we have this little illustration here. It's not perfect, but it'll just give you an idea of what's kind of happening in our problem. So when we started out, we said that Jason wanted to wash a window in a building that is 12 feet from the ground. So this guy right here, this represents our window. Okay, that's in our drawing. And basically you could say that it's 12 feet from the ground. So from right here to right here, that measurement, let me kind of draw a little vertical line. Okay, not perfect, but it'll have to do. So this guy's going to be 12 feet. Again, I'm just going to put 12. And then also, it tells us that for stability, Jason decides he should place the ladder 9 feet away from the building. So the ladder, we can't see it because it's hidden in the grass, but let's just say it's about right there. So from right there to right here, let me use a different color. So from right there to right here, that horizontal measure is going to be 9 feet. So let me again just draw a little horizontal line. Okay, again, not perfect, but you get the idea. So this guy is 9 feet. I'm just going to put 9. And I can put my little symbol here. This is going to be a right angle. So I've got that symbol there. So we have a right triangle, right? We have that this guy here, this horizontal leg is 9. This guy right here, this vertical leg is 12. And I'm solving for this guy right here, which is the length of his ladder. This is exactly what I need to find. I could just put this as x right here. This guy is going to be the hypotenuse, okay? So essentially I can say that, again, for my Pythagorean formula, a squared plus b squared equals c squared, where a and b are the lengths of the two shorter sides, or the legs, right? So we know that's 9 and 12. So we just plug in and say that we have 9 squared plus 12 squared, okay, and it doesn't matter the order that you do that in, is equal to, instead of c, I just have x, so I'm going to say this is x squared, okay? So 9 squared we know is 81, plus we know 12 squared is 144. This equals x squared. And 81 plus 144 is, of course, 225. So we get that x squared, okay, x squared is equal to 225. So we can solve this with our square root property. We know that x would be 15 or negative 15, right? Take the square root of each side. So square root of this side is equal to plus or minus the square root of this side. And let me kind of scroll down to get a little bit of room going. And we can basically say again that x is equal to plus or minus 15. Now, does it make sense? Okay, does it make sense for the measure of this ladder to be negative 15? No, it's nonsense. Okay, so that's where, checking your answer when you think about kind of the steps we gave makes a lot of sense. So if you incorrectly said that the ladder could be 15 feet or negative 15 feet, when you go to check that, you can say, okay, that doesn't make sense, right? A ladder can't measure negative 15 feet. That's complete nonsense. So you just have to throw that solution out and say that x, or the kind of length of the measurement of that ladder, is going to be 15 feet, okay? So I'm just going to write that in there and say this is 15, or again, 15 feet. So let's go back up. And again, we can just kind of write a little sentence to describe our answer. So how long of a ladder will Jason need? Well, we'll say that Jason needs a ladder. Jason needs a ladder that is 15 feet long. Okay? So checking this is really, really easy. Again, we just go through our Pythagorean formula. And it's easier to check something like this by looking at the picture again, just so you get an idea what's going on. Again, we said that with Jason, he needs to wash a window in a building that's 12 feet from the ground. So this is where the window is, and this is where the ground is. So the distance from here to here, that's 12 feet. Okay, so that's where we got the 12 from. And then to avoid a fence, he decides to rest the ladder against the building. So that's why this ladder is drawn in this manner, okay? And then basically it says that for stability, Jason decides he should place the ladder 9 feet away from the building. So from here to here is 9 feet. That's where we got that 9 from. Okay, so this part all checks out. So then we're asked, how long of a ladder will he need? Well, again, we see that we have a right triangle, and so we can use our Pythagorean formula. We plugged in, we got 9 squared plus 12 squared equals x squared. X was the length of the ladder. And so we got 81 plus 144 on the left side of this, which is 225. So we ended up with x squared equals 225. We took the square root of each side, right? And we found that we had x equals plus or minus 15. We threw out negative 15 because it didn't make any sense. So that's how we got our solution, where we said that Jason needs a ladder that is 15 feet long. Okay, so this solution is correct. All right, let's go ahead and take a look at another one. So we have that Larry and Steven were both parked in the same parking garage. Larry leaves first and drives north at 50 miles per hour. 1 hour later, Steven leaves and drives east at 70 miles per hour. How long after Larry starts driving does it take for the two cars to be 290 miles apart? So again, we want to understand the main question. And here it's just to find how long after Larry starts driving does it take for the two cars to be 290 miles apart. So for this problem, we're going to end up using our Pythagorean formula, and we're also going to use the distance formula that we see with motion word problems, right? The distance equals the rate of speed times the amount of time traveled. All right, so before we kind of get into that, though, we need to assign a variable to represent the unknown. In this case, we're going to end up having kind of two unknowns because we don't know how long Larry's going to drive for, and We also don't know how long Steven's going to drive for. Okay, so what we're going to do is, since Larry leaves first, we're going to say that X is the amount of time that Larry drives for before the two are 290 miles apart. Okay, so let's go down here to a fresh sheet. And I'm just going to say we're going to let X be equal to the amount of time. And I'm just going to put for Larry. Okay, and we know what that means. It's going to be specifically in hours, and it's going to be the amount of time that Larry drives for before, again, the two cars are 290 miles apart. Now, for Steven, we can kind of base his time on Larry's, right? We know Larry's time is X. Well, for Steven, we know that 1 hour later, Steven leaves. So he's been driving for an hour less at this point when they are 290 miles apart. So I can just go X minus 1 to represent Steven's time, okay? So we're going to say then, I'll do that in a different color. So we'll say then X minus 1, this quantity is the amount, again, of time for Steven. Okay, we'll just make it nice and simple like that. You could write out something that's really long and say it's the amount of time for Steven, in hours before they're 290 miles apart, but you kind of get the idea, and we want to make it as short as possible. All right, so the next thing we want to do is just come down to a little table, just organize our information so that we know what's going on. So our distance formula, in case you forgot, the distance traveled, which I'm going to say is D, is equal to the rate of speed, which is R, multiplied by the amount of time traveled, which is T. Okay, so the rate of speed is in miles per hour, the time is in hours, and the distance is going to be in miles. Okay, and then we have two participants here. We have Larry, and then we have Steven. Okay, so those two guys are involved in the problem. So what information do we have? Well, we know the time because we said that Larry's going to be driving for X hours when the two are 290 miles apart. And we said that Steven, since he drives an hour less, is going to be driving for X minus 1 hours, again, when they're 290 miles apart. Now, the rate we can get directly from the problem. It tells us specifically that Larry leaves first and drives north at 50 miles per hour. So this 50 miles per hour is going to be his rate of speed. And then for Steven, he leaves and drives east at 70 miles per hour. So 70 is going to be his rate of speed, again, in terms of miles per hour. So let's just fill this in. For Larry, it's going to be 50 miles per hour. For Steven, it's going to be 70. Now, if I have a rate of speed and I have a time, I have a distance, right? Because I can just multiply. R times T gives me D. So 50 times X is 50X. And that's my distance that Larry's going to travel, again, when they're 290 miles apart. So for Steven, he's going to have traveled 70 times the quantity. Remember, this is a quantity and this is multiplication. So put parentheses. So times the quantity X minus 1. And you can go ahead and simplify this now because you're going to have to later. You can just say this is 70X minus 70. So we'll write this as 70X minus 70, just so that we have it ready to go. Okay, so before we kind of set up our equation, I want you to think about something, because usually at this point, people make a drastic mistake. They're used to kind of solving these in another scenario, kind of with the opposite direction travel. With that one, they end up saying, okay, well, the distance Larry travels, which is 50X, plus the distance Steven travels, which is 70X minus 70. They sum those two amounts and they say, okay, well, that's got to be equal to 290, okay? This is wrong. This is what we saw kind of earlier in the course. This is not the current setup, okay? What we have here, and just to kind of illustrate what's going on, I drew a little picture, a little illustration. And basically what we have, again, is another application of the Pythagorean formula, because we end up with something that is a right triangle, okay? So we have that Larry is driving north. So you can picture him starting from here. Let's just say that's the parking garage. And he drives north, which on every map that you look at, that's basically going up, okay? So this is going to be a vertical leg for the right triangle. And we know that measure, the distance, if I go back, is going to be what? It's 50X. So let's go back here. And I'm just going to write this in as 50X. And we know that's for Larry. So I'm just going to put a little arrow here and say that's L for Larry. Okay, that's his distance. That's, again, from here to here. That's the point he's going to be at when these two guys are 290 miles apart from each other. Now, for Steven, let me put a little S here and go this way. He's got this horizontal leg. So this guy to this guy, that distance there, again, if we go back up, that's 70X minus 70. So let me put this here as 70X minus 70. Okay, so you can obviously see what's going on here. We've got our two legs for this right triangle. And again, the formula is that a squared plus b squared. Okay, we square each of the legs and we sum those amounts together. And this is equal to the hypotenuse squared. So c squared, again, normally this is c. But in this case, we have kind of expressions involved. So we just kind of plug those in and work with those. So we end up with, let's just say 50x, that quantity squared, then plus this guy is the quantity 70x minus 70. The whole thing is squared, so make sure you wrap it in parentheses. And this equals our c, or our hypotenuse, is going to be 290. So that amount, that's going to be squared, okay? So we're going to just copy this and go to a fresh sheet because we'd run out of room here because this is going to be quite tedious. So let's just paste this in here and let's get started. All right, so for 50x squared, if we wanted to simplify that, I would need to square 50 and also x. So that would give me 50 squared times x squared. Now, 50 squared is 2,500. So let me just replace that and say it's 2,500. Okay, so then plus. Now, don't make the mistake of doing this. A lot of students, again, I've said this throughout the course, they do what? They say this is 70x squared minus 70 squared. Okay, that is wrong. This is wrong. Don't do that. Remember, if you have something in here with addition or subtraction, you've got to expand it. Okay, remember our special products formula. You can use that here to do this pretty quickly. You're going to square the first guy, which is 70x, that whole thing squared, right? So the whole thing is squared. So it's 70 squared, which is 4,900, times x squared, okay? Then you're going to have minus. You're going to have 2 times this guy times this guy. So it's 2 times 70x times 70. Okay, and we'll just go ahead and crank that out real quick. 2 times 70 is 140. Then times 70 again would be 9,800. So basically what you'd have is minus 9,800x here. So minus 9,800x, or you could say 9,800x, whatever you want to say. And then lastly, you need to take this 70, the last term there, and square it. So we're going to go plus 70 squared, we already know is 4,900. So this is 4,900. Okay, so that's this side right here, and this equals 290 squared is 84,100. Let me slide this down so I can fit this all in one line. So 84,100. Okay, so we have kind of some big numbers involved here. So let's do some simplifying, and then I'll show you what we can do to kind of make this as easy as possible. All right, so 2,500x squared plus 4,900x squared, those are like terms, so we can combine them. So if I had 2,500 and 4,900, I get 7,400. So this is 7,400x squared. Then minus 9,800x, I can't do anything with that as of yet. So we'll just leave that as it is. And then what I can do over here, I'm going to subtract 84,100 away from each side of the equation. Okay, and what that's going to do is that's going to give me 0 over here on the right side. Okay, because I'm solving a quadratic and I want it in the format of ax squared plus bx plus c equals 0, so I can use my quadratic form. Okay, so 4,900 minus 84,100 is going to give me minus, or negative, 79,200. Again, this equals 0. Now, if you want to plug these into the quadratic formula as they are, you can. Most of you, I know pretty much all of you are going to be using a calculator. I'm using a calculator. If you're working with bigger numbers or smaller numbers with a calculator, it doesn't really matter, right? It does the calculation for you. But just to make this a little easier, a little simpler. So what we'll notice here is that each of these numbers ends with 2 zeros. This guy over here is a 0, so it's not going to matter. But if they all ended 2 zeros, they're divisible by 100, right? So if I divided every part of this equation by 100, on the right, 0 divided by 100 is still 0, so that's fine. Basically, I would just knock 2 zeros off from everything, right? So that makes it a lot simpler, right? You have 74x squared minus 98x minus, and this comma would disappear. You'd have 792, and this equals 0, okay? Perfectly mathematically legal to do that. And you would notice that you could also still divide each part by 2. So if you wanted to make it even simpler, you could say that 74 divided by 2 is 37, so 37x squared. And then 98 divided by 2 is 49, so minus 49x. And then minus, if you take 792 and you divide by 2, you would get 396. And we can say this is equal to 0. Okay, so this is a lot simpler, a lot easier to work with. So let's kind of drag this up here and see what we got now. So we're going to use our quadratic formula. So again, this is going to be A, this is going to be B. Okay, it's the whole negative 49. and this is going to be C, again, the negative 396, okay? And I circled the negative ones because sometimes you get confused and you try to just take the number part without the sign. When it's positive, obviously it doesn't matter, right? You're not bringing a sign with you. It's just positive, so it doesn't have a sign in front of it. All right, so with the quadratic formula, again, in case you have forgotten it, x is going to be equal to the negative of b plus or minus the square root of, you've got b squared minus 4 times a times c. This whole thing is over 2a. So all I'm going to do is just plug in. Okay, very, very easy. So for negative b, again, b is negative 49. The negative of negative 49 is 49. Plus or minus, you've got b squared, so you'd have negative 49 squared. So let's just go ahead and do that real quick. If I square negative 49, I get 2,401. So let me write that in. 2,401. That's kind of hard to fit in there. So let me redo this. So square root of 2,401, again, minus 4 times. For A, I have 37. And then for C, I have my negative 396. And we can crank this out now or come back in a minute. Let's just come back in a minute. For A, we have what? We have 37, so let's plug that in there. All right, let's do our calculation. So negative 4 times 37 is negative 148. Then times negative 396 is going to give me 58,608. So let's just put plus 58,000, again, 608. If we sum 2,401 and 58,608, we get 61,009. Okay, so let's write that there. So 61,009. Then down here, 2 times 37, we know from earlier is 74. Okay? All right, so what is the square root of 61,009? Well, if you punch that up on a calculator, you're going to get 247. So let's erase this and put 247. Now, we have two cases here, but you're going to see that one of the cases ends up being nonsense, right? Remember, we're solving for x, which is the amount of time that, in this particular case, Larry's going to travel for or drive for before the two cars are 290 miles apart. So you know that you can't have a negative amount of time. That wouldn't make sense in this scenario. I can't say, well, he drove for negative 18 hours, as an example. Okay, what does that mean? It doesn't mean it's nonsense, so you have to throw it out. So the one of these guys that's going to make it negative, we would just immediately exclude that, okay? So the first scenario would be that x is equal to 49 plus 247 over 74. So we keep that one. The other scenario was what? It's x is equal to 49 minus 247 over 74. This is going to end up being negative, so you can just throw this out, okay? You don't need to worry about that solution at all. So focusing on this one, 49 plus 247 is 296. So if you had 296 over 74, you would have 4. Okay, so nice and simple. So x equals 4. Again, that tells me that Larry drove for 4 hours before the two cars were 290 miles apart. Again, x was the amount of time for Larry. X minus 1 was the amount of time for Steven. So this guy is 4 and this guy is 3, right? Because 4 minus 1 is 3. So again, to officially answer this, how long after Larry starts driving does it take for the two cars to be 290 miles apart? We'll say Larry drives for 4 hours before the two cars are 290 miles apart. Okay, and if you want to check this, again, it's easy to go to the diagram and kind of visually see what's going on. You want to mark down some information that Larry's going at 50 miles per hour and Steven's going at 70 miles per hour. So let's go to the little drawing we have, and let's see if we can make sense of this. We can erase all this. We can actually leave the a squared plus b squared equals c squared. We'll actually use that. So if I plug in a 4 for x, I'd have 200. So that's for Larry. We know that he drives 200 miles from here to here, and that's basically over the span of 4 hours, and that's how far he's going to have traveled when he gets to this point here when they're 290 miles apart. And then for Steven, you can plug in a 4, which is what x is. You get 70 times 4 is 280. 280 minus 70 is 210. Or you could, again, do it kind of manually and say, okay, well, he was going 70 miles per hour. He only drove for 3 hours. 70 times 3 is 210. So either way, you get 210 as his distance from here to here, okay? So again, we know about the right triangle. If this is 200 and this is 210, plugging in, if one is 200 and the other is 210, if we sum those two squares, it should be this guy right here squared. So is that true? 200 squared is what? Well, punch that up on a calculator, you're going to get 40,000, okay? 210 squared, punch that up on a calculator, you're going to get 44,100. And if you sum those two amounts together, you are going to get 290 squared, because that's going to be 84,100, okay? You can easily see that. 40,000 plus 44,100 is 84,100. So we can say here our answer is correct. Larry drove for 4 hours before the two cars were 290 miles apart. All right, so another common type of problem in this section involves finding an unknown area. So generally speaking, these problems are going to deal with some type of rectangular shape. This could be a pool, it could be a garden, it could be a quilt. The example we're going to see next is going to be a rug, okay? So something rectangular in nature. So what I want to cover really quickly is just the formula for the area of a rectangle. So we have a rectangle on our screen, we have our length, and we have our width, okay? So the area of a rectangle, we'll put A here, is equal to the length, which I'm going to put capital L, times the width, which is capital W, okay? So that's the formula for the area of a rectangle. You might want to write that down because we're going to use it immediately in the next problem. So just as a quick example, suppose I said that the length here was 8 inches, and suppose I said the width here was 6 inches, okay? And I said, well, what's the area of this rectangle given this information? Well, the area, I'll just put capital A, is equal to what? It's 8 times 6, which is 48. You're just multiplying. And then inches times inches, you multiply your units. That's going to be inches squared, or you could say square inches. So we're going to say this is 48 square inches, okay? And let me make this Q a little bit better. Okay, so again, 48 square inches when we have a length of 8 inches and a width of 6 inches. All right, so again, let's put this formula to immediate use. So we have here for our sample problem that Jamie wants to put a rug in a bedroom that is 15 feet long and 12 feet wide. She wants to leave a strip of uncovered floor that has a uniform width around the rug. After looking at pricing information, she decides that she can afford to buy a rug with an area of 108 square feet. Okay, so what are the dimensions of the rug? So again, what are we being asked to find? Well, given the fact that she can afford to buy a rug that has a maximum area of 108 square feet, we want to know what are the dimensions of the rug, okay? Well, to solve this problem, if you haven't seen it before, it might be a little challenging for you to kind of set it up, okay? So usually what you do with this is you draw a little diagram, and I have that already set up. And what you'll see here is that the entire rectangle is meant to represent the bedroom, okay? And then you have this kind of smaller rectangle, which represents your rug. And then the brown you see, that's the strip of uncovered floor, okay? That's around the rug, okay? And that's actually the key to understanding this problem. So when we go back up, I just want to read this part one more time. She wants to leave a strip of uncovered floor that has a uniform width around the rug. This is very important. So this uniform width around the rug, okay? Let me go back down, and we're just going to label a few things. So what do we know? We know the length of the bedroom, or the measurement from here to here, is 15 feet, okay? That's given in the problem. We know the width, the measurement from here to here, is 12 feet. That's given to us in the problem. We also know that this kind of strip of uncovered floor has a uniform width. So in other words, I know from here to here, and then from here to here, and from here to here, and from here to here, this is all going to be the same all the way around. The width is all the same, okay? So the key to this problem is letting a variable like x, or whatever you want to use, represent that uniform width for that strip of uncovered floor, okay? So I'm just going to say this is x, this is x, this is x, and this is x. Okay, so given the information that we have now, can you see how you would set up and find the dimensions of the rug? Okay, so for the rug, we want to know what's the length and what's the width. Well, for the length, I know the length of the bedroom. It's given to me, it's 15 feet, so that's from here to here. If I want the length of the rug, well, I need to subtract out kind of from here to here and from here to here, okay? So what's that measure? And I kind of went over there, so let me draw that a little bit better. So what's that measure? Well, it's going to be 15, the total amount, minus this, which is x, okay? This is x, and then minus this, which is x. So 15 minus x, which is going to be 15 minus 2x, okay? So that's going to be my length of the rug. Now, For the width, it's a similar thought process, okay? The width is going to be from here to here. And again, I just want to think about the width of the whole room, which is 12 feet. So I'm just going to put 12 there. And I want to subtract out this guy right here, which is x. And I want to subtract out this guy right here, which is also x. So 12 minus x is 12 minus 2x, okay? So now I have a length as an expression, 15 minus 2x, and I have a width as an expression, 12 minus 2x. So let's copy that real quick. And I'm just going to paste that there. And what we know from our problem, it tells us that she can afford to buy a rug with an area of 108 square feet. So we're going to assume that that's what she buys. So my length times my width gives me my area. So what I'm going to do is I'm going to say 15 minus 2x, that quantity, that's my length, multiplied by the quantity 12 minus 2x, that's my width. This should equal my area, and we're told that the area is 108 square feet. So I'm just going to put 108. Okay, so I'm going to solve this equation for x, and that's going to allow me to find out what is the length and what is the width for my rug that Jamie has. Okay, so 15 minus 2x times 12 minus 2x, we're going to use FOIL for that. So 15 times 12 is 180, and then 15 times negative 2x is minus 30x. Negative 2x times 12 is minus 24x. If I combine like terms, I'm going to have negative 54x, so minus 54x. All right, so then we have negative 2x times negative 2x, which is going to be plus 4x squared. And then this is just equal to 108. Okay, so let me kind of rearrange things here. Let me put this as 4x squared minus 54x plus 180 is equal to 108. Now, what I want to do is subtract 108 away from each side of the equation so that I can have 0 on the right side. And I can go ahead and use my quadratic formula, or you could factor, whatever you want to do. Okay, so in this case, I'm going to have 4x squared minus 54x, and then plus 180 minus 108 is going to be 72. This equals 0. Now, if you want to do this, this is an optional step. You don't need to. You can divide each part here by 2. Okay, that's going to give you smaller numbers to work with. So if I divide this by 2, this by 2, this by 2, and this by 2, I'm going to get 2x squared minus 27x plus 36 equals 0. Okay, that's just something I did to give us smaller numbers to work with. Again, completely optional. All right, so now let's use our quadratic formula. Again, you can solve this one with factoring, but I'm going to use the quadratic formula. So this guy right here, this is going to be A. This guy right here, this is going to be B. This guy right here is going to be C. Okay, so I'm going to plug into x equals the negative of b plus or minus the square root of, you've got b squared minus 4ac, the whole thing's over 2a. Okay, so the negative of b is negative 27, so just plug that in there. Then b squared, you've got negative 27 squared. 4 times a times c, a is 2, c is 36, and then a again is 2. Okay, so we filled all this in, now we can just kind of crank it out. The negative of negative 27 is 27. Okay, so that's easy enough. Negative 27 squared is 729. So this would be 729. Negative 4 times 2 is negative 8. And then negative 8 times 36 is negative 288. So this is basically minus 288. If I do that calculation real quick, I'm going to get 441, right? 729 minus 288 is 441. If I took the square root of 441, I would get 21. Okay, so this is 21 here. And then 2 times 2 is 4. Okay, so we're going to get 2 answers. You're going to find that one of them doesn't work, but we'll get to that in a minute. So 27 plus 21 is going to be 48. 48 divided by 4 is 12. So x equals 12. And then also 27 minus 21 is 6. 6 over 4, you can say that's 3 halves or 1.5. So let's take these back to our illustration. And we're going to see if they make sense. Okay, so let me paste this up here. So can x be 12? Remember, I'm plugging in for x in each case. So I'm plugging in here and here. Well, 2 times 12 is 24. 15 minus 24 is negative. Okay, it's going to be negative 9. Does it make sense for this rug to have a length of negative 9? Okay, no, it can't be negative 9 feet. That doesn't make any sense. It's nonsense. So you get that when you solve these problems. You just have to reject one of the solutions. So go ahead and throw that out. Okay, you can't use that. Can we use 3 halves? Yes, we can. 3 halves is 1.5. If you multiply 2 by 1.5, you get 3. Okay, so what you'd have in each case, you could just replace this with 3 and this with 3. 15 minus 3 is 12, so that's the length of the rug. And 12 minus 3 is 9, so that's the width of the rug. Okay, so we basically found our answer for our problem. So what are the dimensions of the rug? We'll say that Jamie's rug, okay, Jamie's rug has a length of 12 feet and a width of 9 feet. Okay, is that consistent with what we're told in the problem? Well, 12 times 9 is 108. Feet times feet is feet squared or square feet. So that does match up with this, okay? But you can also check to make sure that it is consistent with the rest of the problem. So when we come back to our little illustration, again, we just want to check that this 1.5, this figure matches up with what we got, right? So this 1.5 is the width of this strip of uncovered floor, which has a uniform width. It's supposed to be the same all the way around. So it's 1.5 all the way around. Let me write that like this. Okay. So does that make sense? Well, if the length or the measurement from here to here is 12, and I add 1.5 for this and 1.5 for this, well, yeah, 12 plus 1.5 plus 1.5 is 12 plus 3, that's 15. That's this guy right here, the length of the bedroom. Okay, so that makes sense. Same thing's going to happen for the width. So the measurement from here to here, we know that's 9, then plus another 1.5, plus another 1.5. 9 plus 3 is 12. Again, that's given to us in the problem. So that checks out. And we already checked the fact that the rug matches up and it gives us 108 square feet. So we can basically say we're good to go. This rug has a measurement of 12 feet for the length and 9 feet for the width. All right, so let's wrap up the lesson and talk about another common problem you see in this section. We're going to be dealing with the height of a propelled object in feet. So when we get to this section, we basically have a little formula that we work with. If air resistance is disregarded, the height of an object that's propelled directly upward can be thought about with this formula. So we have h is equal to negative 16t squared plus v sub 0 times t plus s sub 0. So when you're in this section in your algebra course, you're going to be given this formula. They're going to give you stuff to plug in, and then you're going to have to solve for something. Okay, so h is the height of the projectile in feet, t is the number of seconds, v sub 0 is the initial velocity in feet per second, and s sub 0 is the initial height in feet. So when we're talking about height, if I get a height of 0, that means I'm on the ground, okay? If I get a height that's positive, let's say it's 50, let's say for h, again, it's 50, that means I'm at a height of 50 feet in the air, okay? If I get an initial height in feet, it's the same thing. If I got 50, that means I'm launching from 50 feet. All right, let's look at a sample problem. I think you'll find this to be very, very straightforward. A toy rocket is launched vertically upward from an initial height of 500 feet. The initial velocity is 20 feet per second. Find out how long before the rocket will hit the ground. Okay, so obviously we're just answering this part right here where it says to find out how long before the rocket will hit the ground. We're just going to take the formula. Let's go back for a second. And we're going to grab this guy, and I'm just going to rewrite it right here real quick. So h is equal to, you've got negative 16t squared. And you got to be careful here because the t gets confused with a plus sign. So I'm going to put that in a different color. So plus, you've got your v sub 0 times t, or you could say t times v sub 0. So let's put v sub 0 times t. And again, you've got another plus sign, so let's do that in a different color. And then you have your s sub 0. Okay, so this is your formula that you're working with. Now, we can plug in a lot of information here. It says that the initial height is 500 feet. S sub 0 is your initial height. So you can just go ahead and erase this and put 500 there. And then it says the initial velocity is 20 feet per second. So that's this v sub 0 here. So I'll erase that and put a 20 there. Okay. So now we have two variables involved. I have h and I have t. But it says find out how long before the rocket will hit the ground. We already said that when the rocket hits the ground, h is 0, right? That's the height. So I can just replace h with 0. And all I have here is a standard quadratic equation, right? So I have negative 16t squared plus 20t plus 500. If I replace t with x, it's going to look very familiar for you. Okay, and I'm not going to keep it this way. I'm going to keep it with t because that's consistent with our formula. But if you were struggling and you couldn't kind of grasp what's going on, just replace it with x, solve it, and then go back and replace that for t. Okay, not a big deal. So I can solve this using the quadratic formula. I can also solve this particular one by factoring. What I'm going to do to make this a little bit simpler, I'm going to divide everything by 4, just so we have smaller numbers to work with. So divide this by 4, this by 4, this by 4, and this by 4. I'm going to get, and I'm also going to kind of rearrange things. So I'm going to get negative 4t squared, then plus, I'm going to have 20 over 4 is 5, so 5t, and then plus 500 divided by 4 is 125. This equals 0. Okay, let's go ahead and plug into the quadratic formula. So we know that what? We know that this guy right here, this negative 4 would be A. We know this guy right here, this 5 would be B, and this guy would be C, okay, this 125. So instead of x, we have t, so we're going to say t is equal to, you've got the negative of b. B is 5, so negative 5, plus or minus the square root of, you've got b squared. Again, b is 5, 5 squared is 25, minus 4 times a is negative 4, times c is 125. And I'll do this in a minute. This is over 2a is negative 4, so 2 times negative 4 is negative 8. Okay, so negative 4 times negative 4 is plus 16. So let's just put plus, you'd have 16 times 125. That's going to be 2,000, okay? So 25 plus 2,000, you do this all in one shot. This is 2,025. If you punch up square root of 2,025 on a calculator, you're going to get 45, okay? So this guy's 45. Now, one of these solutions you're going to throw out, okay? Because we're solving for t, which is time. So it's got to be a positive value or 0, okay? It's basically got to be non-negative. If you end up with something like negative 800 seconds, what does that mean, right? It doesn't mean anything. Again, it's nonsense. We've seen that throughout this kind of lesson. If you get something that doesn't make sense, just reject it, throw it out, okay? So the first one would be negative 5 plus 45. So let me kind of do that over here. So t equals, so negative 5 plus 45, which would be positive 40 over negative 8. This would end up giving me negative 5 seconds, which again doesn't make sense. So we're just going to throw that solution out. Okay, we don't need it. Then t is equal to, the other one is negative 5 minus 45, which would be negative 50. And then divided by negative 8, negative over negative is positive. I can also simplify by dividing each by 2. So this would end up being 25 fourths. Now, in decimal form, that's 6.25, and that's what we're going to use. So let me erase all this. We don't need any of it anymore. So find out how long before the rocket will hit the ground. Well, we found that it's going to happen at 6.25 seconds, right? So we'll say that the rocket will hit the ground at 6.25 seconds, okay? And again, a very, very easy problem. Very, very easy if you get this question on homework or tests. You just plug into the formula and you're basically just have to set up your quadratic equation and solve. Okay, so how about checking something like this? What would we do? Well, again, we just go through the formula again. It's h is equal to, we have your negative 16 times t squared. For t, I've got 6.25. Again, I can plug in a fractional form here to make it a little simpler. So I'm going to put 25 fourths, this guy squared. Then plus v sub 0, the initial velocity was 20. So we're going to put 20 times, you've got your t, which again, I'm going to put 25 fourths for that. And then you've got plus your s sub 0, which is 500. That was the initial height in feet. So that's 500 feet. Okay, so h is supposed to be 0. So we just check this, make sure we got the right answer. So let's go back down. So 25 squared is 625, 4 squared is 16. So this would be 625. I'm going to write that a little better. So 625 over 16. This guy's going to cancel with this guy and give me a negative 1. So this would basically be negative 625 here. And most of you can already see this is going to work out. This cancels with this and gives me a 5. 5 times 25 is 125. So basically what you have is 125 plus 500, which is 625. And then that's being added to negative 625, so that does give you 0, right? You end up with 0 equals 0. So this is consistent with what we're told in the problem. So we can say here that our answer or our solution is correct. The rocket will hit the ground at 6.25 seconds.